Yes, hi guys, a very good morning everyone. Very good morning and welcome to the GATE 2025 Revision Mega Marathons by OM Institute. Welcome all of you to the platform of OM Institute. Okay, very good morning everyone. A very good morning everyone. Come on everybody, quickly keep on joining. Come on all, quickly keep on joining the session and inform all your friends that the session is now live. Let us get started with this revision mega marathon for control systems. Very good morning all of you. Let me just come on all, quickly keep on joining the session and inform all your friends that the session is now live. Let us get yes, the video and all looks good at my end. Very good morning everyone. Killer Gaming, Avinash, Nagapuri, Sajin, good morning Aditya, Adi, Hamida, Shrikant, very good morning everyone. All right, so I hope you're all ready and excited for this revision of the control systems. No, Meet, even, if you look into all the EC faculties also, you'll be really, studying in a very fantastic manner. But if you have any confusions, contact our support number. They'll call you, and or you call our support numbers. They'll guide you if you are having any confusions regarding to the EC. Okay, good morning Vamshi, good morning Sai Bhargav, good morning Monica. Very good morning everyone. Okay, come on, let everybody join quickly and let's begin up this discussions on the control system mega marathon. Good morning Rohit. All right guys, come on, share the session to all your groups, to all your Telegram and WhatsApp group, to all your friends, to all your or anybody you know preparing for GATE examination, because this is going to be a quick important revision about control system. To share it in all other groups you are connected with respect to your colleges or GATE preparation. Good morning Rahul. So guys, let's get started. People will keep joining. Okay, and guys, not only control system, other marathons are also going to come up for you. Yes guys, I hope you know about this. This is a brief intro about me. Okay, so other marathons for other subjects are going to come up. You're going to get a PMF, you're going to get a power systems, power electronics, you're going to machines, you're going to get a EDC, you're going to get up signals and lot of things, etc. You're going to get up under this complete marathon that has been designed by the team of the OM Institute. Today is the first session. We are starting with the control systems. Right guys, and you're going to yes, signal and system also going to come up, Ganesh, don't worry. Okay, so yes, everything going to come up to support your revision for GATE 25. If you're not subscribed to the channel, only thing is be subscribed so that you are updated what event is happening at what time, and you will be notified on time to time. So do not forget to subscribe to our channel. And guys, quick information that yes, for the GATE 2026 and 26, all the online courses of OM, okay, the OM online scholarship test for EE and EC is on the coming Sunday, that is 19th of January, 6:30 p.m. onwards. Okay, where the top 3 performers will be getting 100% scholarship, and based on your rank slabs you have different discounts as it is mentioned. The syllabus also containing basic subjects has been mentioned in front of you. You can go through it and register for this particular scholarship test if you are willing for the GATE 26 and GATE 27 online preparation. Also guys, so new batches for of course the new batches for GATE, also offline GATE batches will come up after the GATE examination. Okay, and this is the update about the AE offline batches. 23rd January the new AE offline batch, okay, for Telangana and AE examinations, both of them AP examinations going to come up, right? Okay, going to come up. Right, so I'll ensure a very good revision of control system, Nagadeep. I have not even counted. I was preparing last night the entire content. So let's get started. With first of all, okay, the first order control systems. Okay, sometimes very fundamental questions from the transient and especially steady state. Okay, transient also you get the question, but steady state definitely produces frequent questions. So let's get started guys now. with the content one by one. Let's keep on flow on the topic. So as we know, first order control system is one. Defining directly, there are different ways to define order. Okay, directly defining, with respect to the transfer function, the highest power of s in the denominator of transfer function equal to 1. That makes a first order system, and the transfer function is 1 upon 1 plus st. Maybe in the notes I have included all the definition, but let's keep on discussing important bullet points, and definitely, definitely I'll also be, discussing important questions also, rather than only the review of 3. I'll also be discussing the important questions also. Yes. So 1 upon 1 plus st, where t is known as the time constant, which I am going to define. What do you understand by the time constant? And as we know that impulse response of any system makes a Laplace transform pair with the transfer function of the system. Okay, so since the transfer function is of the form 1 upon 1 plus st, impulse response will be coming out to be 1 upon t e power minus t by t. Important discussion on the step response. So step response, we all know, is the response of the system when the input applied is a step signal. Okay, when the input applied is a unit step signal. Okay, RT equal to 1 for t greater than equal to 0. For t greater than equal to 0. And on solving through Laplace transform, the output that we get, of course, guys, we don't need and we should not spend any time on deriving any of the things right now. Okay, so finally, after solving some basic Laplace transform, very basic Laplace analysis, what is the output we get is Ct equal to 1 minus e raised to the power minus t by t. Now, important point here is, what is the waveform for 1 minus e power minus t by t is here shown in front of you. But the important point is, if you talk about this exponential term, this is an exponential decay term. Okay, which is not going to last for a long time. Okay, how much does it long? That all depends on the time constant and settling time of the system. Yes, I'll be sharing you this PDF. Okay, so everything that is written, that is printed, and that what I am writing, every question, every solution you will get in the PDF. Okay, you are going to get everything inside the PDF. Right, I'll share you the PDF in the Telegram after the end of the session. Okay, so if you specifically talk about this exponential term e power minus t by t, we know that it's an exponential decay term, okay, which decays out with respect to time. So this is something which is not going to be there for permanent. Okay, it is something which is not going to be there for a long amount of time. It exists, it is dominant initially for initial values of time, and as the time passes away, it keeps on decaying, and finally when this decays, when time becomes very large, this is going to tend to 0. Okay, this is going to tend to 0 when the time becomes very large, and hence when the time becomes very large, that is limit t tending to infinity, what you are going to get is 1, because this gets converted to e power minus infinity, which is 0. Okay, e power minus infinity, which is 0. Okay, and this is what is known as the steady state value. The steady state value of the response means the value of the response, the value of the output when time becomes very large, limit t tending to infinity, Ct, which is equal to 1. Okay, so when you talk about, the behavior of any system, okay, of course, using this exponential decay, we come to this waveform. But when you talk about the behavior of any system, the time response of any system, it is broken into a transient part and a steady state part. It is always broken into a transient part, which almost like defines the initial part, because every system has a delay. Okay, it needs the time, it needs a specific time to respond to the input. Okay, the input you applied abruptly, input you made it 1, okay, like a DC voltage, but okay, a first order system, just like a RC network. A very common example of a first order control system is a RC network, where suppose you applied a DC volt of 1 and you want the capacitor to charge, and what is the charging waveform for capacitor is something that I was showing you. Okay, but we all know that capacitor won't be charged immediately, and it takes a particular time, okay, to settle to its value. Okay, so in any behavior we talk about the transient part and the steady state part. Okay, transient, which almost like initial behavior of the system. Okay, something which is not permanent is actually the literature meaning of transient. Now, why the transient part is important for you? The transient part is important to know about the nature of the response and to know about the speed of the control system. What are the different nature of the response? Like, I am going to soon define that such a waveform is an overdamped waveform. But in general, if I talk about other categories of control system also, the response may be underdamped or maybe overdamped or maybe undamped at well, or maybe negatively damped, critically damped. Okay, so the basic analysis about the nature of the response, how the output is varying, is actually is actually determined by the transient part, and the transient also determines the speed of the control system. How it decides the speed of the control system, I'm going to talk about that. Okay, so the transient part is important to judge the nature of the system and the speed of the control system. But if I talk about the steady state part, as I told you, steady state part is the part of the response when time becomes very large. Okay, what is the output you see in the steady state? And this steady state part is important in terms of accuracy. in terms of accuracy. Okay, what do I mean here exactly by accuracy? That yes, if you leave the system for large amount of time, you have given enough time, but still does it reach to its desired value? If not, if it deviates still from what it should be, then we say that the system has a steady state error. Okay, so once you measure, like you wanted to charge the capacitor to 1 volt, you leave it for a large amount of time, but still you find that leaving the system for a large amount of time, the capacitor still charges to some level, suppose 0.9. Okay, or anything, the system final output reaches to the 0.9, then we say that there is some sort of error or some sort of defect in the system, and hence we define what is known as steady state error. This is very important. I will have a separate discussion on to steady state error. Okay, I will be having a separate discussion on the steady state error. Okay, the steady state part is important to talk about how accurate a control system is, and transient part is important to talk about how quick, how fast a control system is, and what is the nature of the response of the control system, right? So, as I told you, e power minus t by t is an exponentially decaying waveform. Taking the waveform for 1 minus e power minus t by t, this is the waveform which is overdamped. In some time, I'll categorize what do you understand by overdamped. I will define you. I'll explain you what do you mean by overdamped or underdamped or critically damped or etc, etc, etc. Let me make this once again. It's not that clear here. Okay. Right. So, the output in a sense exponentially rises, and when the time becomes very large, okay, the output is going to settle to the steady state value, and that is the steady state value of 1. The steady state value of the 1 volt. Such a response is overdamped response. I'll more defined about overdamped and underdamped in some particular time. Okay, so coming back to that same waveform, okay, let's define the time constant of the system. The T, as I told you, is known as the time constant parameter. What do you exactly understand by the time constant parameter? So since the output, okay, is growing exponentially given by the function e power minus t by t, okay, this part, okay, this part is exponentially decaying part. Okay, how much time does it take? Okay, how much time does it take so that this exponentially decaying functions quickly reaches to the first exponential power? Now, what do you mean by first exponential power? Is e power minus 1. Okay, is e power minus 1. Okay, and when it reaches to the value of e power minus 1, 1 minus e power minus 1, once you calculate it, approximately turns out to be 0.632. And we define the time constant of the system as the time taken by the step response to reach. 63.2% or 1 minus 1 by e of the final value. The time taken by the step response to reach, okay, 63.2% or 1 minus 1 by e times the final value. And that is of course obtained at what time? Okay, when this becomes the first exponential power, so t by t will be equal to 1, and at what time this is achieved? At the time given by capital T, and the capital T, as I told you, is known as the time constant of the system. Okay, the time constant of the system, okay, is known as the time constant of the particular system, right? Now, if I keep talking in terms of time constant, see, I have the expression Tt, which is 1 minus e power minus t by t. As I told you, if I take the value of one time constant, what is the output? The output roughly is becoming how much time? The output is roughly becoming 63.2%. Let me keep writing in percentage. But if I take the t equal to 2t, at 2t what will happen? 1 minus e power minus 2 will come. If I keep moving now in the integral multiple of the time, so this will be some value 86.4% approximately. If you take the 3 times the time constant, the value that will be obtained is 1 minus e power minus 3, approximately 95%. If you take it as 4t, if you take it as 5t, the output is going to approach the final value. The output is going to approach the final value. 1 minus e power minus 4, approximately 98%. 1 minus e power minus 5, approximately 99%, and etc, etc, etc. Okay, etc, etc, etc. This is how the response of the system is going to vary. It is going to approach the final value, and we know that the final value is 1 here. Okay, we know that the final value is 1 here. So this is the time constant parameter t, where the output reaches how much? 0.632. Okay, but if I keep moving, okay, if I keep taking the time in the integral multiple of the time period, we say that we are able to observe that as the time becomes large, the output is approaching the steady state value. But the point is, what is exactly the steady state value? As I told you, is 1. But that will be obtained only at t equal to infinity. that will be obtained only at t equal to infinity. So if I have to ask you what is the time taken by the system, okay, to reach the exact steady state value, and the time taken by the system to reach the exact steady state value is infinite, is undefined time. Okay, is undefined time. So we come to a concept of settling time. We come to a concept of settling time. Okay, highlighting in the same waveform. Highlighting it in the same waveform. Okay, if I'll just show you here only. Right, that as I have shown you that as the time becomes large, the output is going to approach the steady state value, but the exact time taken to reach the steady state value is infinity, which is the undefined time. Okay, let me consider a specific time, suppose 40. What happened at 40? What happened at 40? The output became how much? 98% or 0.98. Okay, 98% or 0.98. Okay, which is very, very close to 1. Okay. So, the time taken to reach the actual steady state value is undefined. So, we accept some error and we say that whenever the output suppose reaches even 98%, I am satisfied. And the time taken by the system to reach 98% of the steady state value, the time taken to reach 98% of the steady state value can be defined as a settling time. Okay, this is only one example. You can, it's your wish. You can say that whenever output reaches 95%, I am happy. Or somebody could say when output reaches 99%, I am happy. Okay, because exact time to reach 100% is undefined, that is t tending to infinity. So we define the concept of settling time. The time required by step response to reach within a specified percentage. That specified percentage may be 95 or 98. These are the commonly used figures. Okay, if you say that the output reaches 98%, then you are having a 2% error band. Then you are accepting a 2% error band, or we also call it as a 2% tolerance. Okay, 2% tolerance in the output value. Okay, or if you say that, the time taken by the output to reach 95% of the final value, then we say that the system has been taken with a 5% error band. The steady state has been defined with a 5% error band or a 5% tolerance. Okay, so if I define with respect to 98%, okay, if I define with respect to 98%, my settling time for the first order system is how much? 40. If I talk about 98%, my settling time of the control system is equal to the 3t. Is equal to what? Is equal to 3t. As I've shown you in the calculation. Now, this settling time is important, okay, to assume when the steady state has almost arrived. Okay, exact steady state takes a large amount of time. So, we say that whenever the t becomes 40, okay, the part of the response up to this time, will be known as the transient part of the system, and the part beyond it will be known as the steady state part. So settling time in a sense will give you a boundary between the transient and the steady state part of the system. The transient and the steady state response of the system. It gives you a boundary between the transient and the steady state response of the particular system. Okay. Yeah, that is already mentioned here. I'm sorry. That is already mentioned here. Clear? That is what is the concept of the settling time. Okay, 40. Okay. So if you say that a system is faster, okay, if you say that the system is faster, okay, guys, as of now, it all depends on you. So a humble request, don't ask me how many hours it is going to go. I am going to cover as much as possible. It all depends on how attentive you are and how much patience you keep. Okay, marathon means we can learn. We are going to run long. We are definitely going to run long, but it also depends on the attendance and the patience of the students also. Okay, so right now I cannot define how much the session is going to go. Okay, so if you say that, okay, a system should be faster, means the system should achieve the steady state quickly. Okay, when will the system achieve the steady state? At settling time. At what? At the settling time. Okay, and hence we can say that whenever the settling time is lower, system is faster. Okay, so if you want to have a system which is faster, okay, it should have a lower settling time. It should have a lower settling time, and it means that it should have a lower time constant. It should have a lower time constant. Okay, it should have a lower time constant. So system being faster means the transient part getting over quickly. Okay, so that is why I told you the nature of the transient will also define the speed, how quickly the transient will die away. Okay, that much faster the system could be. Okay, now rise time, another parameter for overdamped waveform for the first order, which is an overdamped waveform. It is the time. It is a time taken by the step response to change from 10% to 90% of the final value. The time taken to change from 10% to 90% of the final value. The 10%, see, the output grows from 1. This value 0.1, okay, suppose is obtained at the time t1. Okay, and this value 0.9. This value 0.9 is obtained at suppose some time t2. The time taken by the step response to change from 10% to 90% of the final value is defined as the rise time. That is the time between the t1 to t2. Okay, so the time between the t1 to the t2. So when I do t2 minus t1, let's not derive, but you know the output formula, 1 minus e power minus t by t. Once you equate to 0.1, once you equate to 0.9, and when we subtract, the rise time turns out to be 2.2t. Okay, just like for the RC circuit, for the first order RC circuit, you study the rise time as 2.2 RC. You study this in the circuit analysis also, correct? Right. So this is the rise time of the first order system. I'll take some numerics also, but let's also go to second order system. Let us revise important points of both first and second order. Let's do some numerics and then we'll go to the higher order as well. So second order system, of course, is one in which the highest power of s in the denominator of the transfer function would be 2. I'm telling you, as of now, I'm defining order with respect to the transfer function, the nature of transfer function. For a standard second order system, the transfer function, the prototype block diagram is shown in front of you. The final transfer function turns out to be omega n square upon s square plus 2 zeta omega n s plus omega n square. Right. Now, again, talking about the important parameter, that is the step response. Okay, step response and the nature of poles. Two things are going to be very important. Okay, if I want to talk about the poles, so we can directly take this particular term, s square plus 2 zeta omega n s plus omega n square equal to 0. Okay, so when I solve this, s square plus 2 zeta omega n s plus omega n square equal to the 0. Okay, the roots that we get is given by s equal to minus zeta omega n plus minus j omega n under root 1 minus zeta square. We'll be simplifying these poles under specific values also. Also, guys, okay, the parameter zeta into omega n is also known as alpha. That is known as the damping factor. I will define soon. Okay, and omega n under root of 1 minus zeta square is known as the damped frequency, again, which I'm going to define soon. So quickly writing down the formula in terms of these parameters, we can write down s is equal to minus alpha plus n minus j omega d. Minus alpha plus n minus j omega d. Okay, right, minus alpha plus n minus j omega d, assuming zeta positive. Generally, the poles are making a complex conjugate pair. Okay, this is minus alpha plus j omega d. And this is the another pole, minus alpha minus j omega d. Minus alpha minus j omega d. Right. Now, talking about the step response. Again, step response with beat mod. Okay, take the input RT equal to 1. Okay, step response is the response. Okay, when you take the input as the step input RT equal to 1. So, RS is equal to 1 by S. Okay. Again, everything is solved using S domain here. For simpler calculation, we put down RS equal to 1 by S, shift it on the right side, split into partial fraction and find the inverse Laplace transform. And doing that effort, okay, the output is generalized. Again, this will be simplified under separate values of zeta. Okay, but the output in the most general form is written as the expression 1 minus e raised to the power minus alpha t upon root 1 minus zeta square sine omega dt plus phi. Okay, where alpha, as I already told you, zeta into omega n, omega d is omega n root 1 minus zeta square, and phi is coming up as cos inverse zeta. Okay, we define zeta as cosine of phi. Which phi? Okay, sometimes, you know, some important numerics are there around the relation of zeta and phi. What is that phi? So if I go back to the poles picture, understand. If I go back to this poles picture, okay, what is the distance of this particular pole? What is the distance of this particular pole with respect to the origin? What is the distance of this particular pole with respect to origin? See, it is highlighted here as omega n. So how can you calculate the distance of this pole? You can simply calculate the distance as root over x square plus y square. Okay, by the distance formula, root over x square plus y square. Okay, and once you calculate, once you put down the value of, you know, alpha and zeta, okay, alpha square will become zeta square omega n square, and omega d square is omega n square 1 minus zeta square. So see, zeta square omega n square and minus zeta square omega n square will get cancelled. Under root of omega n will be omega n. So when you calculate the distance of the pole, this one or the other conjugate one also, it turns out to be what value? It turns out to be omega n. This is omega n. Okay, so in a way, omega n, which I am going to define as the natural undamped frequency, but omega n also represent the distance of the poles of the complex conjugate poles with respect to the origin. Now, Let's take the radial line to the pole, the line joining the pole to the origin. Okay, when you join the pole with respect to the origin, suppose it makes some angle that is known as theta. Let's say it makes some angle that is theta. Okay, now when you talk about theta, or let me call it as phi only, when you talk about cosine of phi, see what is going to be the cosine of this phi. So cos theta is base upon hypotenuse, but what is the base? The coordinate is minus zeta omega n, so distance of the base is zeta omega n upon hypotenuse, as I just calculated right now, is omega n, and hence we get zeta. Okay, so that is where I was telling you, zeta is cosine of phi. What phi? Phi is the angle subtended by the radial line to the poles, okay, to this complex conjugate left half plane poles. Okay, when you draw the radial line, the line joining the origin to the pole, what is the angle subtended with respect to the negative x-axis? That is phi, and zeta is cosine of this angle phi. Okay, zeta is known as cosine of this angle phi. So in the formula sin omega dt plus phi, the phi that is coming up can be written as the cos inverse of zeta. Okay, now several important discussions, although the questions are simple, but this important one, based on the different values of zeta, either sometimes the questions directly, indirectly on the nature of the poles or the nature of the step response, okay, or settling time of the system. So what are those different questions that can be built up from here? What are the different questions that can be built up from here? What are the different questions that can be built up from here? Let's have a look into it. Okay, let's have a look into it. So, suppose when zeta is 0. Okay, suppose when the zeta equal to 0, need not derive it again completely. Okay, when you put zeta equal to 0, on simplifying, what is the expression you get is 1 minus cos omega nt, pure sinusoidal. Okay, it's a sinusoidal function, only a cos omega nt is coming up. Okay, and we say that this is a pure sinusoidal or a pure oscillatory term. Okay, and hence when you draw the waveform, okay, when you draw the time response waveform, the response is such that it keeps on oscillating between 0 and 2 for indefinite time. Okay, and we say that the system, okay, is undamped. We simply mention here that the system is undamped. It keeps on oscillating between the value 0 and 2. Okay, the largest value being 2. Okay, it keeps on oscillating between 0 and 2, and the nature of the response is undamped or pure oscillatory in nature. Okay, undamped or pure oscillatory, because there is no damping. What do you mean by damping? Damping is a effect, or damping is a phenomena which will try to reduce the oscillations of the system. Okay, which will try to either reduce the oscillations, or if the damping becomes dominant, it will totally cut off the oscillations of the system. It will totally cut off the oscillations of the system. So when zeta is increased slightly, this is the condition for zeta equal to 0. When zeta is increased slightly from 0 to 1, when the zeta is increased slightly from the 0 to 1, okay, then the output, this is the general expression. Okay, we don't substitute any zeta. Zeta can be any value between 0 to 1. Okay, the output is written by the general expression as I have shown you. Okay, but when you draw it, okay, when you draw the waveform, we can even try these waveforms using MATLAB. So when I plot this waveform, okay, the type of waveform that is obtained is showing oscillatory behavior. Okay, but not periodic. The amplitude of the oscillation keeps on reducing with time. Okay, the amplitude of the oscillation actually, if you join these peaks, will be an exponential function, because it is the sinusoidal term multiplied by an exponentially decaying term. You have a sinusoidal term multiplied by an exponentially decaying term, and that is why the peaks of the amplitude of the oscillations are actually reducing in nature, and such a response is said to be underdamped. I will write it more clearly. Such a response is said to be underdamped. Okay. So this damping, okay, now I'll show you what is more damping. This is underdamped, as I'm telling you, is coming up because of this exponential term. Is coming up because of the exponential term. See what happened previous case, I took zeta 0, and zeta 0 means, if you take zeta 0, so that means alpha also 0. And because alpha 0, so e power 0 becomes 1, and that is why there was no exponentially decaying term, and the response was pure oscillatory. The response was pure sinusoidal. The response was the pure sinusoidal. But if the alpha is present, if zeta not equal to 0, so alpha also not equal to 0, there will be this exponentially decaying term. Okay, and because of this exponentially decaying term multiplied by the sinusoidal part, the output is also, the amplitude of the oscillation is also exponentially decaying. For that reason, we also call the alpha, okay, for that reason, we also call the alpha as the damping factor. Okay, we call the alpha as the damping factor, because it is the factor responsible for damping in the system. If there is no alpha, there is no exponential term. If alpha is 0, the e power 0 will become 1. There is no exponentially decaying function and the system can be oscillatory. Okay, with the same amplitude 0 to 2, 0 to 2 with the same amplitude level. Okay, when the system is oscillatory, when the system is undamped, means it is periodic. Okay, and 1 minus cos omega nt. What is the frequency of oscillation? Omega n. So of course, we know about omega n. Whenever we write down any sine omega nt or cos omega nt function, okay, we know that omega n is known as the natural undamped frequency of oscillation. We know that the omega n is known as the natural undamped frequency of oscillation, and because the system is oscillatory, it will have a time period given by 2 pi by omega n. Okay, so omega n is known as the natural undamped frequency of oscillation. Alpha is known as the damping factor. Now, still there are some peaks, but the amplitude of the peaks are continuously reducing. But you know, the interesting point is, you know, once we come to the overshoot concept, you will understand this. Once I go to the overshoot concept, you are going to understand that. But yeah, you know, the point here is, if I redraw this waveform, if I redraw this underdamped waveform, okay, the point is, just a second. The distance, okay, the time gap between any two peaks, also, although the value of the peak decreases, okay, although the amplitude of the peak will decrease, but the distance between any two peaks, as you will learn in the overshoot quickly, is having the same amount of time, and that is 2 pi by omega d. 2 pi by omega d. Again, the distance for the next peak will be 2 pi by omega t, which looks like a time period term. Here I exactly can't call it as a time period, because time period is there for periodic waveform. It is not periodic, okay, but it has a pattern. It is still oscillatory, but with the amplitude of oscillation reducing, but the distance between any two consecutive peak amplitude will be 2 pi by omega d. Okay, now Nitin, that's what 2 pi by omega d is for underdamped, 2 pi by omega n is for undamped. That is the difference. That's why I'm writing in both the cases. Okay, Nitin. Okay, here because it is, you know, even see, when zeta is 0, omega d will be just omega n only, na? Correct, now omega d will be omega n. So for undamped, you can say 2 pi by omega n or 2 pi by omega d, anything. Specifically, we say 2 pi by omega n. Okay, but if it is underdamped, the distance between any two peaks is 2 pi by omega d. Okay, looks like a time period function, but not exactly a time period. So we call this, you know, omega d, which looks like a frequency term. Okay, not a real frequency. We call it as pseudo frequency, or more commonly known as the damped frequency of oscillations. It is the frequency, okay, of which type of oscillatory waveform? It is the frequency of which type of oscillatory waveform? The damped oscillatory waveform. Okay, the damped oscillatory waveform. Clear, everybody? Okay, and hence we call omega d as 2 pi by omega d as the pseudo frequency. Okay, the damped frequency of oscillation. So that is the difference. Omega d being the damped frequency, omega n known as the undamped frequency. I mentioned here, na? Omega n. Where is that omega n? I'll mention here. Yeah, natural undamped frequency of the system. Clear, everybody? Right. Let's keep moving ahead. Now this is for zeta between 0 to 1. Okay, I will summarize all the values of zeta in one slide. Okay, just one by one, let me keep explaining to you. Okay, now when we take zeta equal to 1, okay, when we take zeta equal to 1 and we simplify, primarily when we take zeta equal to 1, actually, you know, when you solve it, it will be sine 0 by 0 when you put it. Okay, and we solve it using the concept of limits. So when zeta equal to 1, we solve limit zeta tending to 1 ct, and this is the expression we get. 1 minus e power, 1 minus e power minus omega nt, sorry, as a typo error. Forget this, I will rewrite. The ct is given by 1 minus e raised to the power minus omega nt into 1 plus omega nt. So dear, when we derive, we use the same formula and we derive this formula, we rechange this formula for zeta being equal to 1. And when we solve it for the zeta equal to 1, what do you clearly get? That there is no sinusoidal term. Okay, mathematically also, if you see, there is no sinusoidal term, and because there is no sinusoidal term, that means there cannot be any oscillations in the system. That means damping is becoming more dominant. As I told you, what is damping? It is an effect, or it is a phenomena which will always act opposite to the oscillation, which will try to reduce the oscillation. Previous case oscillations are reduced. Okay, because earlier we have a clear-cut only oscillation, but now the amplitude of oscillation kept on reducing. But now when you increase the zeta, you come to a point that there are no oscillation, no sinusoidal term. Okay, we have no sinusoidal term here. Clear? We do not have any sinusoidal term, and the response is 100% non-oscillatory. Okay, so the minimum value of zeta, where you get non-oscillatory response, okay, is the zeta equal to 1, and such a response is said to be critically damped. Okay, good morning Rakesh. Is said to be critically damped. It is a non-oscillatory response. Okay, and it is said to be critically damped. It is non-oscillatory. Okay, it just reaches without any oscillation. Okay, oscillation means to and fro. Okay, like previous case, we have a two up and down, two up and down. Here, the output just quickly reaches the equilibrium and settle. Okay, it reaches the steady state value as quickly as possible. Okay, a non-oscillatory response, and the output reaches the steady state as quickly as possible, and we represent this case as a critically damped system. Now, of course, already you have come to the minimum value of zeta, okay, for non-oscillatory response. So if you increase the zeta beyond it, oscillations are anyways gone now. Okay, the system is only going to become more and more slower. So if I increase the zeta greater than 1, this is an expression I've written for you because you will be solving it using hyperbolic function. Why using hyperbolic function? Because when you substitute zeta greater than 1 here, you are going to get a complex angle. Okay, you're going to get a complex angle sine j theta, which gets converted to hyperbolic function. But this is a formula not to be remembered. What eventually you have to remember, I'll tell you. Okay, but yeah, when we draw the waveform for such a function, it turns out to be overdamped, still non-oscillatory. Okay, overdamped, which is still non-oscillatory because zeta is now more greater than 1. Okay, it is still non-oscillatory, but the difference is it will become slower. It is still non-oscillatory, but it becomes slower as compared to the previous case. As compared to the previous case, it becomes slower. Okay, if I have to draw, suppose, if I just want to compare, I'll show you in a waveform actually the comparison. Okay, I'll show you in a waveform the comparison. So this is actually going to be more slower. So you come to this waveform for a moment. See, for the reference notes I'm giving you completely. I'll share you this PDF, and don't worry, Telegram links and all I will share you. Somewhere later on I will keep sharing you the Telegram links also. So the point is, if I keep highlighting the important value, see, this is what I started with, zeta equal to 0, undamped response. Undamped response. But when you take any value of zeta between 0 to 1, like these are some MATLAB waveforms, this is for zeta corresponding to 0.4. The next one has been taken for zeta equal to 0.5. Any value you take between 0 to 1, the system is still oscillatory, but the amplitude reducing. There is a damping in the system known as underdamped. These two are underdamped, the same waveforms I have drawn. Okay, now when you take zeta equal to 1, the system is non-oscillatory, okay, and it quickly just reaches the equilibrium value, steady state value of 1. Okay, the steady state value of 1. And if you make the zeta greater than 1, like I have taken zeta equal to 2 there. Okay, zeta equal to 2. When you take any value of zeta greater than 1, see what is the effect? The response is still non-oscillatory. Okay, but it becomes slower. See, the time it takes to reach the steady state value, the time it takes to reach the, say 98% also is more than what is in the critically damped case. Okay, so that is the difference between overdamped and critically damped. Overdamped and the critically damped. Hope the things are getting clear for you. So overdamped will be behaving as more slower as compared to the critically damped. As compared to the critically damped. Now when you talk about the zeta, okay, which is between -1 to 0 or zeta between less than -1. Okay, the important point is when zeta takes any negative value, the response, the final value of the response will always be unbounded. It always grows. Okay, for zeta between -1 to 0, it has an exponential growth, exponential amplification, the final value being unbounded, and hence the system will be unstable. Because what is a BIBO stable system? Bounded input. The input is bounded. What input I have applied? Step input is applied. Okay, in all the other cases, look into the underdamped case. Okay, the output is bounded and it settles to the final value of 1. Look into the critically damped, the output is bounded and it settles to the final value of 1. Look into the overdamped case, the output is bounded and it also settles. It may be slower, but finally it settles to the value of 1. Finally, it settles to the value of 1. Okay. But when zeta becomes negative, the output is going to grow unbounded and the system is said to be unstable. Okay. Important point, when zeta takes any negative value. Okay. When zeta is negative, okay, we simply say that the system is negatively damped. We don't here specify any over damping or under damping. We simply say that the system is negatively damped. Okay. The limit t tending to infinity Ct, the final value of the output is unbounded. And hence the system is unstable. And the poles formula I gave you earlier, when you substitute any negative zeta there, the poles always will be in the RHP. It may be real or complex based on the value of zeta, but 100% in RHP. 100% in RHP. 100% in RHP. Okay, so these are only quicker points you need to remember for zeta less than 0. But for any zeta positive, I have given you all the clear-cut analysis. Okay, if I summarize, see, if I summarize the conclusions here, the system being overdamped. Okay, so this is again for you to go home and revise it, because everything I explained to you, what is the value of zeta for the nature of response? Okay, what are the values of the roots? What is the characteristics of the roots? Okay, like when underdamped, the roots are complex conjugate only. Okay, minus alpha plus minus j omega d. Minus alpha plus minus j omega d. Okay, but when the roots are, see here, okay, here this omega naught is our omega n only. Okay, so don't be confused. There is no new term. It is omega n only. Okay, and when the zeta is equal to 0 undamped, the roots are pure imaginary, plus minus j omega n. When zeta equal to 1, system is critically damped and roots are given by minus omega naught or minus omega n minus omega n. Both the roots are real and equal. Both the roots are real and equal. And when zeta becomes greater than 1, okay, you have two real and negative roots, okay, which will be unequal. Real and unequal in the LHP. Okay, and for zeta equal to 1, you have real and equal roots in the LHP. For zeta between 0 to 1 complex conjugate, and for zeta equal to 0, the roots are pure imaginary. For any negative zeta, as I mentioned to you, the poles will be in the right half plane. The poles will be in the right half plane. Okay. Right. Also, guys, other than this table, okay, you also have to remember the step response expression. See, this is the general step response expression. Okay, for zeta equal to 0, this is the expression. Okay, for zeta equal to 1, this is the expression. Sometimes you can expect the questions out of this. Okay, only thing is for zeta greater than 1, you don't remember this expression. If there is any question zeta greater than 1, better to solve it by Laplace transform method. Okay, but at least these three expressions, the general one, okay, and then the zeta equal to 0, the general one for zeta between 0 to 1, and for zeta equal to 1. Remember these three output expressions also. There have been questions out of this in the PYQs, okay. There have been questions out of this in the PYQ. Okay, so please, do try to take it. Please do try to solve it up. Clear? Chalo. And other thing, yeah. So as I'm telling you, in the underdamped, finally the system is stable and reaches to the final value. What is the settling time of this waveform? Settling time, as I already defined, considering that 98% criteria only. Okay, considering the 98% criteria, the time taken to reach the 98% of the final value, the settling time will be 4 by zeta omega n. The settling time will be 4 by zeta omega n for an underdamped waveform. Can there be any settling time? Can there be any settling time for an undamped waveform? Settling time is the time taken, okay, to settle up to 98% or 95%. That definitions can vary, but is it going to settle? It's pure oscillatory. Periodic function. Periodic function is a function which is going to be periodic till infinity also. Okay, it is not at all going to settle. There is no settling time. Okay, it does not settle to any particular value, and there is no settling time defined here. Okay, so remember, we cannot define the settling time for the undamped case specifically. Okay, also dear, here the output is bounded. Okay, here the output is bounded but does not settle. Output is finite between 0 to 2. Okay, output is always finite, but it does not settle to any specific value. We call this case as marginally stable. We call this particular case as marginally stable. All the other cases, as I told you, stable. Okay, all the other cases, as I told you, system is stable. Okay. When you come to critically damped, again the system is stable, but what is the settling time for critically damped? It is given by 6 by zeta omega n, but critically damped means zeta equal to 1. It is given by 6 by omega n. Again, as per the 98% definition. Okay, remember, this is a mistake. I have seen many students doing it. They use the settling time formula for second order system 4 by zeta omega n. That is only for underdamped. Blindly, if you use anywhere else, you go wrong. Okay, for critically damped, it is given by 6 by omega n. For undamped, there is no settling time. Right. For underdamped, 4 by zeta omega n. For critically damped, 6 by omega n. 6 by omega n. Okay, and system is here also stable, critically damped and stable because the output is bounded and settles to the final value. For overdamped, there is no settling time formula. We don't come to any settling time formula conclusion. If at all there is a question, you have to solve using Laplace transform, final value theorem. Okay, Laplace transform, final value theorem. But here also the system is stable because it is bounded. The output is bounded and reaching to the desired value. Okay. For zeta less than 0, it is unstable, as I told you. These are quicker conclusions for you. You have to remember it. Even in one more way, I have given you the conclusion, whatever you feel like. Okay, even graphically, I have given you the conclusion. Zeta greater than 1, zeta between 0 to 1, zeta equal to 0, zeta equal to 1. I'll give you this PDF in Telegram. Okay, but remember, right now only I am telling. Don't ask me later. Right now only I am telling. I will be giving you a password all my sessions. That is the ethics I follow. I will be giving you the PDF, all these notes for free, but it will be having a password protection. Okay, of course, the notes are free. The complete, whatever we are discussing, all revision of control system, you will get the notes and that will be a quick revision notes for you. Okay, but it is password protected. And password, I will tell you, after some time in the session only. That means those who have the effort and patience to understand and to watch, they deserve that particular PDF. Okay, that is the cost of PDF, I would say. There is no monetary cost, but the cost is your sincerity, your honesty. That is the only cost of the PDF. Okay, right, your sincerity and your honesty. So I'll be giving you the password of the PDF later on. Don't ask me in the Telegram. It will be given during this session. I'll give you 1 or 2 times, don't worry. Okay, but let's get moving ahead. Let's talk about the PDF later. This waveform, I already explained you comparison of the nature of the step response for different values of the zeta. Now, some transient parameters, some important formula, and then taking some quicker numericals. Okay, then taking some quicker numericals. So for underdamped waveform especially, taking up some transient parameters. Okay, for the underdamped waveform, taking up some transient parameters. Have a look into it. Rise time, delay time, peak time, settling time, and overshoot. Settling time, I have already given you the formula. Okay, so rise time. Now, for underdamped, okay, I am taking right now for underdamped. Okay, the time taken by the step response to reach desired value for the very first time. Okay, this is the definition of rise time for underdamped. For overdamped waveform, I have already defined with first order system also. For overdamped, it is taken as the time taken to change from 10% to 90%. This is for overdamped, which I have defined with first order also. Okay, for underdamped, it is the time taken to reach the desired value for the very first time. Okay, so why I specify very first time? Because the output, since it is oscillatory, it is going to reach the desired value, which is 1. Okay, desired value, which is 1. It is going to cut this desired value multiple times. It is going to cut the desired multiple times. When it is going to reach the desired value for the very first time, this is what is the rise time. I will highlight here more clearly. This is what is the rise time. Okay, this is the rise time. Okay, I'll give you the formulas for all of them. Okay, not deriving it right now. Then the delay time, the time taken by the step response to reach 50% of the desired value. 50% of the desired value. Okay, so desired value 1, 50%, 0.5. Okay, this is 0.5. Okay, and the time taken to reach this value is known as the delay time. The time taken to reach this value will be known as what? Will be known as the delay time. Clear? Okay. This one marks my CT desired. This is what is the desired value. Okay. Next, settling time. I already told you the time taken to reach 98%. Again, by 98% criteria, I have defined it. Okay. So the time taken to reach 98%. Okay. So say this here, the output should be 0.98 if I take 98% criteria. Then we will come to the overshoot and peak time separately. That is the most important thing actually. Okay, if I talk with respect to questions, that is the most important things I would say. Okay, now if you look into the expressions, okay, the formulas I'll give you, the rise time, the delay time, peak time I will explain you, just you can note down the formula. So rise time is given by pi minus phi by omega d. Phi is coming from, remember, phi is coming from zeta, cos inverse of zeta. Okay, the delay time is given approximately by, because delay time is solved by numerical methods actually, 1 plus 0.7 zeta divided by omega n. Okay, the peak time is given by pi by omega d. Okay, and settling time for underdamped, I already told you, it is given by 4 by zeta omega n. 4 by zeta omega n. Okay, now let's talk about overshoots and undershoots, and then I will give you the peak time also. This is the peak time. Okay, now what is the definition of any overshoot or undershoot? Listen here. Okay, what is the maximum overshoot and the peak time of the system? Okay, the maximum positive deviation of the output, with respect to the desired value is known as the maximum overshoot, and the time taken to reach the maximum overshoot is known as the peak time. Okay, the maximum positive deviation of the output with respect to desired value. So what we say, the system is oscillatory. That means the output level is fluctuating about the desired value. Okay, whether these fluctuations are large or small. If you have large fluctuations, say this is some voltage waveform. Okay, so any large fluctuations may also damage some of our electrical appliances. So what I am now measuring is, this is my desired value. The output is oscillatory or fluctuating about the desired value. Okay, and because of the oscillatory nature, sometimes it goes above and below. The highest value that it reaches, here I have highlighted this as CT max. Okay, and then what is the maximum positive deviation with respect to the desired value? Okay, this is what is my CT desired. This is what is the deviation. I'm not really interested only in the maximum value, but the deviation of the maximum value. Okay, this is the deviation, correct? This is the deviation, and this is with respect to the, what is the definition with respect to desired value? Let me explain it first of all. Okay, so what is the overshoot we defined? As I told you, the deviation. What is the deviation? CT max minus CT desired divided by CT device, because the deviation with respect to desired value. The deviation is required with respect to desired value. Okay, and for percentage, if you want to specify percentage, we multiply it by 100. CT max minus CT desired. Okay, CT max minus CT desired. Now, CT desired is 1 here. Okay, here, okay, it's not necessary it's going to be 1, but here CT desired is 1. Okay, so if CT desired is 1, what I'm only interested is to calculate CT max. Okay, for CT max, what do we do? For maximum of any function, we first start by the stationary points. D by dt of CT equal to 0. When you solve d by dt of CT equal to 0, you come to a formula that is given by n pi by omega d, where n can take the value 1, 2, 3, 4, etc. Now, why multiple values of time will come up? Because d by dt of CT equal to 0 will not only give you maxima, it's a stationary point condition which can give you a maxima or minima. Okay, which can give you either maxima or a minima, or sometimes point of inflection. So see what is happening. The waveform has a maxima, local maxima, then a local minima, then a local maxima, then a local minima, etc. So you have several maxima and minima within the waveform, isn't it? And that is why several values of time are being obtained. Okay, when you put n equal to 1, that is the first particular time that corresponds to maxima, that corresponds to your overshoot. Okay, this is what dear is known as, this is what is known as your first or maximum or peak overshoot. Because for the first time only it is the maximum overshoot. For the next time, if you come here, there is an overshoot, but definitely below, because the system is damped. When you go here, there is still overshoot, but again lesser. Again lesser. All these are, what is this? This is my second overshoot. This is known as my second overshoot. This is known as my third overshoot, and etc, etc, etc. Clear? Now similarly, when the output dips below, when the output goes below the desired value, that will be represented by undershoot. This is the first undershoot. Okay, this is your second. This is your third. All these are known as undershoots. All these are known as undershoots of the system. All these are known as undershoots for the system. All these are known as undershoots for the system. Okay, so the n equal to 1 will correspond to the first overshoot, and there, that is the time which we call it as the peak time, as I defined. Let me go back once again. The maximum positive deviation, positive means upper side, the positive deviation of the output with respect to desired value is the maximum overshoot. The time taken to reach that maximum overshoot is the peak time. So what is the time at which you get the first or the peak overshoot? TP, it is the peak time, and that will be obtained for n equal to 1. Okay, n equal to 1, you get the peak time. Okay, that is the first particular time, and that is pi by omega t, as I've already listed the formula earlier, peak time. Okay. But when you put n equal to 2, you will get undershoot, minima. Then n equal to 3, overshoot, and etc, etc, etc. Now, first of all, solving CT max, okay, for TP equal to pi by omega d. Okay, right. So, TP is the pi by omega d, and at this particular time, when we calculate CT max and substitute in the percentage overshoot, the percentage overshoot formula that we get will be given by, normally in several books, you will find it as e power minus zeta pi upon root 1 minus zeta square into 100. Simple way, according to me, to remember is e power minus pi cot phi. E power minus pi cot phi will be a simple way to remember it. Okay, because what is the value of cot phi? Cot is cos upon sine, and as I already told you, cos is zeta. So what is sine theta? Under root 1 minus cos square theta. So under root 1 minus zeta square, same expression will come. Okay, so easy way to remember the formula is simply e power minus pi cot phi. Simply put it that way, e power minus pi cot phi. The percentage overshoot will be given by the formula e power minus pi cot phi. Clear, everyone? The e power minus pi cot phi. Okay. Now, moving ahead to the next. This is for the peak time condition. But as I'm telling you, if you take any value of n, which is 1, 3, 5, 7 alternately, that is n equal to odd, any odd value you take, you get overshoots. Alternately, you get overshoots. Okay, alternately you get overshoot. Okay, so that means if I talk about n equal to 1, that I already defined. First overshoot, that is the peak overshoot condition already. Okay, the time there is given by TP. N pi by omega d, n equal to 1. Pi by omega d. The overshoot value is given by, so I'll put it as a table. Or let me put it as a simple table here. Similarly, dear, when you take n equal to 2, 4, 6, the other alternate values, that is even values, you get undershoots, as I have highlighted. You get undershoots. So dear, if I keep writing the value of n, okay, and then the nature, and then the value of the time there, and the value of overshoot or undershoot. Okay, the value of the overshoot or undershoot. Understand the general trend. Because sometimes, see, normally questions we expect on peak overshoot. Sometimes they can suddenly ask, what is the time taken to reach the third overshoot? Or what is the third overshoot value? Okay, what is the third overshoot value? So, if I keep drawing it, see, if n equal to 1, okay, so n equal to 1 means overshoot. Time is pi by omega d. The value is e power minus pi cot phi. For percentage, multiply by 100. If I take n equal to 2, that will represent undershoot. Undershoot and overshoot will alternate. That will be undershoot. Time will be 2 pi by omega d, because the general time formula is n pi by omega d. I am just substituting the n value. The value of the undershoot, will be e power minus 2 pi cot phi. Okay, e power minus 2 pi cot phi. For n equal to 3, again you will get overshoot. The time will be 3 pi by omega d, n equal to 3. The value of the overshoot now, that is the second overshoot. Okay, that is the second overshoot. Okay, and that will be e power minus 3 pi cot phi. Similarly, n equal to 4, that will be undershoot. Second undershoot. Okay. 4 pi by omega d, e power minus 4 pi cot phi, and etc. That means the value of undershoot, overshoot will also be generalized, can also be generalized as e power minus n pi cot phi. can also be generalized as e power minus n pi cot phi. Okay. So, if they ask any type of undershoot or overshoot, okay, you can answer it. You can answer it. Remember, for n equal to odd, it will be overshoot. For n equal to even, it will be the undershoot. The general time is given by n pi by omega d, and the general value of the undershoot or overshoot will be given by e power minus n pi cot phi. Okay. Now have a look into this numeric. Okay, very simple numeric. This is a first order case system actually. For the system shown below, what is the rise time and settling time? Okay, the transfer function that is given, I think the picture is not clear. I will write down the transfer function directly. 5 upon s plus 5. But yeah, if you know the time constant, you know both the cases. Okay, so there can be a simpler question like this. 5 upon s plus 5, or if I divide by 5 throughout, so 1 upon 1 plus 1 by 5s. And this becomes the time constant. 1 upon 1 plus st is the time constant form. 1 upon 1 plus st is the time constant form. Okay, so time constant is 1 by 5, or that is 0.2 seconds. Okay, so the question is, what is the rise time of the system? Okay, and what is the settling time? What were the formulas? The rise time is 2.2 t. That is 2.2 of 0.2. So that should become 0.44. The settling time, okay, settling time, of course, if nothing is mentioned, by default use the 98% criteria. The settling time is given by 4t, and that is equal to 4 into 0.2, 0.8 seconds. 0.8 seconds. Okay, so the respective times, option number C. Okay, the respective answer is option number C. Okay, yes, correct. Just little info. Correct answer, option number C. Okay, next question. Next question. A good question from first order system. Unit step input to a first order system GS yields a response as shown below. This can happen when the values of k and a. Now, actually, what is the nature of the response? See, I think colors are merged here. I'll highlight this actual step response. This is what is the actual step response we know, overdamped waveform. Okay. It is shown to be approximated by a straight line. Okay, and every straight line has the important property, that is the slope. What is the slope of the straight line? It is the slope of the step response at origin. Okay, the point here is, the moral of the question is, the slope of the straight line which is used to approximate by a response corresponds to the slope of the step response at origin. Okay. Now, what is the step response? I will go and see the transfer function. How the transfer function is given? GS is given as k upon s plus a. GS is given as k upon s plus a. Again, writing in the time constant format, I will divide by a. Okay, so k by a and 1 plus 1 by as. This becomes my time constant value. Okay. Right. How do I write down the transfer function, dear? The transfer function will be k by a 1 upon 1 plus st format. Okay. The formulas that I have given you for step response is for the standard transfer function 1 upon 1 plus st. K by a is a constant multiplier scaling. It is a linear system. The output will also be scaled. So what is the step response of this? What is going to be the step response? The step response, okay, let us say this output is the step response Ct. It is actually to be amplified by k by a, and then the formula was 1 minus e power minus t by t. 1 minus e power minus t by t. Okay, and the time constant is the reciprocal of a, so 1 upon t will become a. So this is the step response, k by 1 minus e power minus at, or you can again solve by the Laplace transform also, your choice. You can simply solve by the Laplace transform also the step response, not a very big deal, not a very big deal. Okay. Now, one thing is shown to you is, okay, that the slope of the line should be equal to the slope of the step response at origin. Okay, so what is that step response? Let me rewrite the step response actually. Ct is k by a 1 minus e power minus at. 1 minus e power minus at. Okay, so what is the derivative of this? D by dt of the Ct. D by dt will be k by a, derivative of 1, 0, and minus e power minus 80 derivative will become plus a e power minus 80. Okay, no, at t equal to 0, origin means t equal to 0. Okay, slope means d by dt. Okay, so at t equal to 0, the value of the slope at t equal to 0 will become only k. This a and a actually cancelled, only k e power minus 80. And if I put t equal to 0, the slope is k. But what is the slope of the straight line as per the coordinates? As per the coordinates, the slope can also be written as height upon base. The height is given as 5 and the base is 0.1. Okay, this point has been mentioned and this is origin. So height is 5 and the base is 0.1. So that is 50. That is 50, and hence this k is also equal to 50. Because slope of the straight line should be equal to the slope of the step response at origin. The slope of the step response at origin is k, and the slope of the straight line as per the coordinates given should be 50. So k equal to 50. Okay, we want the value of k and a. Okay, k is 50. See, as of now question finished, because only one option has k equal to 50. So as of now question finished, but let me help you in calculating a also. Let me help you in calculating a also, right? So this is the value 50. Now, next is one more thing that you can observe from the waveform, that when the time becomes large, the output settles at the value of 5. Okay, so what is this 5? Okay, this 5 can also be specified as the steady state value. Steady state value. Okay, steady state value. Okay, so now when I come to the steady state calculation, steady state value, which is defined as limit t tending to infinity ct, is mentioned in the waveform as 5. Is mentioned as 5. Now put t tending to infinity. K by a, 1 minus 0, e power minus infinity 0. So this should be 5. And hence k by a equal to the 5. Okay, but k is already calculated as 50. Okay, so a should be equal to the 10. A equal to 10. Option number C anyway is tick marked, but that is how we can find the value of A. The value of the A also, right? Okay. Clear everyone? This is a good question from the first order system. Now, coming to a second order system, a complete question, where, 3-4 formulas will be used together. Consider the system shown in the figure. First, we need to simplify the block diagram. First is what is the value of k, so that the damping ratio is 0.5. So that the damping ratio is 0.5. See, for such a case, you not necessarily have to solve the entire transfer function. You will have to solve the inner loop first. What is the gain of this inner loop? Okay, the gain of the inner loop, g upon 1 plus gh. It's a unity negative feedback system. So 10 upon s plus 0.8 upon 1 plus gh. So g is 10 upon s plus 0.8 and hs equal to k here. So multiplying by s plus 0.8 numerator denominator, I am able to obtain 10 upon s plus 0.8 plus 10k. S plus 0.8 plus 10k. Right, dear? 10 upon s plus 0.8 plus 10k. Right? So 10 upon s plus 0.8 plus 10k. This is what is the inner loop gain. Now for a complete loop, no need to find the entire transfer function. See, what is the second order transfer function generally? What is the second order transfer function? The transfer function, second order, as we have already discussed, the transfer function is given by omega n square upon s square plus 2 zeta omega n s plus omega n square. Okay, the nature of the poles can tell you everything about the system. The nature of the poles can tell you about stability, nature of the response, and etc. So we normally target the characteristic equation of the system. What is the characteristic equation? We just take the denominator equal to 0. S square plus 2 zeta omega n s plus omega n square equal to 0. This is the characteristic equation for second order. Or more generally, if you take any transfer function in the form of g upon 1 plus gh, what is the characteristic equation we define? The characteristic equation we defined is the denominator, that is 1 plus GSHS equal to 0. 1 plus GSHS equal to 0. Okay, so later on there will be even a bigger role of the characteristic equation once I start going for higher order systems also. Okay, so the gain of the inner loop is known. Now it is cascaded with 1 by S. Okay, and the overall feedback gain is unity. So what is the characteristic equation of the system? Let me come to the characteristic equation of the system. What is the characteristic equation? 1 plus GSHS. So what is the GS now? These two blocks are in cascade. That is 10 upon S plus 0.8 plus 10K into 1 by S. These two. When two blocks are in cascade, the gains are multiplied. Okay. GS into HS. HS is 1. Overall feedback is unity. 1 plus GSHS equal to 0. So multiplying, simplifying this, S into S, S square. Next term is 0.8 plus 10K whole multiplied by S and plus 10 equal to the 0. Now dear, that is what you have to compare with the standard second order characteristic equation. It's a second order system, S square. Okay, so what is the value of omega n square? That is 10 and the value of omega n is given by the root 10. The value of the omega n is given by root 10. Okay, then what is the value of 2 zeta omega n? 0.8 plus 10K, right? So 2 into zeta. What is the value of zeta? That's what is mentioned. The value of K, so that the damping ratio is 0.5. Damping ratio is 0.5. That is the required damping ratio. Omega n is root 10. This should be 0.8 plus 10K. Right, simple. So calculate the value of K from here. Calculate the value of K from here. How much it is going to be? Let me write down the value. Yeah, so the K is approximately 0.236. 0.236. Okay, 0.236. Now next is calculate rise time, peak time, overshoot and the settling time in the unit step response. Okay, that is the next part of the question. Now after obtaining K, okay, K is done, but let me rewrite the value of zetas and omega n. What is the damping ratio? 0.5, that is already given. Omega n I have calculated as root 10, or let me call it as 3.16, approximate value of the root 10. Okay, and then what will be alpha? First alpha also will be required. So alpha is zeta into omega n. So when you multiply these two, how much should be the answer? 1.58, and omega d is given by omega n root 1 minus zeta square. So omega n, let me take it as root 10 right now, into root 1 minus zeta square. 0.5 square 1 by 4. Okay, so this can be written as how much? Root over of 10 into 3 by 4. Okay, root over of 10 into 3 by 4. So final value, actually that is more important. 2.74. 2.74. Okay, sometimes they can only ask damned frequency of oscillation. Okay, 2.74. Now this is omega d. Fine. Now let us come to the question. Rise time. The first is rise time. Okay, let me also calculate phi also. Now zeta. Zeta is given by cosine phi, which is 0.5. So which angle should you take? Cos 60. But in the standard form, we call it as pi by 3. Cos 60 is 1 by 2, na? Cos 60 is 1 by 2, correct? Okay, so what is the rise time? The rise time is given by the formula pi minus phi upon omega d. Pi minus phi, the phi is pi by 3 upon omega d 2.74. Solving it, what is the final approximate value? The final approximate value is given by 0.76. So the rise time of the system, 0.76 seconds. Okay. Next question is what? What all they are asking? Rise time, peak time, overshoot and settling time. Okay, so peak time. Next is peak time. The peak time formula is simply pi by omega d. Pi upon 2.74. So how much is this value? Approximately 1.15 approximately. 1.15 seconds. Done. 1.15 seconds. Now let me complete the timing value first. What is the settling time of the system? The settling time is, because it is underdamped, 4 by zeta omega n, or you can directly say 4 by alpha. So alpha we calculated as 1.58. So approximate value how much? 2.53. 2.53 seconds. The settling time is given by 2.53 seconds. Okay, right? Because underdamped to 4 by zeta omega in formula. Now when I talk about the overshoot, okay, percentage overshoot. So as I told you, remember by the formula e power minus pi cot phi into 100. Now since the phi is pi by 3, okay, what is cot pi by 3? Which is 1 upon tan pi by 3 and tan 60 degrees root 3. Okay, so what is the overshoot you are going to get here? The overshoot is e power minus pi by root 3 into 100. Solving this value, yes, it is 16 point, or approximately, let me write it as 16%. How much is the overshoot? 16%. Correct? How much is the overshoot? Is the 16%. The overshoot is known as the 16%. Now also remember, there have been sometimes questions on the trend of the overshoot. Remember, I'll put down a point there. Okay, that whenever zeta will increase, okay, the overshoot will decrease. Remember, whenever zeta will increase, the overshoot will decrease, and overshoot occurs only for zeta equal to 0 to 1. Okay, right, for oscillatory waveform, underdamped oscillatory waveform. Okay, overshoot occurs for zeta between 0 to 1, and right, zeta increases, overshoot decreases. Clear? Right. So if zeta equal to 0, there is 100% overshoot, undamped waveform. Okay, zeta equal to previous question 1 by 2, we got 16% overshoot, it decreased. If you take zeta equal to 1, okay, or zeta greater than 1, zeta greater than equal to 1, non-oscillatory waveform, okay, there is no overshoot, remember. Zeta greater than equal to 1 means non-oscillatory waveform. We have seen all the waveforms, na? Okay. Zeta equal to 1 critically damped, zeta greater than 1 overdamped. Okay. Overdamped one. That is what you also have to put the habit, Naveen Sri. You have to, adapt the virtual calculator very, very quickly, so that even in the GATE, okay, as much as possible, you don't spend time lot on calculations, but more on concepts. Next question. For a second order system, the question is related with the pole. Very simple question actually. The location of poles is mentioned to you. For this system, the location of poles is mentioned. Calculate the peak time and settling time. Now dear, what is the location of poles? General formula. Minus alpha plus minus j omega d. And it is given to you as minus 2 plus or minus j5. Minus 2 plus or minus j5. This is the given answer. Minus 2 plus or minus j5. Okay. So now coming to the peak time. What is the peak time formula? Pi by omega d. So question finished. Now what is omega d? You compare pi by 5. Omega d is equal to 5. Okay. Omega d equal to the 5. So 0.63. 0.63 seconds is the peak time, and settling time for 2% range, 2% error, and that is given by 4 by zeta omega n or 4 by alpha. Alpha is directly 2. Okay, the settling time is 2 seconds. Finished. So it's an easier question, I would say. It is just an easier question, I would say. Next. Okay. Now for second order system, if the zeta increases, it is still stable. Na? Underdamped, critically damped, overdamped, they are all stable. When zeta is negative, that makes the system unstable, Aditya. Okay. When zeta is negative, that makes the system unstable. Right. Next. The system shown in the figure is non-oscillatory, but yet has the lowest possible settling time. What is the meaning of this language? First of all, you have to just decode the meaning of this language, and then you have to find the value of k. Then you have to find out what is the value of the k. And then you will have to find out what is the value of the k. What is the value of the k? Come on. Let us try to find out. The system shown in the figure is non-oscillatory, but yet has the lowest possible settling time to the step input. Lowest possible settling time to the step input. What is the value of k? Lowest possible settling time for the step input. So see, if you decode this language, it is non-oscillatory. Non-oscillatory means critically damped. If I say only non-oscillatory, so critically damped or over-damped are the non-oscillatory behaviors, but has the lowest possible settling time. Okay, lowest possible settling time. That means the system reaches the quick equilibrium, the steady state value very quickly, and that is for critically damped. Out of these two, then it is critically damped. Okay, and critically damped means zeta equal to 1. So this is the indirect way. There can be a direct question. Find the value of K for the zeta equal to 1 or zeta equal to any value. Like in one of the previous question, find the value of K to find damping ratio, to obtain a damping ratio 0.5. This is indirectly they are mentioning. So that is why, from this chapter, I also highlighted on the conceptual part. What is the meaning of, the different natures of the step response, because language also plays, the concept also plays an important role here. Okay, and of course, then we have formulated all the important things and solving it. So finally, what does it mean is zeta equal to 1. Okay, so first I'll again try to solve this inner loop. Okay, this inner loop gain will be GS 100 by S square upon 1 plus GSHS. Okay, so multiplying by S square, actually it should be 100 upon S square plus 100 KS. So what is the final characteristic equation? 1 plus GSHS. The final GS is, now this inner loop appears in the forward path gain actually. So that is 100 upon S square plus 100 KS into HS, which is 1. The final feedback gain is unity. So simplifying, I am getting S square plus 100 KS plus 100 equal to 0. Again, this term will be compared to omega n square, which is 100. So omega n is 10. The omega n square is 100. Okay. Then you take this particular term. 2 zeta omega n is 100k. Okay. 2 zeta omega n is 100k. Let me solve it here. So 2 into zeta. Zeta required is 1 as per the discussion. Omega n obtained is 10 and this is 100k. So 20 by 100, k value is 0.2, option number B. The k value is 0.2 and that is your option number B. That is your option number B. Correct. K value 0.2, option number B is very correct. Yes, Nitin, correct answer. Yes, never stop learning, omega n correct. Okay, dear, let's move ahead to the next question then. Okay, let's move ahead to the next question. A MSQ type question. Okay, now a forward path transfer function of a unity feedback system. Okay, UFB in short, I will be using it several times later also, is unity feedback system. The forward path gain is given to you, GS equal to K upon S power N into S plus A. The system has a 10% overshoot and the velocity error constant of 100. Now, I am going to take up steady state errors actually, but since it is revision, I expect that KV formula you are knowing and I am going to revise it soon for you. Okay, so what is the KV formula? What is the KV formula? Limit S tending to 0, S into GS actually. Limit S tending to 0, S into GS. That is the KV formula. Okay, which of the following is or are true? Which of the following options is or are true? MSQ question. One or more than one options can be the correct here. Clear? So, limit S tending to 0, S into GS I need to solve. Okay, now if I put down the limit S tending to 0, S into GS. First of all, KV. Velocity error coefficient is related with ramp error and it has to be type 1. Okay, steady state error for ramp will be finite. It has to have the finite value of, it has to have the value of n equal to 1. Okay, even if you put this way, na? Okay, limit S tending to 0. Okay, S into K upon S power N into S plus A is 100. That is finite. And if it is finite, there should not be any single S term in the denominator. Because if there is the S left in the denominator outside, 1 upon 0 will be infinity. Okay, so that first of all tells you n equal to 1. Okay, type 1. I am going to define the definition of type. Okay, it is type 1. The number of poles of GS at origin for unity feedback. Just wait, I'll define it. I think I took this question here because of the overshoot actually. Okay, it is a type 1. Okay, now what is the value of K and A also? See, if you take n equal to 1, then what is the limit S tending to 0? This will cancel. Okay, S equal to 0, so what will be left? K by A. So K by A is 100. That is one relation. But what is K and what is A? What is K, what is A? For that we need to use the overshoot, and then we can also calculate the damping ratio. So what is the value of overshoot given to me? Okay, what is the value of the overshoot? The percentage overshoot is 10%, or if I take the absolute value, which is to be obtained by e power minus pi cot phi, is 0.1 actually. The absolute value 10 by 100. Okay, e power minus pi cot phi. So minus pi cot phi will become ln 0.1, will become ln 0.1. Okay, ln 0.1. You can solve, or I'll give you one more formula here. Okay, you can just solve. So what is the value of tan phi? Actually, if you are going to use calculator, calculator will not give you the cot function but the tan function. So tan is 1 upon cot, that will become minus pi upon ln 0.1. Okay, so how much is this value approximately? This value is 1.36. Okay, taking the inverse of it, taking the tan inverse of it, my answer is 53.76 degrees. Okay, so what is the zeta? Zeta is cosine of phi. I got the phi, then I can calculate zeta also. So it is 0.59 approximately. We can call it as 0.6, not a problem. 0.6, correct? So zeta is 0.6. Okay, or another way can be, if you want to go, if you can remember more formulas, see, overshoot is e power minus pi cot phi. Okay, solving from here, zeta turns out to be ln overshoot divided by under root of log of overshoot whole square plus pi square. Even if you solve using this formula, yes, you will be getting the answer as 0.6. Okay, minus ln overshoot, of course, overshoot is less than 1, na? Yeah. So this is what is the formula that you are finally going to get it. Okay, so if you want, you can use this formula. Same answer, zeta equal to 0.6 will come up from here also. Okay, so that is another way. If overshoot is given, you can note down the zeta formula, minus ln mp upon under root of ln mp whole square plus pi square. Otherwise, you can solve by the overshoot formula also, as I've showed you both the methods. That model is important. So now zeta is known to me. Now coming to the characteristic equation here. Zeta is 0.6, so option number B also correct. Now coming to the characteristic equation of the system. See, what is given to me? GS. GS is K upon SS plus A. And HS is equal to 1, unity feedback. In the GS, n value 1, I have already decoded. Okay, so what is the characteristic equation? 1 plus GSHS equal to 0. So S square plus AS plus of K equal to 0. S square plus AS plus of K equal to the 0. Okay, plus of K equal to 0. Omega n square will be K. Okay, and omega n square is K. And what about this particular term? 2 zeta omega n equal to the A. Right, out of which zeta is known to me. Okay, and omega n square is K. And what I know, one more relation, K by A is 100. K by A is 100. So we have to convert into one variable. So as we have noted earlier, K by A is 100. Na? So let us use K is equal to 100A. Okay, so let us use K as 100A. So I can write down omega n at least as 10 root over A. Okay, let me write down omega n here as 10 root over A. And this is equal to A. Solving from here, I am going to get the value of A. And how much is that value? I am left with under root A will be 12. So A will be 144, 12 square. A will be 144. Clear? Okay, if A is 144, then K, which is 100A, will become 14400. 14400. Right? Okay. Sajid, don't worry. If you need more clarity about type, I'll just come to steady state error actually. I'll first define you the type. Okay, I'll first define you the type. I think it will be automatically clear. Okay, so see, what are the correct options till now? The type 1, system is type 1, correct. The damping ratio 0.6, very correct. The value of A, 144, correct. The K value is 14400, the D is wrong. 3 options are correct for this MSQ question, that is A, B and C. The three options are correct for this MSQ question, and that is known as the A, B and C. That is known as what? A, B and C. Okay, A, B and C. Okay, let's move ahead. Okay, let's move ahead. Okay, let's move ahead and let's come to this particular question. Steady state errors. Okay, let's talk about the steady state errors also. Okay. Okay. Numerator has e power minus s. So you can think about time shifting property, na? Okay, in the s domain you have an exponential term. Right, Venkat? That is how you can approach that particular question. Yeah, let's come up here the steady state error. First of all, the error signal as a standard definition, if it depends on the system also, but most general definition of error is defined as the error between reference input and the obtained output, RT minus CT. And then of course in the S domain it becomes RS minus CS. When I say steady state error, it is the error at steady state. It normally means what? Error at the steady state. And steady state means t tending to infinity. That means steady state error ESS will be defined as the value of the error signal limit t tending to infinity ET, but from the final value theorem point of view, limit s tending to 0 s into ES. It will be defined as the limit s tending to 0 s into ES. Okay. Right. So to calculate the steady state error, I need the ES. If I am solving in the S domain, I need the error signal ES in the S domain. Okay. Now if I take a non-unity feedback system, see what is given, what is the first thing I have taken here is a non-unity feedback case. Okay. In non-unity feedback case, okay, this is our input signal. This is the output signal. Okay. This is what is suppose some signal known as the feedback signal CS into HS. Let me write it here. CS into HS, that is the feedback signal that is going to be compared with the input. Okay, and the corrected input applied to the plant, is known as the US, which is also known as actuating signal. Actuating signal, or we also call it as the corrected input as per the feedback obtained, the input corrected and then applied to the plant GS. Okay, actuating signal or corrected input. But what is the value of this actuating signal? This actuating signal is very clearly the RS minus CS into HS. So if I talk with respect to this block diagram, there is no node where you are able to define error signal. Error signal is R minus C. What you are getting here is R minus CH, which is the actuating signal, but in general not equal to the error signal. Okay, but yeah, if HS I remove, that means if I take HS equal to 1, then you get R minus C, then that is the error signal. Okay, for HS equal to 1, the actuating signal is equal to the error signal. So what I will do is, first I will do the discussions for unity feedback system. Now, can't we find the error for non-unity feedback system? Yes, we can. I'll come to non-unity feedback in some time. Let us first focus on the unity feedback system actually. First target unity feedback so that you come to non-unity feedback after it. Okay, so first talking about unity feedback signal, where the actuating signal will become the error signal, as you see R minus the output coming up here directly, and then again solving from the block diagram, easily you will get that the ES is RS upon 1 plus GS. What I am interested in the steady state error. So what is that steady state error? As I already defined by final value theorem, it is limit s tending to 0 s into RS, limit s tending to 0 s into ES, and then it can be written as s into RS upon 1 plus GS, correct? Limit s tending to 0, s into RS is divided by 1 plus GS. Limit s tending to 0, s into RS is divided by the 1 plus GS. That is what is the steady state error, clear? Limit s tending to 0, SRS is divided by 1 plus GS. Now, that means the steady state error depends primarily on, two things. See, S is a variable which will be, substituted 0 later on. But number one, it depends on the input. Okay, it depends on the nature of the input. The error of the system depends on the nature of the input. RS is the Laplace transform of input. So what type of input you apply. And secondly, it depends on GS. Okay. It depends on GS, and GS now will define the type of the system. Okay, we all know what is the order. Now listen to what is the meaning of type of the system. Okay, what do you understand by the type of the system? And error, by combining the input and the type of the system, we can have straightforward conclusion for error, and then some general questions also we will solve. Okay, so based on the type of the system, what do you mean by the type of the system? First, let me go to the type of the definition of type of control system. What do you mean by type of control system? The type means number of poles of GS, the number of poles of GS at origin when system is connected in unity feedback. When the system is connected in unity feedback. So remember that the definition of type is for unity feedback systems. The definition of type is for unity feedback system. Number of poles of GS at origin when the system is connected in unity feedback is known as the type of the system. We can call it as K. Suppose there is a GS given K, 1 plus ST1, 1 plus ST2, some simple zeros divided by S power n, 1 plus STA, 1 plus STB, some simple pole terms. But how many poles at origin? If there is a S power n term separate in the denominator, we say that there are n poles at origin, and such a system is a type n system. So I can call this case as a type n system. Clear? But remember, type is defined for unity feedback. Remember the important point. And then the number of poles of GS at origin is known as the type of the system. This is type n. Okay, this is what is the meaning of type. So that's what I'm telling. The error depends on the nature of the input and the type of the system. Okay, now based on the different nature of input, suppose you apply the step input. When you apply the step input, we define a constant known as step error constant, or very commonly known as static positional error coefficient, given by the formula limit s tending to 0 GS. And once you calculate the Kp, which is limit s tending to 0 GS, then the steady state error due to step, as I'm telling you, this is with respect to the step input, steady state error due to step input is given by 1 upon 1 plus Kp. So if the question is calculation or error due to step, okay, it has to be 1 upon 1 plus Kp. So you have to find Kp first, limit of s tending to 0 GS. Then, if the question is the ramp input applied to the system, we define a velocity error coefficient, okay, and the steady state error due to the ramp input is given by the formula 1 upon kV, just the reciprocal of kV. So you have to calculate the kV first, where kV is given by limit s tending to 0 s into GS. Just that formula which I used in the previous MSQ question, kV, limit of s tending to 0 s into GS. Then if a parabolic input is applied to the system, okay, we talk about the parabolic error coefficient or the static acceleration error coefficient and the steady state error, okay, of a system due to parabolic input, okay, due to parabolic input is given by 1 upon Ka, where Ka is the acceleration error coefficient given by limit s tending to 0 s square into GS. Now all these are with respect to unit step, unit ramp and unit parabolic. That also we have to be careful. Okay, due to unit step. Okay, due to unit step. Okay, unit step means RT equal to 1 for t greater than equal to 0. Okay, due to unit ramp. Okay, so what is the unit ramp input? Unit ramp input is equal to how much? Unit ramp is t for t greater than equal to 0, and then we substitute the Laplace transform and solve this, and we get this formula. Laplace of step is 1 by s square. Laplace of ramp is 1 by s square. Laplace of step will be 1 by s. Okay, next is unit parabolic. For unit parabolic, the steady state error already I have given. What is that unit parabolic? RT equal to parabolic t square by 2 function for t greater than equal to 0, and the Laplace of it is given by 1 upon s cube. 1 upon s cube. Okay. So firstly, what I am telling, to calculate the error depends on the nature of the input and the type of the system. Clear? Okay. Based on the input, if the input is step, error is 1 upon 1 plus Kp. So you need to calculate Kp, which depends on GS. Then similarly, what to do for ramp and what to do for parabolic, I have briefed out. Now let us come to the type of the system. As I've defined the type as number of poles of GS at origin for unity feedback system. If it is type 0, see the calculations are written in front of you. Okay. For completion of notes, it is written. I will give you the final conclusion in a tabular format. This is for you to go through. Type 0 system, no poles at origin. So that is why what type of condition is coming up here? S power 0 condition is coming up here. No poles at origin. Okay, then there can be a type 1 system. Okay, S power 1. Error due to step ramp parabolic is calculated. If you want, you go through, otherwise not required actually. But just as a notes, I will give it to you. Then type 2 system, 2 poles at origin, S square in the denominator. The results are noted. I will brief out these results in a tabular format. Okay, remember this simple 3 cross 3 tabular format. Okay, remember this 3 cross 3 table. It is very important. It is very important. So what I have done is I have written the type of the system like type 0, type 1, type 2, and I have written the nature of the input, step, ramp and parabolic. Step being 1 upon S, ramp input means 1 upon S square, ramp input means the 1 upon S square, and the parabolic input means the 1 upon S cube. Okay, right. For a type 0 system, whenever step input is applied, we get the finite answer. Okay, for ramp and parabolic, infinite answer. For a type 1 system, when the ramp input is applied, there we get a finite answer. For step, it will be 0. For ramp, it will be infinite. For type 2 system, we get a finite error. For parabolic input, for step and ramp, 0. So primarily, okay, we'll come to that also if not unity feedback. Just wait, never stop learning. So primarily, all diagonal elements are going to be finite, non-zero finite numbers. Okay, all diagonal elements are going to be non-zero finite number. Okay, so what you can say, type 0 step, type 1 with ramp and type 2 with parabolic will give you finite error. How do you remember it? Type 0 with step, type 1 with ramp and type 2 with parabolic will give you finite error. Okay, then if you have a higher order input, the error will be infinite. If you have a lower order input, that means above 0, below infinite. Okay, type 2 with parabolic finite. So step and ramp are lower order inputs, 0. Okay, this is how you can remember. This is how you can remember. Okay. Also remember one more thing, because this discussion has come up. All this discussion has come up with the help of what? With the help of final value theorem. With the help of what? Final value theorem. Okay, final value theorem has been applied, as I've told you earlier also. Okay, final value theorem is applied. Okay, and that is applicable. Remember, final value theorem, there are some boundations also. Applicable if all poles lie in the LHP or at most one pole at origin. All poles lie in the LHP or at most one pole at origin. All poles lie in the LHP or at most one pole at origin. At most one pole at origin. Clear? At most one pole at origin. At most one pole at origin. At most one pole at origin. Okay, so that is some foundations that you have to take here. Now with this table, let us first solve the simple questions on the unity feedback. Normally a lot of questions are there from unity feedback. Then I'll turn to the non-unity feedback. See here, for the unity feedback control system shown in the figure, the open loop transfer function GS is given to you, 2 upon S, S plus 1. What is the steady state error due to unit step, ramp and parabolic inputs? Due to unit step, ramp or parabolic inputs, what is the steady state error? Due to unit step, ramp or parabolic. So see, unity feedback system is given, very good. What is the GS type then? Okay, 2 upon S, S power 1, one pole at origin. Okay, so it is type 1. Since it is type 1, okay, what are the conclusions? Steady state error due to step. See, type 1 will go with ramp, na? I will write down all the 3 first. What I am telling you is, type 1 you have to link with the ramp. Okay, for steady state error due to ramp will be some finite given by the formula 1 upon kV. Okay, so if it is a lower order input, answer will be 0. I know it. If it is a higher order input, answer will be infinity. Okay, so two answers I already know. They have asked for both step ramp, I have asked for all three, step ramp and parabolic. Now, if it is ramp, the error is finite value 1 upon kV. What is that kV? Okay, so kV we can find separately. kV we can find separately. Limit of s tending to 0. S into GS is my formula. So you solve it up. Limit s tending to 0. Okay, S into GS. Okay, how much will be the value actually? S into GS. So S into GS, SS will cancel and then put S tending to 0, 2 upon 1. So answer is 2. The answer will be 2. Correct? Okay, so the answer for steady state error will be 1 upon 2, that is 0.5. So these are all the three answers. Steady state error due to step will be 0, due to ramp will be 0.5, due to parabolic will be infinity. Finished? So, under a given input, actually you need to calculate only one calculation and rest you can, just conclude from the table. Okay. Right. A will be the amplitude. We'll come to that also, Vaishnavi. Okay. Venkatanaga Vaishnavi, will come to that also. Next question. Now, sometimes error would be given for the feedback system shown in the figure. Okay, the steady state error is 20%, or in the absolute form, it is 20 by 100, that is 0.2. For the step input, what is the value of K? What is the value of K? Okay, what is the value of K? Okay, so error given and some unknown parameter about the system is asked. Okay, so first of all, what is the overall forward path gain? Okay, forward path gain. These two blocks are in cascade. So when you multiply, you are going to get K upon 1 plus 4s is multiplied by the 1 plus s, correct? K upon 1 plus 4s multiplied by the 1 plus s. Now, what you are going to do is, okay. So the error due to ramp, okay, error due to step, and error due to step will require Kp calculation. What is the Kp? Limit s tending to 0, Gs. Limit s tending to 0, Gs. Okay, so when you put s tending to 0, you get K upon 1 into 1, only the K. Kp will be equal to K. Clear? Kp will be K. Now what is given? Steady state error due to step, which should be actually 1 upon 1 plus Kp according to us, is given to you as 0.2. That means 1 upon 1 plus Kp. So Kp is K, is 0.2. So solving it, 1 upon 0.25 and minus 1, K equal to 4. Done. K equal to the 4, option number D. The K equal to the 4, and that is option number D. K equal to 4 and option number D. K equal to 4, option number D, correct answer. Right, next question. Okay, let's move ahead to the next question. See, the unity feedback system has the forward path transfer function 5 s plus 1 upon s square s plus 3. If the system is subjected to the input 1 plus 2t plus 5t square, now understand it. Okay, here your doubt will also get coming up, Venkata. See, RT is equal to 1. How can I write down this input? See very clearly, the input that is given to me is, let me take it here. The input that is given to me is 1 plus 2t plus 5t square. This is step, ramp and parabolic, but I have given you the results with respect to unit step, unit ramp, unit parabolic, na? Okay, so how can I classify this input? This input is 1 plus 2 times t plus, now what is my parabolic? Unit parabolic input is t square by 2. My unit parabolic input is t square by 2, correct? So I have to write it as 10t square by 2. Okay, now this is my unit step, unit ramp and unit parabolic. Clear? Clear? This is what I mean. Now the question is on type. Okay, GS is type 2 here. Number of poles of GS at origin will be 2. It is a type 2 case. Now, because it is a type 2 case, error due to step, see, what is the steady state error? Because it is type 2. Okay, so I already know steady state error will only be finite because of parabolic. For other lower order, it will be 0, 0, plus twice of 0. Okay, plus 10 times 1 upon Ka. See, linearity being applied here. What is the error due to unit parabolic? The error due to unit parabolic is 1 upon Ka. If it is given 10 times unit parabolic, the error will also be 10 times 1 upon Ka. 10 times, because a linear system, na, if input is scaled, output will also be scaled, and hence RT minus CT, the error is also scaled. Simple logic. Okay, so error will also become 10 times. Okay, so that is what is the A factor you are talking about. So the answer actually here has to be 10 upon Ka. The first two parts are 0 only. 10 upon Ka. If there was some error due to ramp, it should be twice here, twice into whatever value. So that is why I have carefully written twice into 0. Now 10 upon Ka, what is the Ka? What is the Ka? Ka I am finding here. Ka we know is limit of s tending to 0, s square gs. S square gs. So when you multiply s square, this is cancelled, and then you put s tending to 0. So 5 into 1 upon 3. So yes, 5 by 3. The value of Ka is 5 by 3. The value of Ka is 5 by 3. So 10 upon 5 by 3, 30 by 5, it has to be 6. The error is 6. 100% some typo error, everything is good only. Okay, I'll correct this option. Okay, and I'll make it as 0.6. What I've opted is 6. So let's say this answer is 6, and I'll mark the option, tick mark the option D. It is 6 only. Okay, all is good. Maybe some typo error happened here. Option number D. Option number D. That is what is the final correct answer. Now you should also know it is not necessary that the question is on step ramp or parabolic only. Na? What if the input is t cube, cubic input? See, normally for most of the times you are getting the questions around step ramp and parabolic. So I have given you that tabular conclusion. Okay, but it does not mean that we cannot solve for any other higher order input. Okay, so if it is t cube, what are you going to do? If it is t cube, what are you going to do? Can you conclude on to this? If it is t cube, then what you are going to do? Okay. If it is t cube, what you are going to do? Just a second here. Please solve it. Yeah. Okay, guys, let's continue here. Let's continue the discussion. Okay, so if it is a cubic input applied, and even the type, see, even normally the questions are on type 0, type 1, type 2, right? But here it is type 3. The type of the system is also higher. It is a type 3 case. So we'll go to the basic formula. Yes, we'll go to the basic general formula of the steady state error. What is that general formula? Okay, so here we are going to use the steady state formula, limit t tending to infinity et, or limit s tending to 0 s into es. S into es. Now what is that es? Okay, it is further given by limit s tending to 0 s, and es was given by rs upon 1 plus gs. Okay, what's going to be my rs? Okay, what is going to be my rs? See, what is the Laplace transform for any t power n function? T power n function, Laplace transform factorial n upon s power n plus 1. Factorial n upon s power n plus 1. So what is the rs here? It is going to be factorial 3 upon s power 3 plus 1. So 6 upon s power 4. That is the Laplace transform of the input. 6 upon s power 4. So steady state error will be given by limit of s tending to 0 s into 6 is divided by s power 4 whole divided by 1 plus gs. Okay, gs, if I write it completely, 1000, okay, 1000 into s square plus 4s plus 20. Okay, actually the entire expression will not be required also. S square plus 20 s plus 15 divided by s cube s plus 2 s plus 10. Okay, now when you simplify the numerator, that is 6 upon s cube, one of the s get cancelled. Okay, so then your expression will be of the form limit s tending to 0 multiplying by s cube throughout now. So 6, and here you will get s cube, and when you multiply s cube here only you are going to get the 1000 term into something divided by s cube cancelled, so only s plus 2 s plus 10 will be there. Okay, but now when you put s tending to 0, answer is 6 upon 0 plus 1000 into s tending to 0. So that is why I only need the term 20. Then from the next bracket 15, and then denominator 2 into 10. So this 2 into 10 is actually 20. So 6 by 15, 0.4 upon 1000. Okay, so 0.4 into 10 power minus 3. And as per the options, I will arrange it as 4 into 10 power minus 4. 4 into 10 power minus 4. Option number A, very correct answer, Nitin Sai. Okay, yes, it is the option number A. 4 into 10 power minus 4 is the final correct answer. The 4 into 10 power minus 4 is the very correct answer. The 4 into 10 power minus 4 is the very correct answer. Right? Now, let's move ahead and let's talk about if it is non-unity. As I told you, the earlier discussions are for unity feedback. Okay, right. So the simple way of dealing with non-unity feedback is, as I told you, in the non-unity feedback system, this is the actuating signal, corrected input, which is not equal to the error signal. This is my forward path gain G. This is my feedback gain H. The way of solving the error for non-unity feedback is converting into an equivalent unity feedback system. So what I do is, I'll convert it into equivalent unity feedback system. Now, what is the equivalent system? Two systems are equivalent if they have the same gains, if they have the same transfer function. Okay, so when you convert to unity feedback here, see here, HS is one unity feedback. But of course, I'm assuming that the forward path gain can be modified, and suppose that is GE, the forward path gain of the equivalent system. But because it is unity feedback, this is the output C, this is the input R, and this becomes the error node R minus C. This becomes your error node R minus C. Clear? And once you convert to unity feedback, you can solve as per you are solving earlier. How do you convert to unity feedback? As I'm telling you, it should be equivalent unity feedback. The final input to output relation should not change. So what is the final transfer function here? Okay, for the first system, because it is non-unity feedback, the transfer function is G upon 1 plus GH. The other one is unity feedback. So the transfer function will be GE upon 1 plus GE, no H there. So you have to equate these two. And once you equate, okay, once you equate, you will get the GE as G divided by 1 plus GH minus G. GE will be equal to G upon 1 plus GH minus G. That is the way to handle non-unity feedback question. Let's understand with the help of example also. Okay, determine the type of the system, because type is also, I told you, defined very clearly. I mentioned that type is defined for unity feedback system, and the steady state error for step, ramp and parabolic for the system given below. Okay, so errors can be calculated for non-unity, but the procedure should be converting to unity and solving it. Okay, I think, I'll mention it. Diagrams are not, some of the diagrams are not clear. So k s plus 1 upon s square s plus 2, and this is s plus 4 upon s plus 3. Non-unity feedback is given to you. Okay, the procedure number 1 is to convert to unity feedback, correct? Okay, so the first procedure is converting to unity feedback, and to convert to unity feedback, the GE will be G upon 1 plus GH minus G. That is the formula I told you. So I will start with this formula, GE, which is G which is k into s plus 1 upon s square s plus 2 upon s square s plus 2 divided by 1 plus G into H. What is the H? Is s plus 4 s plus 3, s plus 4 upon s plus 3 minus G, which is again k s plus 1 upon s square s plus 2 upon s square s plus 2. Now I will multiply throughout by k, actually I'll multiply throughout by s square s plus 2 s plus 3. So once I multiply s square s plus 2 s plus 3, numerator will be left out as s plus k s plus 1 s plus 3. Denominator, the first term will become s square s plus 2 s plus 3 plus k, this will be entirely cancelled, k s plus 1 s plus 4. Next term again k s plus 1, but s plus 3 will be multiplied. Up to this part will be cancelled. Okay, so when I simplify this GE, okay dear, let me write down the simplified GE here. What is going to be the value of GE? That is k s plus 1 s plus 3. K s plus 1 s plus 3 upon, let me simplify the denominator, it becomes s power 4 plus 2 plus 3 5 s cube, then 2 into 3 6 s square. Okay, and from the last two terms k s plus 1 common, so s plus 4 minus s plus 3 will be 1, so only k s plus 1. So we can open it like this, k s plus k. But can you take any s alone common? Can you take any s common? Can you have poles at origin? Okay, no, you cannot take any s common from here, not possible. Not possible. That means this type of system is a type 0 system. Clear? Type. See, again I am repeating, please do not say the type from here, okay, the system is type 2, that goes wrong. Type is defined as the number of poles of GS at origin for unity feedback. Not only the poles of GS at origin, but poles of GS at origin for unity feedback. So I first convert to the unity feedback as per the procedure I explained to you. Okay, and then I am able to comment that the type is actually 0. The type is actually 0. Because the type is actually 0, the steady state error, okay, for step, okay, will be obtained 1 upon 1 plus kp. But because it is type 0 goes with step. So for higher order input, it will be infinite. Error first, ramp will be infinite. Error for parabolic will be infinite. Error for the ramp and parabolic will be infinite. Okay, for the step, it is 1 upon 1 plus kp. Now, what is that kp? Okay, first let me figure out the kp, and kp is limit of s tending to 0 gs. Limit s tending to 0 gs. Okay, or GES here. Here the forward path gain is GES. So when you apply to GES, s tending to 0, numerator is k into 1 into 3. Denominator 0, 0, 0, 0, 0, only k is left, k cancelled, it is equal to 3. Okay, and the final answer is for step 1 upon 1 plus 3, that is 1 by 4 or 0.25. For step it is 0.25, for ramp and parabolic it is infinite, of course. For ramp and parabolic it is of course infinite. Correct, dear? That is what is the answer. That is what is the answer to be noted, okay? All right. Now our next question. Please look into this next question. Okay, a GATE 2 marks question, specially, handle with care type of question. See, what is the steady state error of the system shown in the figure? Exact, this is the question with the diagram. Steady state error of the system shown in the figure for unit step input. Okay, handle with care question. Now, it looks like it is a non-unity feedback. Yes, looks like so. Okay, it is a non-unity feedback system. It is a non-unity feedback system. Will you convert to unity feedback? Normally, yes, but not here. Not here. See, that is what, handle with care. If it is non-unity feedback, we normally convert to unity feedback. Why we wanted to convert to unity feedback? Because our standard definition of error says that the error signal should be R minus C, and in non-unity feedback, this is known as actuating signal. Clear? And that is why to define a node for error signal, we convert to unity feedback. That was the logic, to convert to unity feedback. Look into this question. Okay, for this question, I converted to GE. But for this next question, you please carefully see this node. They have mentioned what is the error signal. They have redefined the error signal. I told you in the beginning, if the error definition may change also under circumstances. So here, error signal is equal to, okay, what is this? This is R. And what is this? This is the output C applied to the feedback gain, that is H. Okay, so the output of this block is CH. That is going to be subtracted to R minus CSHS, which is the actuating signal. So here the error signal is equal to actuating signal. So need not convert to unity feedback, because if you convert to unity feedback, okay, because if you convert to unity feedback, okay, the node that you define at the summing point output will not be the error node. So please do not convert to unity feedback. Okay, so you have to solve by how? You have to again solve by fundamentals. Okay, how do I solve this question then? How do I solve this question then? Okay, because, okay, my error definition is something new now. So what will I do? Steady state error. Again, limit. Whenever it is any generic case, now I'll use the formula like I use for the cubic question also. S into RS upon 1 plus GSHS. Why? Why like this? Okay, first let me show you this, or let it be like this. First, let me show you this calculation. Okay, so what is the, output node? See. Output is equal to, what is the input here to this block? This is my GS block, cascade of these two. Okay, E applied here, multiplied by G will give you the output. Okay, but what is E signal? I have written already. E signal is R minus CH here. R minus CH into G. So from here, actually let me convert to the error signal. I am interested in error signal. Okay, so C is E into G. And error, as I'm telling you, is R minus CH. That becomes R minus C, which is E, G, and then H. So from here, if you find error signal, it will be R upon 1 plus GH. For unity feedback, it was R upon 1 plus G. Here it is R upon 1 plus GH. Okay, so we'll go with the basic formula, limit S tending to 0, S into RS upon 1 plus GS. Putting down the values now, limit of S tending to 0, S into RS. RS is the step signal only. So Laplace transform of step is 1 by S. Upon 1 plus GSHS. What is the GS? 4 upon S plus 2. And what is the HS? Is 2 upon S plus 4. 2 upon S plus 4. Okay, so SS cancelled. This is 1 and then 1. S tending to 0, so 4 by 2 and 2 by 4. So denominator is 1 plus 1. So final answer 1 by 2. NAT question it is 0.5. Okay. That is what a handle with care question. What point, Avinash? What about K I have taken? Na? This K I have taken in the forward path gain. This entirely I have taken Sajin as the GS. So K is included here. This is my GS. Okay. I have taken with care. Yes, Avinash, can you help me? What point is not clear? What I want to say is, if it is non-unity feedback system, we normally convert to unity feedback. Why we convert? The reason was clear, na? Because in non-unity feedback, generally the output of the summing point is the actuating signal R minus CH, which is not the standard error signal. Standard error definition, if nothing is mentioned, is R minus C. So if I want R minus C, if I want the error, I convert to unity feedback and I got some GE formula. But what is the specific thing in this question? Okay, what is the specific thing in this question? I'm repeating again since some of you are having the doubt. In this question, look into the block diagram. This is the exact question of GATE given. So in the output of the summing point, they define error signal. That means they have redefined the error signal. What is the redefined? RS minus CS into HS. Okay, RS minus CS into HS. So what I do is, okay, now I see the output equation. C E into this is G. I have taken this as the G gain. Okay, so E into G is the output. Okay, and what is the E signal? E signal is R minus CH. So I put down the value of C. Okay, and then I simplify, I get error as R upon 1 plus GH. Since the definition of error changed, but what will not change is the final value theorem. So what I have applied here, see, what I have applied here, once again, steady state error means limit t tending to infinity et, which means limit s tending to 0 s into es. That will not change. The final value theorem I have applied, and then es equal to rs upon 1 plus gs I have substituted, correct? This is what I have used. Okay, hope that is clear. Hope that is clear to you. If there is any other thing, rest is calculation. If there is any other thing, you can let me know. If there is any other thing, you can let me know. And now, slowly also enter into the stability criteria. Slowly also enter into the stability criteria. First, starting with the absolute stability, the Routh-Hurwitz. Okay, where the most important case in Routh-Hurwitz is around auxiliary equation, the row of zeros case. Okay, so when we talk about stability, we consider two types of stability criteria: absolute stability and relative stability criteria. Okay, what do you mean by absolute stability criteria? First we'll start that, later we'll go to the relative stability. What do you understand by absolute stability? Absolute stability means which will only say the quality of the system. It is known as a qualitative measure. What quality? Whether the system is stable or unstable. It gives an idea whether the system is stable or not. That's it. Okay, that means it just gives a yes or no answer. Given a system, whether it is stable, yes or no, that's it. Okay, but when I talk about relative stability, see, sometimes if you have two systems, maybe both are stable. So absolute stability can only tell yes, both are stable. It can only give a yes or no answer for both, and suppose yes, both are stable. Okay, yes, both are stable. Okay, so which of them is more stable if both are stable? Can we compare? That comparison can be done by relative stability method. But to compare, we need quantity of stability. Okay, we need the quantity of stability, because randomly, suppose for example, if I pick up two things, okay, one is this phone, one is this mouse. If I pick up two things, of course, for me this looks heavier. If I want to actually measure who is heavier, I will measure weight. Okay, I will measure the weight. There is something, if I want to compare who is heavier, I need to have a quantity, that is weight here. Similarly, I am telling you I want to compare stability of two systems. So I need to have some measure, like weight is the measure to compare who is heavy or who is lighter. So we need to have a measure, and that measure is in terms of gain margin and phase margin, which I will cover after some time. That measurement of stability is in terms of gain margin and phase margin. So this relative stability, it is a quantitative measure which is used to compare the stability. Okay, the system having like the body having more weight is said to be more heavier, na? Similarly, the system having more gain margin or more phase margin is said to be more stable. Okay, okay. But before going to that, let us start with the absolute stability. Later we'll go to the relative stability. Okay. Yes, Avinash, very correct. And never stop learning also correct. If that ES node was not mentioned, then you will convert to unity feedback and then only will solve. That also is 100% correct. Okay. That also is 100% correct. Okay, please note that if I just change the question, okay, if this was by chance not mentioned, then you have to convert only. Then you have to, if nothing is mentioned, you have to follow standard definition of error, R minus C. Clear na? Clear na? Okay, let's go back. Okay, let's go back. Okay, so yeah, we are defining the types of stability, absolute and relative stability. Okay, what is the meaning of both of them? Absolute and relative stability. And now, the next thing we are going to do, okay, is talk about, the relation of absolute stability with respect to the poles. Absolute stability with respect to the poles as per our basic discussions and understanding of the system. Final conclusions here, and then the methods, that if all the poles of the system are in LHP, if all the poles, okay, whether 1 or 2 or whatever number of poles, but if all of them are in LHP, system is stable. Even if a single pole, whether there are 10 poles, 9 in LHP but 1 in RHP, but even if one single pole in RHP, the system is unstable. Okay, when there is a pair of complex conjugate roots on the imaginary axis, system will be marginally stable. Okay, zeta equal to 0 case you can relate, zeta equal to 0, pair of imaginary roots. Okay, now see here, sometimes I'm using the word root, sometimes I'm using the word poles. Let me make it very clear. These will be interchangeably used. See, these will be interchangeably used because what is my closed loop transfer function? What is my closed loop transfer function? It is given by the formula GS upon 1 plus GS HS. But for stability, what is important? For stability, what is important? Stability depends on location of poles. Okay, stability depends on the location of poles of the closed loop transfer function or the closed loop system. Now, how do you calculate the poles? Denominator 1 plus GSHS equal to 0. Okay, and the equation 1 plus GSHS equal to 0 is known as what equation? This is the characteristic equation. So I can say that the poles of the systems are equal to the roots of the characteristic equation. Okay, so this is going to be used interchangingly. The roots of characteristic equation or the poles of closed loop transfer function is one and the same thing. This is the characteristic equation we know, right? So if all poles are in LHP system stable, even if minimum one pole in RHP system is unstable, if there is a pair of imaginary roots, complex conjugate roots on the imaginary axis plus minus j omega, and then the system is marginally stable. If there is a repeated pair on the imaginary axis, system is unstable. No need to derive, but actually it corresponds to T into sin T batch, T into sin T type of signal. Okay, so when there is a repeated pair on the imaginary axis, system is unstable. When there are two different pairs of complex conjugate roots, then also marginally stable. Okay, so what are the important bullet points you have to remember? If you want a system to be stable, purely stable, all the poles must be in LHP, not even imaginary axis. Okay, if you want the system to be purely stable, all the poles, whether the poles are real or complex, I don't know, but okay, real or complex, I don't know, but they should be in the LHP, whether real or complex, anything, but they should be in the LHP. Okay, second point, marginally stable if there is a pair of complex conjugate roots on the imaginary axis, pair of j omega roots. Okay, now how will a system be unstable? What can make the system unstable so that we know how to avoid that case? What can make the system unstable? If there is a RHP root, number one, that RHP root may be real or complex, anything. There is a RHP root. Second, if there is repeated pair on the j omega axis, if there is a repeated pair of roots on the j omega axis, then also the system will be unstable. Clear? Okay. Right? Right. Chalo. So now, if you want to talk about some important points about stability only for first and second order, then we go to higher order. For first and second order, if all the coefficients have the same sign, system is stable. Say for example, if I just write down second order only, if I write down second order, s square plus 2 zeta omega n s plus omega n square. So this is omega n square, okay, and even in fact omega n natural frequency is positive. So this is positive, this is positive. But what we have learned till now for second order, that whenever zeta positive system is stable, zeta negative make the system unstable, made the system unstable. Okay, Monish, it will be taken on the app actually. Okay, so zeta positive makes the system stable, and if zeta is positive, actually all the coefficients are positive. So for second order, in fact for first order also, okay, if all coefficients are of the same sign, system is stable. I am specifying this condition because I have seen that students even sometimes for second order start applying RH. You can apply RH. Okay, you can apply RH. You can apply RH, but not required for second order. You can apply Routh-Hurwitz, but not required. For second order system, if you just see that the coefficients are of the same sign, then the system is stable. Okay, let's take a question here. Let's take a question here. Guys, can you please try to answer this question? Correct? Yes, Manish, as I told you, that's going to be app class. Okay. How the exact class will be, if you want to have some information about it, it will be app class. You can contact our numbers. They'll guide you exactly how the classroom will look like. Yes. Please solve this question, guys. Give me a minute's time. Yes. Yes, guys. Let's see if you have solved it. All right. So the open loop transfer function of a unity feedback control system is GS equal to K S plus 2 upon S plus 1 S minus 7 for K greater than 6. Yes. Let's see. For K greater than 6, the stability characteristics of the open loop and the closed loop system, both. Okay, so open loop transfer function is already given, and any transfer function or any system is stable if it does not have RHP poles. Okay, so if you talk about OLP, okay, I will keep using this word now. OLP means open loop poles. Okay, what are the open loop poles? Poles of open loop transfer function. S is -1 and +7, RHP. And if there is a RHP pole, that transfer function or that system cannot be stable. So very clear, open loop system, unstable. Open loop system is unstable. Okay, very clear. For that, you don't have to do any calculation. You just have to observe the poles. Now coming to the closed loop system. Okay, of the closed loop configuration. So for closed loop, what is important? No need to get the transfer function. Poles of closed loop system means roots of characteristic equation, I told na. So only what I need is the characteristic equation. What is that characteristic equation? 1 plus GSHS 1 plus K S plus 2 upon S plus 1 S minus 7. into HS, unity feedback, it is equal to 0. So solving it, S square minus 7 plus 1 minus 6S minus 7 plus KS plus 2K. So rearranging the terms, S square plus K minus 6 into S plus 2K minus 7 equal to 0. Now the characteristic equation starts with plus and it is a second order. That is what? It is a second order. And because it is second order, K minus 6 into, because it is a second order, do I need any RH criteria? Actually not, because okay, only coefficient sign will matter. Now what is given about K? K greater than 6. That is actually given to you. Given K greater than 6. So what about K minus 6? It is positive. Now K minus 6 will be positive. Now because K is greater than 6, that means 2K will be greater than 12. Okay, so 2K greater than 12, also greater than 7. Na? So 2K minus 7 will also be positive only. 2K minus 7 will also be positive. All coefficients are of same sign. Dear, all coefficients are of the same sign. What can I say? System is surely stable. All coefficients are of the same sign. The system is purely stable. Okay. So yes, the closed loop, open loop is unstable, but the closed loop is stable. Okay, option number C. Unstable and stable. Option number C. Yes, correct answer by Nithin. Correct answer by Just Lil Info. Yes, correct answer. Okay, open loop unstable and the closed loop is stable. Okay, so that is what for second order you don't need actually any type of RH criteria. Sometimes students will apply. That's why I'm giving you this question additionally. And there have been questions on second order also. Okay. But what I'm telling you, if it is a higher order system, the above condition is necessary. Above condition is necessary means all the coefficients must be of same sign. Okay. But not sufficient. That is necessary. If this fails, system can't be stable. But if all coefficients are of same sign, then we need to check one more condition. Alone, this is not sufficient. That sufficient condition is the Routh-Hurwitz actually. Will be coming up in the form of Routh-Hurwitz. So let's move forward. Okay, so if I take a nth order characteristic equation, see what are the necessary conditions so that the above equation does not have any RHP root is all coefficients must be of same sign and none of the coefficients must be missing. What it means that? It simply means that all coefficients strictly positive. If I assume positive, all coefficients strictly positive, not even 0. Okay, not even 0, because if a coefficient is 0, suppose if I take a coefficient 0, okay, then it is missing. That particular term will be missing. So you should not have even a missing term also. Okay, so all coefficients strictly positive is the necessary condition. Now, if the necessary condition is met, okay, you need to solve Routh-Hurwitz for sufficient condition. Okay, the sufficient Routh-Hurwitz how to form, I will directly explain you with the question. Okay, the sufficient condition so that characteristic equation does not have any RHP root is there should be no sign change in the first column of Routh-Hurwitz. That is a sufficient condition. Then the number of poles, okay, the number of poles lying in the RHP is equal to number of sign changes in the first column of the Routh-Hurwitz. Number of sign changes in the first column of the Routh-Hurwitz. Okay, some more basic, sometimes theoretical points you should also remember that Routh-Hurwitz. How to form Routh-Hurwitz, I'm just explaining you with the question, but it will be only for polynomial equation, something like this. Okay, polynomial equation is an equation involving several powers of s. Okay, s square, s cube, s power 4 up to any s power n. Okay, but not involving any of the terms like e power s or sinusoidal sine function of s. Only for polynomial function. Okay, it is applicable when the coefficients are real. So all the coefficients like here 1, 1.5, 2, 4, 5, 10, they must be real number. Complex coefficients not allowed. Okay, it will be only telling you the quantity of roots as per the sign changes in first column. Okay, but it will not tell the exact location. I don't need also. I only need whether the root is an RHP or not. Anywhere if there is a root in RHP, system is unstable. So I even don't need the exact location, and it can't distinguish between real and complex roots. Suppose it tells you there are two RHP roots. But it will not tell you that whether those two are real or those two are complex conjugate pair. But again, not needed. Na? If 1 or 2 or any root in RHP system is unstable, that's what. Na? So that's not required also for stability, but as a general limitation, you should know about this procedure. Now let's come to the question. comment on stability, and mostly the question these days will not only talk about commenting on stability, the number of j omega RHP or the LHP roots, okay, for the given characteristic equation. Okay, now how do you form the Routh array? Routh array will be started by first two rows. Understand the formation of Routh array here. Understand the formation of Routh array here, and the Routh array is to be formed by taking the first two rows as s power 5 and s power 4. The highest coefficient is s power 5, highest term is s power 5. Then the coefficients to be taken is alternate terms, s power 5, s power 3, s power 1 coefficient. So that is 1, 2 and 5. 1, 2 and 5. Then s power 4 row, okay, take the coefficient starting from s power 4 again in the alternate manner. So s power 4 coefficient, s power 2 and s power 0. That is the constant term. So 1.5 and 4 and 10. 1.5 and 4 and 10. 1.5 and 4 and 10. Okay. If you don't know, I'm just explaining you the formation of Routh array directly by an example. Okay, now see, first two rows are directly obtained by the given equation only. Then we form the s raised to the power 3 row. Then we will form the s raised to the power 3 row. Okay, what is the s power 3 row? It will be formed by using the rows, two rows above the s power 3, and you solve this determinant in the reverse order. You will take these four numbers and solve the determinant reverse. Normally you cross multiply 1 into 4, but here you will be solving in the reverse manner. Okay, and that is 1.5 into 2 minus 1 into 4 is divided by 1.5. Clear? Okay, I'll write down this calculation actually separately. 1.5 into 2 minus 1 into 4. Okay, and then divide by the first element of the above row. What is the first element of the above row? 1.5. Okay, so how much will be this calculation? 3 minus 4, minus 1 upon minus 1.5. See, a sign change occurred, na? Minus 1 upon 1.5. Next. Now next, how do you form the next element here? See, when you are solving the next element, what determinant? The first column will always be the first column above. Second column will keep changing. Second column will be the column next to the element. Second column, like here, this was the second column. For this element, this is the next column, the column next to it. But first column will not change. Okay, so this cross multiplication, 1.5 into 5 minus 1 into 10. Okay. Next, 1.5 into 5. 1.5 into 5 minus 1 into 10, and again I told you divide by the first element of the above row. So divide by 1.5 always. So how much this is? Minus 2.5 upon 1.5. Minus 2.5 upon 1.5, and last element of a row will always be 0. Last element of a row will be always 0. Why? Because, if you want to solve the determinant, where is the next column? No next column means 0, 0. And if a column is 0, determinant value is also 0. Okay, determinant value is also 0. Okay, now dear, if there are fractional numbers, that is your choice. But if there are fractional numbers, okay, like, 1 upon 1.5, 2.5 upon 1.5, you can multiply entire row, not a single element, but you can multiply or divide entire row by any constant, but a positive constant. Multiply an entire row by any positive constant. Don't take a negative constant, sign change will occur. Sign change is the most important thing here. Okay, so what can I do, dear? What can I do? I can multiply this by 1.5. By any common value you can multiply. So then the s power 3 row will look like minus 1, minus 2.5 and 0. Clear? Now go to the next calculation, s square. Multiplying this or not is your choice. But I suggest to multiply so that the next calculation is of course simple. Okay, but whether to multiply or not, that is your choice. Okay, now, and multiply by any constant but positive. Don't sign change by yourself. Okay, now, now because this is the s power 3, you don't count this now. Okay, please don't count this. This is gone. Okay, now, minus 1 into 4. These two are the above rows. Okay, minus 1 into 4. Now, calculations are clear. I will not write down. I will write down the final answer. Minus 1 into 4. Minus of minus will become plus. So, 1.5 into 2.5. How much it should be? 1.5 into 2.5 is 3.75, I think, right? Yes. Okay. Yeah, correct. And then earlier, minus 4 and minus plus. So how much I am getting? I will be getting, and divided by minus 1. Divide by the first element of the above row. So what I am getting is minus 0.25 upon minus 1. So 0.25. what I am getting simply is 0.25. Clear? 0.25. Okay, now come here, next element. Okay, so minus 1 into 10, minus 1 into 10, minus 0. So only minus 1 into 10 divide by minus 1. So only 10 and then 0 and then 0. Now coming to the s power 1 row. Okay, now coming to the s power 1 row. S power 1 row. So see here, 0.25 into minus 2.5 minus minus plus 10. So let me just write down the numbers here once again. Minus 2.5 into 0.25. So this should be 0.625 according to me. Correct, na? 1/4 of it. Right. So minus 0.625 minus minus plus 10. Okay, divided by 0.25. Okay, so how much it should be actually? 37.5. Just cross check the calculation. It should be 37.5. What about the element here? Keep looking. What is the element here? The column on the top. The next column on the top is 0. So the element will be 0. Last element always 0. Now coming to the s power 0 row. 37.5 into 10 minus 0. So 37.5 into 10 upon 37.5, 10. And again this is 0 because the next column is 0. Last element always 0. Last element always 0. Clear? Last element always 0. Yeah, last element always 0. Done? Don't worry, Avinash. It is left where we have time. If you think in 2 hours you can complete control system, that is not possible. So I know what topics are there, what are not there, but you have to have patience. I told you that by the time you have patience, I will keep covering. If you lose patience, of course, in 2 hours, 3 hours, can you cover control system? Not possible. Na? At least we have to go some more hours. Okay. Chalo. So that is what. Okay. This is what it is. Okay. But what topic I cover, I will cover sufficiently so that you have revised, and even if you're studying it for the first time, it is understood. Not just like, rushing out through the things. That I will not do. Simply rushing out through the things I will not do. Now, if I tell you the first column, now see, very neat and clean. What is the first column? Okay. Let me bring it here. Understand the neat and clean first column here. So what are the elements in the first column? 1, 1.5, next element minus 1. Okay, next element 0.25, next element 37.5, and next element 10. Finish. Okay, next element 10 is finished. Okay. Now, please tell me how many sign changes. See, I'm not interested how many negative numbers. I'm interested in sign change. So plus, plus and minus sign change. Then again minus 2 plus 2 sign changes. Then rest is plus only. 2 sign changes. Okay. So what can I say as per the sufficient condition of the Routh? What can I say? That the number of sign changes corresponds to number of RHP roots. Okay. Number of RHP roots. Okay. So see, how many RHP roots? How many RHP roots? Is 2. And because there are 2 RHP roots, system is unstable. Even if a single RHP root, system is unstable. Correct? So comment on stability is also done. But now I'm asking how many are not only RHP, how many LHP, how many J omega, everything I want. Okay. How many J omega axis roots and how many LHP roots? J omega axis roots 0. I'll give you a simple point. J omega roots, okay, can only occur with auxiliary equation, and auxiliary equation will come with row of 0. So dear, unless and until you get a row of 0, unless and until you get a row of 0, unless and until you get a row of 0, right? Don't think about J omega roots, clear? Don't think about J omega roots unless and until you get a row of 0. Okay. So how many LHP? So order of the equation was s power 5, fifth order equation. Fifth order equation will have total 5 roots. 2 goes to the RHP, nothing on the J omega. So 3 on the LHP. 3 on the LHP. So if they ask LHP, don't think about J omega till you get the ROZ case. So I'll come to the ROZ case also. We'll come to the ROZ case also. The most important case actually from the RH, most expected and most important case. Okay. Now, some specific cases in the RH also let's take. Okay, and the first special case, when first element of a row is 0, then I will take when the entire row is 0. Then I will take when the entire row is 0. That is what is ROZ. Okay, row of zeros. But right now, only when the first element of a row is 0. Understand by this example. only when the first element of a row is 0. Please understand by this particular example. Okay, what is the characteristic equation of the system? S power 5 plus S power 4 plus 2SQ plus 2S square plus 11S plus 10. Let me form the Routh array here, starting with S power 5 and S power 4. Okay, what are the alternate coefficients? Starting with the S power 5. Okay, so 1 and 2 and 11. Okay, 1 and 2 and 11. S power 4. So 1 and 2 and 10. That becomes 1 and 2 and 10. Clear? Now come to the S cube row. Now coming to the S cube row. So 2 minus 2. See here. 2 minus 2. 0. Okay. 0. Then 11 minus 10. 1 upon 1. Divide by the first element of above row. So 1 minus 1 upon 1. 11 minus 10. That is 1 upon 1. The answer is, this was 0. This is 1. And then last element of a row is always 0. Now please see that if you are going to form the S square row, what is going to happen? If you are going to form the S square row, what will happen? You think, na? If you are going to form the S square row, what the things can change? If you are going to form the S square row, any element of this row is divided by the first element of the above row. Okay, to form this row, we have to divide by the first element of the above row, and the first element is 0. Okay, so all divide by 0, all undefined parameters can start coming. All undefined parameters can start coming, and hence our Routh array becomes undefined. Okay, right. Routh array was being undefined. Okay, right. Routh array becomes undefined. So if the Routh array becomes undefined, we have to come to a solution. Okay, so when the first element of a row becomes 0, then all elements of the next row will be undefined. To overcome this problem, replace the 0 element by some small variable. Suppose 0 is not 0, it is some small variable epsilon, and then solve the Routh array. So what will I do is, I will replace this small element. I'll replace this 0 by some small element, suppose epsilon, and now continue in terms of epsilon. Now, first let's continue in terms of epsilon. So what is the next row now? 2 epsilon minus 1, cross multiply, divide by epsilon. Next, epsilon into 10 minus 0. So epsilon into 10 upon epsilon. So 10, and last element anyway is 0. The last element anyway is 0. Okay, now S power 1 row. Next is the S power 1 row. What is the S power 1 row? So suppose x into 1 minus 10 epsilon divided by 2 epsilon minus 1 by epsilon. So after dividing, the first term will be 1 only, minus 10 epsilon upon 2 epsilon minus 1 by epsilon. So better shift the epsilon to the numerator. That becomes 10 epsilon square. This element will be 0. See, because the column on the top is 0 and last element always 0. Last row S power 0. Say this is x. X into 10 minus 0. So only x into 10 upon x. X cancel 10 and 0, 0. This is 0 because the next column is 0. Last element always 0. This is the Routh array solved now. So in terms of epsilon, we are able to solve the Routh array, correct? In terms of the epsilon, we are able to solve the Routh array. In terms of the epsilon, we are able to solve the Routh array. Clear enough? In terms of the epsilon, we are able to solve the Routh array. Now, what is the value of the first column? Writing separately again, as epsilon tends to 0, because epsilon came up with 0. Now let us replace back and put down epsilon tending to 0. For epsilon tending to 0, I get 1, epsilon tending to 0, epsilon. Now here, of course, undefined will come, but at least I know the sign. I have done some calculation. Epsilon 0, so minus 1 upon 0, minus infinity. Next will be epsilon 0, so 10 into 0 is 0, only 1 is left. And last is constant. Okay, we know that an undefined element is come, and at least we now have completed the Routh array, and we know the sign changes also. Okay, we know the sign changes also. See the sign changes here. Okay, plus, 0, you can count plus, minus, anything. Let's count plus. Okay, so plus, plus to minus, minus to plus. Yes, there are two sign changes. There are two sign changes occurred here. Correct. If there are two sign changes that occurred here, then what will I say? Okay, then what will I say? Number of RHP roots. How many RHP roots? 2. So the system is unstable also. Okay, how many J omega roots? 0. How many LHP roots? So fifth order equation again. So 5 minus 2 plus 0. So LHP roots will be 3. LHP roots will be 3. Good to know, just little info. Yeah, I hope, you'll save time for most of the subjects if you keep following the marathons. Okay. Right, Srihari, what do you want to specify? Can you please elaborate your point? Okay, so that is what it is. Okay, so we have two sign changes, and j omega roots, I told you, think only when it comes to the row of 0 condition. So that is why I directly put j omega roots as 0. Okay, right. There is an alternate also for this method. Okay, there is an alternate also for this method. Okay, replace the 0 element, or the alternate method is replace s by 1 by z. Okay, some variable 1 by z, form new characteristic equation and solve Routh-Hurwitz again. Then you will not get this first element 0 for sure. Okay, then you will not get the first element 0 sure. This is an alternate, but I usually don't suggest this. Why? Because from looking into the question, you can't say whether the first element will be 0, right? Now that we can't say. So we start making the Routh-Hurwitz. We have done some efforts and then we come to know 0. Then you will remove the entire Routh-Hurwitz. Then you will make a new characteristic equation and then you will again solve the Routh-Hurwitz. So not required that much effort. So I usually don't suggest it. So, you can fix to the epsilon method. I think okay. I think for me it is okay, but there is another method, okay, which I have just informed you. Okay, which I have just informed you. Okay, which I have just informed to you. Now, before I go to the ROZ, the most important case is ROZ. Before I go to it, okay, one more condition, okay, that is shifting the origin. Okay, now what type of questions? Some numerical questions, maybe not directly related to stability, but some numerical mathematical questions can be expected. To determine the number of roots of any equation lying to the left or right of any line. See, normally RH will tell you LHP. What is the Routh-Hurwitz criteria telling you? LHP roots and RHP roots. What is that LHP and RHP? It is left of j omega and right of j omega, correct? So, what is my LHP, what is my RHP? When I talk about LHP, RHP, it is the left of j omega and the right of j omega. Okay, this is what is my S-plane. Okay, this is my real axis, which is also known as sigma axis, and this is my imaginary j omega axis. When I say LHP, okay, LHP means simply left of j omega axis. Okay, and when I say RHP, so j omega axis is my boundary, na? Okay, RHP means right of j omega axis. This is what is the information, LHP and the RHP. LHP and the RHP, and this is the S-plane given to me. Okay, this is the S-plane. But now if I say you any random line given, sigma equal to minus a. Okay, now what is sigma equal to minus a? Sigma equal to minus a is just like sigma equal to minus a. Sigma means x-axis. It is just like x equal to constant, and x equal to constant is a line parallel to the y-axis. It is a line parallel to y-axis. This is sigma equal to minus 1, for example. Okay, so if I am asking that there is a line sigma equal to minus 1, okay, how many roots will lie to the left or right of this line? But if you directly apply RH will only tell you how many to the left of this line. RH will tell you the answer is this zone and that zone. But what I want, if you apply RH, answer will be 2 and 1. I don't want 2 and 1. What is the answer I want? Left of this right 1, right of this line 2. Okay, that is what is the answer I want. 1 here and 2 here. The smart thing is replace the S by S minus A. Replace the S by S minus A and then apply the RH. Replace the S by S minus A. So here, if you replace S by S minus 1, okay, what is the meaning of S minus 1 actually? Okay, S minus 1 is right shifting the roots. Okay, right shifting the roots. Okay, this is the logic. Right shift the roots by 1. Okay, right shift the roots by 1 means S replaced by S minus 1. That is what mathematically means, S replaced by S minus 1. So if I right shift the roots by 1, okay, suppose say this root was, this is like a minus 1 line. So this is minus 0.5. This is suppose some root, plus 0.5. And this is suppose some root, say minus 1.5. If you right shift by 1, so this minus 1.5 will be minus 0.5. This will become 2.5 and 0.5 plus 1, 1.5. And now apply RH. Now apply RH. First you right shift the roots and now apply RH. What is the answer by RH? RH, okay, with respect to j omega axis, answer is given in RH. And as per RH, how many left? 1. How many right? 2. And that is the answer I want. What is the answer I want? I have framed it. I will get the same answer by RH, but not applying the direct characteristic equation. Applying the RH on the new characteristic equation, which is formed by replacing S by S minus 1. So very briefly, I have explained you the procedure. Finally, what you have to remember? Replace S by S minus A and solve. You will get your answer. See, there is a GATE 16 2 marks question. Okay, and there have been other indirect questions also on this type of concept. Given equation, see, this is not about stability. It looks like a mathematical question. To be honest, it looks like a maths question. Okay, given the polynomial equation. Now, please see that it is a GATE 2016 question, and exactly from GATE 2016, scientific calculators were banned in the examination. Only virtual calculators, the virtual online inbuilt scientific calculator. And you all know that virtual calculator will not have the cubic equation facility. The virtual calculator will not have the cubic equation facility. Okay, right, because if the cubic equation was there, then the question no method. I can calculate the 3 roots by calculator and I will see what is the answer, how many roots will have real part less than -1. Okay, so smartly this question is started from the year where there are no calculators actually, where there are no scientific calculator, only virtual scientific calculator, not the Casio one. Okay, so now what is the number of roots of the polynomial which have real parts strictly less than -1? Okay, so number of roots. So let's say the root. What is the root? It is an equation in S domain. The root is S, which is sigma plus j omega. What type of roots I want? Which have real parts. What is the real part? Sigma less than -1. Okay, what we need? We need the roots having sigma less than -1. That means roots for which sigma less than -1. So now, dear, as I told you, this is the line sigma equal to -1. So any root lying to the left will have sigma less than -1. If you go right, sigma will increase greater than -1. So what I want here? What I want here? Sigma less than -1. The roots lying to the left of sigma equal to -1. Roots lying to the left of sigma equal to -1 will have the sigma less than -1. So to find the number of roots lying to the left or right of the line, first replace S by S minus A and then solve the Routh-Hurwitz. Okay, so let's solve it here. So what is the given characteristic equation? S cube plus something 5.5 S square plus 8.5 S plus 3 equal to 0. Okay, replace S by S minus 1. So you will get a new characteristic equation. S minus 1 cube plus 5.5 S minus 1 square plus 8.5 S minus 1 plus 3. Okay, you will get a characteristic equation. Apply the identities A minus B whole cube and A minus B whole square, which you all know. Okay, get the new characteristic equation, solve, and then feed into the Routh array. You all know how to form the Routh array. So this much calculation procedure I have told to you. You can complete this much calculation as homework. Let's not spend time on this calculation. You will get another cubic equation which you feed in the Routh array. Now whatever Routh array answer will give, how many right? That will be actually right of the line sigma equal to -1. Okay, that will be and you want left. So total 3 minus right. How do you get right? Number of sign changes. 3 minus the right roots will be the left roots. There is no j omega till now also. Clear? So hope you can complete this calculation. Solve and feed to the Routh array, you get your answer. You get your answer. Clear? No, Avinash. See, S by S minus 1 only. See, what is the procedure I have told you? Sigma equal to minus A. The line also taken as sigma equal to minus A, then replace S by S minus A. If it is +1, then you make it +1. So see, what is the line I have given? I have also given the line. I also want the roots to the left of sigma equal to -1. So S minus 1 only. Clear, Avinash? S minus 1 only. It has to be S minus 1 only. So see, sometimes the question may not look like a control system question, but it has to be solved by control concept only. So this is a question on mathematical application of Routh-Hurwitz. Okay, it looks like a polynomial mathematics or aptitude question. Okay, a cubic equation question, where calculators are not there. Remember, cubic calculators are not there with you. Correct, na? So if that is correct, next question. Now let's go, okay, to the most important case. As I've been telling you, when complete row of Routh-Hurwitz becomes 0, I will call it as ROZ. You get row of zeros. The ROZ, the row of 0. Okay, the row of zeros. Let's take up a question and then understand the procedure. Come up to this question first of all. Okay, s power 6 plus s power 5 plus 5s power 4 plus 3s cube plus 2s square minus 4s minus 8 equal to the 0. Okay, suppose this is what is some equation given to you. S power 6 plus s power 5 plus 5s power 4, 3s cube, 2s square minus 4s minus 8 equal to 0. Okay, so now what is required is, see, first let me start forming the Routh-Hurwitz. Okay, let me do it here. Let me start forming the Routh-Hurwitz. Let me take this entire section starting from s power 6 and then s power 5 row. What is the s power 6? Alternate coefficients 1 and 5 and 2 and minus 8. Acha, I will solve it still because I may need number of RHP and LHP roots, but what will I say here? Dear, what is the important point to be noticed here is, okay, there are sign changes in the characteristic equation only. Okay, sign changes in the characteristic equation means what can I say is that necessary condition itself fails. Necessary condition itself fails. Okay, necessary conditions fail. The system is not stable. That is for sure. If they ask now whether the system is stable, that you can say no, it cannot be stable. No, it cannot be stable for sure. Necessary condition failed. It cannot be stable for sure. Okay, but if I want the LHP, RHP roots, I will have to do the complete analysis. So let me keep forming the Routh-Hurwitz. Okay, let me keep forming the Routh-Hurwitz. So starting with the s power 6 row, s power 6, so 1 and 5 and 2 and minus 8, right? Alternate coefficients 1, forgot, 5 and 2 and minus 8, 1, 5, 2 and minus 8. Then s power 5, so 1 and 3 and minus 4, 1, 3, minus 4, the rest is 0. Whatever is not there will be 0, correct? Now s power 4, okay, s power 4 row, cross multiply 5 minus 3, 2, 2 upon 1. Okay, then 2 minus 4, so 2 plus 4, 6, 6 upon 1, 6. 1 into minus 8, rest is 0. So 1 into minus 8 upon 1, so minus 8 and then 0. Then let's come to the s power 3 row. Okay, now you see the calculation. Okay, 1 into 3, okay, minus 6. I think I've done, yeah, sorry. This is wrongly written. No, sorry. This is correct. This is what I have wrongly typed, I think. This was 5 minus 3, 2 by 1. Okay, then 2 plus 4, 6, correct. 1 into minus 8 by 1, correct. Rest all is correct. Okay, rest all is correct. Yeah, you're correct, Mithun Sai. Now, s power 3, 2 into 3, 6, 6 minus 6, 0. 2 into minus 4, minus 8, and again minus of minus 8, 0. This is 0 because the next column is 0 and last element of a row is always 0. This is the case I am referring to. Now you get it. What you have got it is a s power 3 row of zeros. Okay, what you have got it right now is a row of 0. Very clearly what you have got right now is a row of 0. What you have got right now is a row of zeros. Okay, right. So that is what I wanted to highlight to you. Okay, so yeah, let me now call it separately. Complete row of 0 obtained. Now what is the procedure? What is the procedure and what are the conclusions of ROZ? One by one, let's understand with this problem. Okay. No, Sajan. I told you, for higher order, even if all coefficients were positive, Nitin, Sajan, if even all of them were positive, I will say necessary condition fail, necessary condition satisfied. But still system is stable or not, we can't say. That is not sufficient. So then also we go to RH. Then also we go to RH. What I was trying to tell you, necessary condition fails, system not stable for sure. But if necessary condition satisfied, then we need to go for sufficient. Okay, I hope that is clear. Yeah, guys, now let us come, okay, and to understand the ROZ, to, whenever there is a row of 0, you will form auxiliary equation. You will form auxiliary equation. How do we form auxiliary equation? How do we form the auxiliary equation? The auxiliary equation will be formed by using the row above the row of 0. Okay, by using the row above the row of 0. This will give you an auxiliary equation. Now, this equation is a s power 4 equation. What is the first coefficient? 2. S power 4. Next is 6, and we know that these are alternate coefficients. So 6 with s square minus 8 s power 0. So s power 0 is 1. This is what is my auxiliary equation. Clear? So whenever I get a ROZ, I will make a auxiliary equation. Step number 1. Step number 2, I will differentiate this auxiliary equation. I will differentiate this auxiliary equation. Okay, so 2 into then 4, 8s cube, 6 into 2, 12 into s equal to 0. 8 is constant. Okay, so second step is I will differentiate the auxiliary equation, which I have done. Step number 3, I will form a modified s power 3 row. Okay, so next what we form is known as a modified s power 3. We will replace the row of 0, okay, by a modified s power 3 row, and with the coefficients. What is the coefficient of s power 3? 8. Next coefficient 12. So I will come and write down here. What I will come and write down here, I will be writing down a modified s power 3 row. I'll call it as star s power 3, coefficient 8 and 12, rest to 0. This is the procedure, and then continue the Routh array, and then please continue the Routh array in the very same manner. This is what is the procedure I was just trying to tell you here. We first form the auxiliary equation. Okay, then we differentiate the auxiliary equation. How do we form the auxiliary equation? Okay, by using the row above the row of 0. Okay, above the row of zeros. Okay, then differentiate the auxiliary equation, then replace the row of 0, okay, by the coefficients of the above equation. Above means the derivative of auxiliary equation, and then now continue the Routh array. So let me continue first and then talk about other conclusions. Okay, now let me continue the Routh array. Okay, so next row will be s power 2. Now you see 8 into 6. Now this is to be eliminated. This is gone. It has been replaced by a modified row. Okay, so 8 into 6, 48 minus 24. 24 by 8, 3. So next is 3. Then 8 into minus 8, this is 0. So divide by 8. So next is minus 8. This is 0 because this column is 0 and last element of a row always 0. Now s power 1 row. Okay, 36 minus 64. So that is plus 100, 100 by 3. Okay, then this is 0. See the next column 0. Here also next column 0. So this is 0. Last element always 0. Last row s power 0. 100 by 3 into minus 8. Divide by 100 by 3. So only minus 8 is coming out. 0, 0, 0. Clear everyone? Okay. This is what is the conclusion. This is what is the first row, the entire Routh array obtained, I will say. Now, how many sign changes? Okay, if I'm interested in number of RHP roots, now listen to me. If I am only interested in number of RHP roots, okay, is equal to how much? That is still the same number of sign changes in the first column. That will not change. And how many sign changes in the first column? If I scan from top to bottom, 1 plus 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 and a minus. Here is one sign change. Okay, and one sign change will have one RHP root, and even if there is one RHP root, system is unstable. That conclusion is okay. So if they ask about stability, that was already concluded. Here also I concluded is unstable. If they ask only number of RHP roots, then also you need to do only this much. Yes, question finished. But normally what they are asking, tell me the number of LHP roots. Okay, tell me the number of LHP roots. So what they are asking, okay, R is 1. How many roots on R? Okay, what they are asking, LHP roots. So this is a sixth order characteristic equation. 6 minus 1. Okay, but is it only 5? 1 on the RHP, 5 on the LHP? No, it is 1 plus, you have to figure out something now. Okay, you have to now determine if there are j omega roots. If there are j omega roots. So normally they are not asking RHP. If they are asking RHP sometimes, then your question stops here. Only thing is you should know that row of 0 means auxiliary equation, differentiate the auxiliary equation and form the new s power 3 row. Finish. Okay, your question finishes. But if they ask LHP or if they ask LHP or J omega roots, you have to do some more analysis. And what is that some more analysis? What is that some more analysis? To explain you, let me just take an example. Okay, so what is my auxiliary equation? You don't have to solve the auxiliary equation, but just for one case you understand. Just for one case you understand. What is the auxiliary equation? 2s power 4 plus 6s square minus 8 equal to 0, or I can eliminate 2, so s power 4, okay, plus 3s square minus 4 equal to 0. It is factorizable as s square plus 4, s square minus 1 equal to 0. Okay, so s square is minus 4, s equal to plus minus 2j, s square equal to 1, so s is plus or minus 1. Now, important point is, these are the roots of auxiliary equation. Okay, suppose s equal to 1, any of them, okay, s equal to 1 or any of them, try in the characteristic equation. Try in the characteristic equation. Characteristic equation will also be satisfied. You try, s equal to 1, you try in the characteristic equation. Okay, 1 plus 1 plus 5 plus 3 plus 2 minus 4 minus 8, it will be 0. You try it out later. 100% it is going to be satisfied. That means every root of auxiliary equation will be a root of characteristic equation. Are you getting it? That is why roots of auxiliary equation are important. Okay, roots of auxiliary equation are important. Okay, so this is the procedure to handle ROZ case. This is the procedure to handle ROZ case. Now, okay, the row of 0, important point, ROZ will always be in the odd power row. Like here we have got in the s power 3. It can be in any odd power row. Important point is the roots of auxiliary equation. The roots of auxiliary equation will also satisfy characteristic equation. Every root of auxiliary equation is a root of the characteristic equation, and hence auxiliary equation is a factor of the characteristic equation. Okay, is a factor of the characteristic equation. What does this point number 2 says? That characteristic equation can be factorized into auxiliary equation into some other factors. But one of the factor of the characteristic equation is auxiliary equation. Clear? Every root of auxiliary equation will satisfy characteristic equation. Okay, that means, dear, in the question I have got 4 roots, na? In the question I have got 4 roots. All 4 roots are the roots of characteristic equation. Okay, all of them are the roots of characteristic equation. Now, what is the root picture here? What is the root picture here? If I draw it, see, there are 2 roots, plus and minus 1. Plus 1, minus 1. 1 LHP, 1 RHP, but equal magnitude. And plus minus 2j. Imaginary pair. Plus 2j, minus 2j. This is the root picture. You know, normally what will happen? Okay. Normally what will happen? Okay. Normally what will happen? See here. See, the presence of ROZ. What is the importance of presence of ROZ? It may lead to one or more of the following conditions. What is the following conditions? There is at least one pair of imaginary roots. Okay, case number 1. There can be a pair of imaginary roots. Okay, plus jy minus jy. Okay, s equal to plus or minus jy obtained. Okay, or there may be at least one pair of real roots having equal magnitude but opposite sign. Equal magnitude but opposite sign. That's what I got, plus minus 1. Let me generalize it as plus a and minus a, s equal to plus minus a. Okay, or the third condition, there are 2 pairs of complex conjugate roots located symmetric with respect to imaginary, a quadrature of complex conjugate pole. Okay, say this is x plus jy, its conjugate x minus jy. Say this is minus x plus jy, then its conjugate minus x minus jy. The roots are of the format plus minus x plus minus jy. Okay, but important point is all of them are symmetric with respect to origin. How? See, y above origin, y below origin. A to the left of origin, A to the right of origin. Okay, and even all 4, when you calculate the distance of any of these 4 with respect to origin, it will be same. Okay, so they are diagonally symmetric with respect to origin. So roots of auxiliary equation. Roots of auxiliary equation. They are always and always symmetric with respect to origin. Symmetric with respect to origin, and this gives us the important conclusion. What is the important conclusion? See, in the first case, how many roots to the left, how many to the right? Nothing to the left, nothing to the right. L and R 0. In the next case, 1 to the left, 1 to the right. In the next case, 2 left and 2 right. So because of this symmetry there, because of the symmetry, the number of L and number of R roots will always be equal. The number of L and the number of R roots will always be equal. For auxiliary equation, I am telling the number of L and the number of R roots are always equal. Clear? So this is giving you, and what I am telling, whenever there is auxiliary equation, any one condition minimum will come. Not only one, sometimes like in our question, what has happened? First and second condition both has come na, in our question. Okay, so one or more of these conditions will come up. Sometimes one or sometimes more. Okay, but yeah, whatever is there, it is between these three conditions. Nothing other than this can come up. Roots of auxiliary equation cannot be anything other than these three cases. Tell me if there is any doubt. Okay, you see this. You see my roots of auxiliary equation. Case number 2, case number 1 and case number 2 both have come up. One or more of the following conditions can come up. Clear? Now, what I am trying to tell you is, what I have told you right now is, for auxiliary equation, I have written a conclusion for you. Okay, let me bring this slide better to the top. Yeah, come up here. So what is the shortcut for AE roots? Okay, the number of LHP and the number of RHP roots are equal. Number one thing I told you, because of symmetry, and because of that, now see, number of L and R are equal, but what is R roots? It is number of sign changes below the auxiliary equation. See, auxiliary equation is also a equation. It is also a polynomial equation. If I go back to my table, suppose I tell you my Routh-Hurwitz starts only from this point of time. Suppose my Routh-Hurwitz starts only from here. Forget the above portion. Forget the above portion. Okay. So let me duplicate this slide and show you the calculations again. Okay. Yeah. Arey, why it is not moving? Arey dear, please move with me. Please coordinate with me. Yes. Okay. So what I'm trying to tell you is, okay, auxiliary equation is ultimately a polynomial equation, S power 4. Forget to the top. Forget to the top. Forget to the top. Okay. Just look into this part of the Routh-Hurwitz. This is the part starting from auxiliary equation. It is also some equation. Na? Now, if I say this is some important equation for me, how many roots will lie to the right of this equation? Again, by Routh-Hurwitz means sign changes. Again, by Routh-Hurwitz means sign changes. So see how many sign changes only in this part. You don't have to focus here. How many sign changes only in this part? Again, one sign change. How many sign change in this part? Only one sign change here. Okay, only one sign change here. So what I'm telling, number of RHP roots is always number of sign changes, but below AE, because I'm interested for AE roots. But number of LHP and RHP roots are equal. So what should be my conclusion? Okay, for this question. What should be my conclusion for this question? Okay, final answer. The final answer, by this shortcut. Okay, what will you do? You will draw a table with me. Okay, where you will first write down characteristic equation and then you will write down, first write down auxiliary equation and then write down the characteristic equation. Okay, keep listening. First thing is write down the order of both. What is the order of auxiliary equation? Fourth order. What is the order of the total characteristic equation? Sixth order. Now, for characteristic equation, keep listening carefully. For characteristic equation, how many RHP roots? One RHP roots. Why? Why? Because total number of sign changes from top to bottom is also 1. Total number of sign changes from top to bottom is also 1. Okay, so number of RHP roots 1. But what I was not knowing, this I have written earlier also. This much I have written earlier also. I have concluded that the system is unstable. But what I was not knowing is, are there any j omega roots? Are there LHP roots? That is what I was not knowing. Na? So to get the clarity of j omega roots, I have got auxiliary equation. Currently, I solved the auxiliary equation. For any future question, you don't have to solve the auxiliary equation. You don't have to solve it. Okay, so what you are going to do is, okay, for auxiliary equation, remember, number of LHP and RHP roots are always equal because of symmetry. And then those RHP roots are equal to, number of sign changes below AE. So look into this. In this part, how many sign change? Again, one sign change in this part. Again, one sign change. So how many L and R? Only one L and only one R. That one each. So how many on the j omega? J omega can only occur because of auxiliary equation. I told you earlier also. And how many J omega? 4. Total order 4. One goes to the left, one goes to the right. Whatever is left is on J omega. Whatever is left on the J omega, and you just have to copy this value here. Because J omega can only come because of A, na? So you copy the information there. Copy the information here. How many on J omega? 2. Now you get the LHP roots of the characteristic equation. 6. 1 on the right, 2 on the J omega. Total 3 roots of the characteristic equation will be in the LHP. This is the analysis you have to do. Okay. Correct, na? 1 on the left, 1 on the right, 2 on the J omega. This is the shortcut. This is the shortcut. I have proved the same thing. I have proved the same thing. 1 on the left, 1 on the right, 2 on the J omega. I have proved you the same thing, na? But for the question, you don't have to solve it. I have solved it for the clarity, but you don't have to solve this way. Every time auxiliary equation may not be solvable also. It may be a lengthy or complicated case. You don't spend time on solving whether it is easy or lengthy equation. You use this point only and get your answer. As simple as that. Get your answer as simple as that. Most important case of Routh-Hurwitz, and please handle with this shortcuts. It will be very easy. Okay, it will be very easy. Okay. The next question for you in the MSQ format. Please answer me. A next question for you in the MSQ format. The characteristic equation of a system is given to me. S power 6 plus S power 5 plus S power 4 plus 4S square plus 4S plus 4 equal to the 0. The number of poles in the left half of the S plane are 4. The number of poles in right half is left half is this much. So there are 4 options. Which of them is correct? So let me start feeding to the Routh array. Let me start feeding to the Routh array. The first 2 rows starting from S power 6. The first 2 rows to be starting from S power 6 and S power 5. S power 6, S power 5. Alternate coefficients are 1, 1. Oh, very careful in this question. Dear, very careful in this question. This is okay. S power 6, S power 4, S square. This is alternate. This is not alternate. Alternate means even power. S power 6, S power 4, S square, and then the constant term. So 1, 1, 4, 4. 1 and 4 and 4. S power 5. S power 5, 1. There is no S cube term. So 0. Okay, then S. Okay, so 1, 0, 4. 1, 0, 4. Are you getting it? Okay. There is no S cube term. There is no S cube term. So that means I have taken it as 0 into S cube. Clear? I have taken it as 0 into S cube. The coefficient is 0. Now keep solving the Routh array. So S power 4, 1 minus 0. Okay, this is 1 minus 0, 1 by 1. Then this is 4 minus 4, 0. And then 1 into 4 by 1. So that is 4 and 0. Now S cube row. Okay. 0. 4 minus 4, again 0. 0 because the column to the next is 0. Last element always 0. Okay, once again what have you got? Once again what have you got? You have got a ROC. And for every ROC what will you do? For every ROC what will you do? You will form the characteristic equation. Auxiliary equation. For every ROC what will you do? You will form an auxiliary equation. What is that auxiliary equation? Okay, S power 4. Okay, 1 into S power 4, and then there is no S square term. 0 into S square, and then 4 into S power 0. That is how you will write. Na? That means your auxiliary equation is S power 4 plus 4 equal to 0. Next step is differentiate. Okay, differentiate. So 4S cube equal to the 0. 4S cube equal to the 0. Okay, so then you have a modified S power 3 row. What is that modified S power 3 row? The modified S power 3 row will have the coefficient of S power 3, 4. Rest all zeros. Rest all will be zeros. Clear? Rest all will be zeros. Now continue with the Routh array in the regular procedure. So now S square row. Okay, so 4 into 0 minus 0. Okay, again a 0 coming up. Then 4 into 4 divide by 4. So this is 4. Okay, this will be 0 because the column to the top is 0 and the last element always 0. So now this is a mixture of 2 cases. This is a mixture of 2 cases. This is not a row of 0. Only first element 0. So what is the method I have told you? Only when the first element is 0 replace that first 0 element by some small variable epsilon. And now I will solve the Routh array. S power 1 row, epsilon into 0, that is 0, minus 16 by epsilon. Okay, last element is, let's see, anyways this is going to be 0 because top column 0, again top column 0, last element always 0. S power 0, last row, minus 16 by epsilon into 4 upon minus 16 by epsilon, so only 4. Next will be zeros. Now minus 16, here in simple case, now epsilon comes because of 0, the epsilon tending to 0, this will be minus infinity. Okay, this will be minus infinity. Now I'm just going to write down the answer by my table. Okay, by my table, direct shortcut answer. So what do I do in the shortcut? In one side I will write down auxiliary equation, on one side I will write down the characteristic equation. Okay, then I will write down the order for both the equation. What is the order of auxiliary equation? 4th. What is the order of the characteristic equation? 6th order given. Okay, 6th order given. Clear? 6th order given. Then for auxiliary equation, the number of L and R roots are equal to sign changes below the auxiliary equation. Equal to the sign changes below. Okay, so in this much of the portion, how many sign changes, dear? In this much of the portion, how many sign changes? Okay, so see, 1 plus epsilon 0 plus. Okay, so plus 2 minus and minus 2 plus 2 sign changes. 2 in this much of the portion also 2 sign changes. Okay, so ln r equal to 2. Ln r equal to 2 means how many on j omega? It's a 4th order auxiliary equation. 2 goes to the left, 2 goes to the right. So is there anything left for j omega? Nothing. So how many j omega roots? 0. Then I come to the characteristic equation. The sequence is for characteristic equation, first you will write down r, then you will write down j omega, then you will write down L. How do you write down r of characteristic equation? By the Routh array. So number of sign changes in the entire first column, that also is 2. Here only sign changes occurred. So in the entire first column also how many sign changes? 2. J omega you have to copy from this left side. So how many j omega? Nothing. So how many on the L? 6 minus 2 plus 0. So 4 roots on the LHP. 4 roots on the LHP. Now this completes our MSQ question also. The number of poles in the LHP is 4. Yes, very correct. So the B option goes wrong. Number of poles in the RHP 2. Very correct. Number of poles on imaginary axis 0. Very correct. ACD. ACD. Nathan, ACD, not ABD. Just check it out once. So ACD is the very correct answer for this particular MSQ question. So they can make this MSQ question also from here, asking you everything, the L and the R and the j omega roots. You know, now if you actually go to detail, not required for this question, but if you actually go to the detail, if you go to the details and take the auxiliary equation s power 4 plus 4 equal to 0, you solve it, not required, just I'm telling you for additional knowledge. Okay, if you solve, okay, what do you get? You will be getting S in the format plus minus X plus minus JY. It's not going to be complicated also. You try to solve it, you'll get plus minus X plus minus JY. Okay. Once you solve it, see, I have got a shortcut, so we are not solving the auxiliary equation. But once you solve it, you are going to get this quadrature of the poles. And that is why our table also says 2 on the left, 2 on the right. Our table also says the same things, 2 on the left, 2 on the right. Correct. But we know it from the shortcut. So no need to solve the auxiliary equation. Don't spend a single minute on solving the auxiliary equation. Just follow this tabular shortcut. Okay, the shortcut made out of the auxiliary equation. Very, 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 very important. Okay. Next type of question expected from the Routh-Hurwitz. Next type of question expected from the Routh-Hurwitz. Again made it as a MS2 question. Okay. The frequency of oscillation. With several parts I will cover here. Okay. Right. What is there to be checked for S square rho? Okay, so you know the system oscillate. What is the frequency of oscillation if the system is oscillatory? Okay, S square rho, what you are telling? S square, 0, correct? Correct only, na? See, Sajin, when you are forming S square, these are the two rows. Be careful, S power 3 and S power 4. Don't use this because this is already replaced, na? Okay, so you know if you use these two, it's correct only, I think. Okay, dear? So coming back to this question, right? So, you know, next category and next important question from RH is about the frequency of oscillation. Okay, but the frequency of oscillation will come when the system is oscillatory, pure oscillatory, and system is oscillatory means marginally stable condition. Okay, so let me keep solving for it. It's a fourth order equation. Let me form the Routh array before I place any conclusions here. Let me form the Routh array starting with the first two rows, s power 4, s power 3. S power 4, 1 and 15 and k. 1 and 15 and k. And then 20 and 2. The alternate coefficients are only 20 and 2 and 0, correct? Yeah. Now let me keep solving the Routh array first. S square. Okay. 20 into 15, 300 minus 2, 298 by 20, 14.9. 20 into k minus 0. So 20 into k by 20, again k, and last element 0. S power 1, 14.9 into 2, that is 29.8 minus 20k. Divide by 14.9. This is 0 because the column on the top is 0, last element always 0. Coming to s power 0 now, say this is x, x into k minus 0. So x into k by x, only k. This is again 0 because column is 0, last element always 0. My Routh array is finished. Okay, na? My Routh array is finished. Now, for what value of k system stable or unstable or oscillatory means marginally stable? For that, first let me give you the general conclusion. See, if you want the system to be stable, okay, for pure stability, what do you want? If there is a RHP root, system cannot be stable, system is unstable. That means no RHP roots. That means no sign changes in the first column. No sign changes in the first column. That is the first condition you want. But I am telling pure stability. Okay, so pure stability, the system should not have ROZ also. Why? Because if there is a ROZ, what are the three cases of ROZ? If there is the ROZ, there will be auxiliary equation. So auxiliary equation roots, three cases I told you, no? RHP roots unstable, but at least a j omega root, so marginally stable. So dear, one more point to be noted. When there is a row of 0, there will be auxiliary equation and the system will never be purely stable. The system may be unstable if case 2 or 3 comes, or best to best case system will be marginally stable. System cannot be purely stable. System cannot be purely stable if there is a ROZ coming up. So if you want stability, there should not be ROZ also. Okay, so keeping this in mind, what will I say? This is plus, no sign change. So rest all should be plus. Okay, so k should be also positive. K should also be positive, and this element, okay, which is 29.8 minus 20k upon 14.9. So 14.9 anyway is positive, the numerator also positive, and this will give you k less than 1.49. Okay, so for stability, k positive and less than 1.49. So 0 less than k less than 1.49. See, this is also a question. This is also a separate question. Tell me the range of k for stability. That is a separate question. Okay, commonly asked from here. Okay, what is the range of k for the system to be stable? What is the range of k for stability? This is the range of k for stability, correct? This is what is the range of k for stability. You can note down. What is the range of k for stability? Here it is. Range of k for stability, here it is, correct? Okay, so that means option number A is correct. System is stable for k equal to 1. Any value up to 1.49, system is stable. Okay, so of course, if k greater than 1.49, sign changes will occur. What will happen? Reverse. If k is greater than 1.49, then the coefficient 29.8 minus 20k will be negative. Okay, then that will give you two sign changes. Okay, if this becomes negative, so plus, minus and plus. Okay, two sign changes will occur. Okay, so the system will be unstable. The system will be unstable for k greater than 1.49. Okay, and it will be unstable with two RHP roots. Clear? The system is unstable for k greater than 1.49. So k equal to 1.25, system is unstable? No. 1.25 means below 1.49 also. So B is wrong at least. Now what is the cutoff? What is the boundary? It means, Okay, what is the boundary? The boundary between stability and instability is marginally stable case. So for k equal to 1.49, the system is marginally stable. For k equal to the 1.49, system is marginally stable. Okay, marginally stable. Correct. Now if the system is marginally stable, what to be done? Okay, marginally stable. So what you are going to get? See the s power 1 row. See the s power 1 row. You will have 0, 0, 0. So always for marginally stable, row of 0 will come, because marginally stable means j omega roots. J omega roots can only come because of auxiliary equation. Auxiliary equation can only come when there is a ROC. So see, s power 1 row becomes 0. S power 1 row becomes 0. So what is that auxiliary equation? Acha, if the system is marginally stable, means the system is oscillatory. Okay, system is oscillatory, correct? So if the system is oscillatory, they can ask you, na, what is the frequency of oscillations? What is the frequency of oscillation? So if the system is marginally stable, we know one more thing. If the system is marginally stable, okay, what are the poles or what are the roots of characteristic equation? What are the roots of characteristic equation? Pure imaginary, plus minus j omega n. This omega n is what is the frequency of oscillation. Na? So you need the poles. If you get the poles, plus minus j omega n is the frequency. Okay, now for obtaining, we have to solve the auxiliary equation. What is the auxiliary equation, dear? So if this becomes a row of 0, auxiliary equation will come from the row above the row of 0. That is 14.9 s square plus k. Okay. 14.9 s square plus k equal to 0. 14.9. Okay, I know the value of k also. So 14.9 s square plus k is 1.49, because system is marginally stable for k equal to 1.49. Okay, for k equal to 1.49. That means D is also wrong. Marginally stable for k equal to 1.49, right? Okay, so this is equal to 0. So s square is becoming minus 1.49 is divided by 14.9, and that becomes minus 1 by 10. S square is becoming minus 1 by 10. Okay, so when you solve it, s equal to plus minus j under root of negative number, and you will get 1 upon root over 1 by 10. Yes, so 0.316. Okay, that means what is the frequency of oscillation? You can call it as 1 by root 10 also, or on solving, if it is NAT question, it will be 0.316. Correct. So that means what option is correct? C option is correct. For k equal to 1.49, system is oscillatory. Correct. Oscillating at omega equal to 1 by root 10. Yes, the complete statement itself is correct. Okay. So see, I have made it as MSQ question. There are different parts that you can make from this question. What is the range of k for stability? Okay. Or what is the value of k for which the system is marginally stable or oscillatory? Or the next question, if the system is oscillatory, what is the frequency of oscillation? So for that, you have to solve auxiliary equation. Okay. For finding the frequency, you have to solve the auxiliary equation. Auxiliary equation means the equation using above the row of zeros. Whether using the equation above the row of zeros. Okay. Hi Murli. All right. Just connect me in the Telegram once, Shri Hari. We can have a more detailed discussion right now. Otherwise, the flow of the topics will be lost. All right. So, yes, guys, enthusiasm to learn more. Okay. The transient part, steady state part, Routh-Hurwitz parts is done, but do you have the enthusiasm to learn more? I want to teach more. Okay, tell me you have the enthusiasm to learn more. Just tell me you have the enthusiasm to learn more. And guys, a quick update that for GATE 2026 and 27, the online live courses. Okay, the online live courses will start from 8th of February 2025. Okay, the fee for 1 year, that is 2026, will be 99.99, for 2 years 28.999. But if you register till 30th of Jan, 25% additional discount you can obtain here. Okay, you just have to use the coupon code OMGATE26. Right? Yes. Yes, do you have the energy to learn more? Tell me. Tell me. Yes. Okay. Good. So what I will do is, if you want to learn more, what I will do, dear, we'll go for a quick break. Okay, let me also have some refreshment so that, we'll keep, continuing. That is what, see, Ramesh, the condition that we derive, na, the system is stable for k between 0 to 1.49. That is what is a conditionally stable system. The system is stable for some conditions of k. Okay, that is what conditionally stable system is. Okay, clear? So let's go for a quick break. You also have refreshment. Okay, because if I'm continuing, I'll continue for some more time, not like 10 minutes or 30 minutes only. Okay. Probably, according to me, I want to pick up the next topic as Nyquist plot, but you can also let me know in the comment box what is the next topic you want. Okay, I'm preferring Nyquist plot because that is the important one. Okay, but you can also let me know, right, what topic you are exactly willing more right now. Okay, so we'll go for a, small lunch break. Okay, the session will be live only, guys. You have to join in the same session. Okay, for approx 20 minutes. Not more, guys. Quick refreshment. We cannot delay beyond it. Okay, we cannot delay beyond it. Okay. Okay, we cannot delay beyond it. So let's go for a lunch break for roughly 20 minutes, and we are going to resume at, it's 1:55, approx 2:15 p.m. We will resume at 2:15 p.m. Okay, we'll resume from 2:15 p.m. Take this as a 20 minutes timer for you. Take this as a 20 minutes timer for you. Okay, dear? Take this as a 20 minutes timer for you. I am going to start roughly in after 20 minutes. You also have the refreshment. Okay, let's keep on going. Okay, we'll see you soon. Okay guys, so let's resume. It's 2:20 almost. Let's continue now. Let's continue once again now. Yes, are you all done with your lunch? Yes guys, so students not back till now. Just waiting for the students to join. Students, it seems, not back till now. Yes, let everybody continue quickly. Okay. Chalo, so let's start by the time others will keep joining. Okay. Okay. Yeah, Telegram. Chalo, so let's start by the time others will keep. So Telegram link was already shared. Get the Telegram link now. Where is that? Yes, I'll reshare it, but Telegram link I shared it for going to the break only. Popa, you can continue with the mega marathon right now, and yeah, how to utilize those videos, I'll tell you that. Okay. Chalo. Okay, fine, guys. Let us get started now. Okay, let us get started. Meanwhile, others will keep joining. So, as for most of your response, I think we should first go with the Nyquist plot and the polar plot discussions, and then we'll see what is the next topic you demand. Okay, what is the next topic you demand? But yeah, I think where the students are lost. Okay, joining slowly. Chalo. So first of all, see, the understanding of Nyquist will be clear if you are quick in sketching the polar plot. So first, let us talk about sketching right now. How do you quickly sketch polar plots? How do you quickly sketch Nyquist plots? Okay, and then how do you do the stability analysis using the Nyquist plot? But before that, let's talk about the sketching activity. How can you do the sketching completely and quickly? Okay, so first of all, directly starting with the shortcut procedure for sketching the polar plot. So given GSHS, open loop transfer function, okay, as k 1 plus st1 1 plus st2 some zeros term divided by s power n, okay, 1 plus sta 1 plus stb and etc. Okay, right. So say if this is the GSHS given to you, so GSHS, as we know, GSHS is known as open loop transfer function. Just wait, I think there is some issue right now. Okay, no problem, Nitin. We'll take it later, root locus. Right now, since I've started polar plot, let me continue with that. Yeah. So some open loop transfer function has been given to me. I will keep defining a quantity, and let's say P, okay, is the total number of open loop poles. Okay, so P here means the total number of open loop poles. Okay, let Z be the total number of open loop zeros. Okay, let Z be the total number of open loop zeros. Okay, and then specifically this N, total number of open loop poles counts the poles at origin also, but specially write down what is N. N is the number of poles, number of open loop poles at origin. Number of open loop poles at origin. Clear? The number of open loop poles at origin. Okay. Okay, Vikram. So once we go to root locus, you can raise it out once again. Chalo, so now what is the quick sketch, quick procedure for sketching the polar plots? See, normally for polar plots, given any GSHS expression, we are majorly interested in the angle GSHS. So if you convert to GJ omega HJ omega, okay. If you convert to GJ omega HJ omega, the function will look like K 1 plus J omega T1, 1 plus J omega T2, etc. whole divided by J omega power of N 1 plus J omega Ta and etc, etc, etc. So what is the angle expression? Okay, what is the angle expression? Okay, the phase expression or the angle GJ omega HJ omega. The phase expression or the angle GJ omega HJ omega. So K is a positive real number, zero phase, but for x plus Jy, phase can be written as tan inverse Y by X. So, for every 1 plus J omega T, phase is coming as tan inverse omega T1, tan inverse omega T2 and etc, etc, etc. Then for denominator, we know we subtract the phase. Okay, J omega is a pure imaginary term. The phase is 90 degrees. So minus 90 degree into N, because N factors are there. Then there will be a term, okay, minus tan inverse omega Ta and etc, etc, etc. Minus tan inverse omega Ta, tan inverse omega Tb, etc, etc, etc. Now, let us directly work out on the starting and the diving phase. Let us work out on the starting and the diving phase. Okay, so let me write down a formula here, okay, which will be represented as theta st. Which will be represented as theta st. That means the value of the angle Gj omega Hj omega, the value of the phase angle Gj omega Hj omega at the starting frequency omega equal to 0. So when you put down the omega equal to 0, what you are going to get? Okay, all tan inverse 0 term will be 0. The only expression that is left is minus 90 degree into N. With a precaution, I will tell you. First, let me write down the normal formulas. Okay, so what is the theta st is minus 90 degree into N. Then we define another angle, that is theta d. Okay, that is angle Gj omega. It's like closing angle. Angle Gj omega Hj omega. Okay, at omega equal to infinity. Now d here means diving. See, this is known as starting angle. Only mostly by these 2 points you can complete. If there is some clarification required, I will use the complete angle formula. But mostly, most of the problems, starting and diving angle will be sufficient. Okay, diving angle theta d is the angle at omega equal to infinity, and that once you simplify all the terms, what you are going to get is minus 90 degree into P minus Z. P is the total number of poles and Z is the total number of 0, because for every 0, you will get plus 90, tan inverse infinity. For every pole, you will keep getting minus 90 degree. So minus 90 degree into P minus Z is the diving angle. These are the 2 points to be remembered first of all. Why do I say diving angle? Where do I dive? I will explain you with an example. Okay, so normally, okay, you have to start with this procedure. I'll repeat. Minus 90 degree into N and theta d will be minus 90 degree into P minus Z with some precautions. Okay, with some precautions. But before I tell you the precautions, let me first go ahead and tell you, one example based out of this. Okay, how I'm going to use this. See, sketch the polar plot for GSHS equal to 1 upon S 1 plus ST. Now that is what I want, that every time you should not write down the phase expression. Every time, do not try to write down the phase expression. Okay, do not try to write down the phase expression. Let me just start. How many poles and how many zeros are there? Okay, how many poles? So N is what? Number of poles at origin is 1. How many total number of poles is 2? How many total number of poles is 2? And how many total number of zeros is nil? Okay, so this is the data I have. So what is the starting angle for this case? Okay, what is the starting angle for this case? The starting angle will become minus 90 degree into N. Minus 90 degree into 1 is minus 90 degree. Okay, P equal to 2. Okay, P equal to 2, Z equal to 0. So what is the diving angle? Out of these two, what is the diving angle? Diving angle is given by the formula minus 90 degree into P minus Z, and that is minus 180 degree. Now what is minus 90 degree? Okay, minus 90 degree means negative y-axis, and minus 180 degree means negative x-axis. Any problem in the axis, please let me know. Okay, because minus means clockwise angle. When I say minus 90, okay, so when I go 90 degree but in the clockwise direction, I reach negative y-axis, but 180 in the clockwise direction, when I take 180 degree, I reach the negative x-axis. Clear, na? That means by diving angle is minus 180, my starting angle is minus 90. Now, if I have to draw the polar plot for this, okay, I'll draw it simply here only. If I am required to draw the polar plot for this, see, I told you theta d means diving. Now, why it is diving? Understand with this example. Why it is diving? Because when you calculate the magnitude at infinity, when you calculate infinity, okay, so omega equal to infinity means s equal to also infinity, and if you put s infinity here, 1 upon infinity, how much magnitude? 1 upon infinity, how much magnitude? 0. So basically, at omega equal to infinity, you are getting the magnitude equal to 0. And that means magnitude equal to 0 for which point? Origin. That means you are going to dive into origin. So let me start by the diving actually. Okay, at omega equal to infinity d. What is d here? What is d here? Let me be specific. D here, diving. Diving means dive into origin. Diving means what? Dive into the origin. So you are just going to dive into the origin. You are going to touch the origin. But at what angle? So when you dive into the origin, what is the angle? Minus 180 degree. That means, okay, you can come to origin from anywhere. From anywhere you can come to the origin. Okay, but the point is when you come to the origin, your angle should be minus 180. That means along negative x-axis. When you are going to come to the origin, you should be coming along negative x-axis. When you come to the origin, you should be coming along negative x-axis. Okay, you should be coming along negative x-axis. Now, there are also two conditions here. Negative x-axis, this is negative x-axis. Whether you are coming from this side or this side. Okay, second quadrant or third quadrant. That also leads to a question. Okay, you are going to touch the origin, dive into the origin, either second or third quadrant. Okay, so for that, I will now see the starting angle from where the polar plot will start. Minus 90 degree, that is negative y-axis. Minus 90 degree means negative y-axis. So polar plot is starting along negative y-axis. That means you are coming from down, and hence, okay, third quadrant case. Approximately, just come and join like this. Approximately, this is what is my starting. It starts parallel to the negative y-axis and it dives into the origin. Okay, this will be represented as my infinity point or infinity plus, to be specific. Frequency is positive and we call it as 0 plus, and I join the arrows from 0 to infinity. Okay, there will also be the cases where the polar plot can change quadrant. This polar plot is entirely in the third quadrant. Can it also change the quadrant? I will tell you what is the possibility when the polar plot can change the quadrant, lying in the multiple quadrant. Okay, now as I told you, if omega is infinity and if n equal to 0, now see, both the cases you understand. Once again. Okay, so what I am going to do, I am going to convert this to the gj omega hj omega first. Understand? Normally for the question, or better let me not write it here. Normally for the question, for the upcoming question, the angle part itself will be sufficient to write down. But okay, to explain you this part, what I will do is understand what is gj omega hj omega magnitude. Understand what is the mod gj omega hj omega. So 1 upon j omega, okay, magnitude of j omega is omega. Next term is 1 plus j omega t. So magnitude is root over x square plus y square for a complex number. So I will get root over 1 plus omega square t square. Clear? So dear, when omega is 0, very clearly the magnitude 1 upon 0 tends to infinity. That is why my polar plot will be starting somewhere from infinite, but parallel to the negative y-axis. Okay, parallel to the negative y-axis, somewhere from infinite. If I take omega equal to infinity, okay, so I told you already 1 upon 0, magnitude will be tending to 0 and 0 means origin. 0 means origin. So at omega equal to infinity, you dive into the origin. That is why I have used the name theta d. Rather than theta ending, I call it as theta d, known as the diving angle. Okay. As of now, before going to the next question. As of now, I have shown you two formulas, starting and diving, but with precautions. Now let me tell you the precautions. Okay, what are the key points to be noted? Okay, while using these formula, what are the important key points? Okay, number one, like in our question, n not equal to 0. If n not equal to 0, what will happen? N means number of poles at origin. Keep understanding. Like here, n equal to 1 not equal to 0. That means poles at origin. When you convert to the gj omega frequency domain function, you get 1 upon omega term. And if omega equal to 0, starting 1 upon 0, infinity. The starting will always be from infinity. The first key point is, if n not equal to 0, polar plot starts from infinity. But which infinity? Okay, this is also infinity, anywhere from large distance I can come, everything is infinity. Okay, so polar plot starts from infinity. So from which direction you will start? Okay, for that only I have given you the starting angle. Whatever the starting angle, that you can come parallel to that axis, minus 90 degree into n. Clear? But if n equal to 0, no poles at origin. See in this function, if there are no poles at origin, if I remove this particular term, poles at origin, then at omega equal to 0, what do you get? At omega equal to 0, k into 1 into 1 upon 1 into 1 into 1, only k. That means some finite non-zero number is obtained. Correct? Finite non-zero number is obtained. So that means, what can I say now? Okay, if n not equal to 0, polar plot starts with finite magnitude. Okay, finite magnitude with how much theta st? n0 to theta st 0, that is 0 degree. Positive real axis. 0 degree means positive real axis. Positive x-axis or positive real axis. Okay, so for n equal to 0, your polar plot will start from a finite magnitude. I will take that question also. Okay, this is the first key point to be noted. Second key point. See, what is the type of function I have taken? All terms are 1 plus st. So when you calculate any pole or 0, it is minus 1 by t. That means negative real axis or negative side. Okay, all the poles and zeros are in LHP. And when all the poles and zeros are in LHP, such a system is a minimum phase system. So these techniques is for a minimum phase transfer function. Okay, what happens if there are poles and zeros? What is minimum phase? Everybody know, I think. Okay, when all the poles and zeros lie in the left half plane, such a transfer function is a minimum phase transfer function. So second key point I am telling, if there are zeros or poles in the RHP, we will take appropriate question also. If there are zeros or pole in the RHP, then there will be slight changes in the formula. Okay, there will be slight change in the formula. What will not change is the diving formula. There is no change in the theta d. Okay, the diving angle will be same. Okay, what will change is the starting angle. Theta st will be minus 90 degree into n. This was the original formula. Minus 90 degree into n. Okay, plus of 180 degree. For 1 0 in RHP. Similarly, if there are multiple zeros in RHP, for every RHP 0, plus 180 will keep happening. Okay, and theta st similarly minus 90 degree into n minus of 180 degree. Okay, for one pole in RHP. Clear? For one pole in the RHP. So theta st will change. Plus 180 for 0, minus 180 for pole in the RHP. Okay, rest minus 90 degree into n is same. But theta d will still remain to be the same. Okay, theta d will still remain to be same. And the third key point is, okay, if the total number of poles are less than equal to number of zeros, which usually, okay, is not given in the questions, but yeah, if we should know this also, if total number of poles less than equal to number of zeros, okay, or if zeros are more, okay, okay, so that means there will not be any diving. Remember, there is no diving into the origin. There is no diving into the origin. So polar plot, remember, there is no diving into the origin. So polar plot terminate also at infinity. Maybe starting also infinity, maybe termination also at infinity. Clear? So if zeros are more, okay, so a polar plot also may start from a, will end on a finite magnitude or an infinite magnitude. Okay, that's what I told you. See, firstly, if number of poles are more than the number of zeros. Okay. Diving into origin will happen. Diving into origin will happen. Okay, but if number of poles equal to number of zeros, okay, I am talking about infinity, the final result, omega equal to infinity. Okay, you will have finite magnitude. Diving into origin means zero magnitude. Okay, the polar plot terminates with a finite magnitude, and if the number of poles are less than number of zeros, number of zeros more, numerator having more degree, so that means infinite is more in the numerator. So there will be infinite magnitude even in the termination also. Okay. Now let's go to the next question and keep telling me if there are any doubts. This was 1 upon s 1 plus st. Now I am going to try for 1 upon s square 1 plus st. Do it quickly. Just little info. See, mathematically non-minimum phase means, mathematically, then I'll tell you the correct definition. Non-minimum phase means if any pole or zero is in RHP. See, what I first told you, all poles and zeros in LHP, all poles and zeros in LHP is minimum phase. But if any pole or zero in RHP, it can be non-minimum phase. But practically, if pole is in RHP, system is unstable. Okay, so we want to ensure stability of the system, and that is why we give the definition like that. Okay, if some zeros are in RHP but poles in LHP is non-minimum phase. Got it? But mathematically, if any pole or zero in RHP is a non-minimum phase system. Okay, with respect to phase calculations, if I say. Okay, but yeah, what you are telling is correct in a sense, because normally we define it this way because we want to make the system stable. Okay, so the poles in LHP and if some zeros in RHP, non-minimum phase. One more case, poles in LHP and all zeros in RHP, all in RHP, that is maximum phase. That is maximum phase. Chalo. Next question. Sketch the polar plot for GSHS equal to 1 upon s square 1 plus st. So see what is the condition. See what are the conditions. First of all, if I start with the value of n is equal to 2, okay, not equal to 0. That means my polar plot starts from, n is not equal to 0. The polar plot starts from where? The polar plot starts from infinity. Okay, polar plot starts from infinity. Okay, so what direction? With the starting angle as minus 90 degree into n. Okay, minus 90 degree into 2, minus 180 degree, that is negative real axis. That is negative real axis. That is known as negative real axis. N is not equal to 0, so negative real axis. Clear, everybody? Negative real axis. Clear? Okay, then, okay, the number of poles is 3 total, 2 at origin and 1 on negative real axis. Total poles 3. There are no zeros. Okay, there are no zeros. So what about the diving angle? Theta d minus 90 degree into p minus z. So that is minus 270 degree. And minus 270 degree means minus 270 degree will actually be positive y-axis. Right now, positive y-axis. Minus means clockwise. So how much clockwise? 90, 90, 90, 270 you reach here. This is 270, na? Okay, minus 270 because of clockwise. Clear? Any still doubts in the axis you can ask me. So how a polar plot should look like? Let me always draw it from the diving. Let me always start the, let me always start it from diving. Okay, let me take this slide here. Let me start it from here. Let me start from the diving. Okay. See. So if I start from diving, where does it dive? Okay, it dives along, it dives into the origin, but along positive y-axis. Along positive y-axis. Okay, it dives into the origin. Okay, but there can be multiple ways of coming to the origin, but you have to come along positive y-axis. But again, whether it is the second quadrant or the first quadrant, it has to be the second. Why? Why it has to be the second? Because the starting is along negative real axis. You see the starting is from backside. Okay, so somewhere negative x-axis or parallel to negative x-axis, the polar plot will start. Starting is from infinite magnitude, as I mentioned, n not equal to 0. Okay, so this will be your point 0. Okay, and you dive into the origin for infinite frequency. Okay, along positive y-axis. This should like be, you are coming tangential to the positive y-axis. Clear? Okay, tangential to the positive y-axis. Clear? Okay, any doubts, keep asking me. Now that means there is a transformation in the polar plot. This is one point. Okay, there is a transformation in the polar plot. See here, if I draw the previous polar plot, if I just draw the previous polar plot. Okay, what was my previous polar plot? 1 upon s 1 plus st function. Clear? 1 upon s 1 plus st function. Now 1 upon s square, what is this function right now? Is 1 upon s square 1 plus st function. 1 upon s square 1 plus st function. Clear? 1 upon s square 1 plus st function. So what happened to the polar plot? You see, this was my starting. My starting, which was positive. Let me just copy this diagram here again. My starting, which was along negative y-axis, goes to negative x-axis, 90 degree change. My diving, which was along negative x-axis, now the diving is along positive y-axis. That is also 90 degree transformation. That in a way means that all the points are 90 degree transformed in the clockwise direction. Okay, and this has happened because of what? This has happened because of pole at origin. 1 upon s 1 plus st, 1 upon s square 1 plus st. A pole at origin has been added. A pole at origin has been added. So let me just show you a conclusion here. Have a look into it first. What is the effect? What is the effect of addition of open loop pole at origin? Okay, what is the effect of addition of open loop pole at origin? Okay, omega equal to 0 plus and infinity plus. Both the points are shifted by 90 degree clockwise. Actually, I will say, see, since we are drawing with 0 and infinity points, I have given the conclusion like that. But actually, okay, you can say that entire polar plot, okay, is 90 degree rotated. Like entire polar plot 90 degree rotated clockwise sense. Okay, that is the effect of pole at origin. Whenever there is a pole at origin, then we will see the next point. So what should be the effect of 0? Reverse. What should be the effect of addition of 0? Okay, 0 plus and infinity plus. Both the points will be shifted by 90 degree anti-clockwise. Again, I will say entire plot. Okay, reverse conclusion. Entire plot 90 degree anti-clockwise rotated this time. Okay, that will be the effect of addition of open loop 0. Now to see the effect of addition of poles and negative real axis, s equal to minus 1 by t. Okay, now let me go to the next question. A very, very important case. Okay, GSHS equal to, consider the numerator as k actually. K upon s 1 plus st1 1 plus st2, and one of the most important case out of which directly indirectly from this type of function lot of questions are built directly indirectly from this function. Okay, so let's try for this one. Okay, k upon s 1 plus st1 1 plus st2. Okay, k upon s 1 plus st1 1 plus st2. Now see here, what is the number of poles at origin n? N is equal to 1, again not equal to 0. Okay, n is not equal to 0 once again. And here, if n is not equal to 0, what will I say? My polar plot starts from infinity. Okay, with how much angle? With the theta st as minus 90 degree into 1, that is minus 90 degree, meaning negative y-axis. Minus 90 degree means negative y-axis. Clear? Yes, Google, that is what is going to come up. Now, what about the number of poles and zeros? The total number of poles becomes 3. 1, 2, 3, and the zeros are still nil. Okay, so what is the diving angle? Minus 90 into 3 minus z, that is minus 270 degree. That means positive y-axis. Minus 270 I have just now explained you, positive y-axis. Positive y-axis. Okay. Type 2 plot. It is coming from negative x-axis only, na? Just little info. This was coming along negative x-axis only. It is like that only. It is coming along negative x-axis only. This is what is negative x-axis, right? Okay. If you want to say this way, if you are seeing this way, this is wrong then. If you say this way, that is wrong. Okay. You can prove it by, expanding the function in the Cartesian form. You may see this in some of the Indian author books, but this is wrong. Okay, wrong. Even for this function, even for this function, what do you see in some Indian author books? You see it like this. This is actually wrong. Okay, this is actually wrong. Okay, even if you draw it this way, it's not affecting the stability, but that shape is actually wrong. Okay, so just little info, if you are trying to specify this particular plot, then that is actually wrong. The correct shape is what I have drawn here. Okay, right. Although for stability results, it won't matter a lot, but that is the correct shape actually. Right. Chalo. So let's draw this particular polar plot now. Let us draw this particular polar plot. So whether it is touching to y-axis or not, that can only be, calculated once you calculate the coordinates at infinity. For that, you have to go to Cartesian form, but not required. I'm talking about quick ways of sketching polar plot. Okay, but the shape that I've drawn is 100% correct. Okay, be sure about that. Yes, along the asymptote, Google, correct. Now you come here. Now you come up here. If you talk about 1 upon k upon s, 1 plus st1, 1 plus st2, what is going to happen here is, okay, 1 upon s, 1 plus st2, 1 plus st, 1 plus st1, 1 plus st2. So, where is the diving? Let's again start with the diving. Minus 90 degree, positive y-axis. Positive y-axis. But again, from where? Positive y-axis, if you are touching, it may be this way or it may be this way. Okay. And then I will see the starting. Starting is minus 90 degree. N equal to 1, not equal to 0. Polar plot starts from infinity. Polar plot starts from infinity. Okay, but with what direction? Negative y-axis. Where is negative y-axis? Downwards. Downwards. Okay, that means you're starting downwards and you want to close upwards. Starting is negative y-axis, diving is positive y-axis. So definitely starting from down, closing at the top, you will have to change the quadrant. You will have to change the quadrant. You know how the polar plot will turn out? Will be something of this kind. Okay, you will have to change the quadrant. Now, first I will define, see, omega c, which is equal to omega p also here. See, first of all, let me define what do I mean by omega c. What do I mean by omega c? Omega c here for me is critical frequency. And then what is omega p? I will define after some time. Okay, I will define it after some time. Okay, what is critical frequency for a polar plot? Critical frequency is the frequency at which the polar plot will change the quadrant. Okay, the frequency at which polar plot will change quadrant. The frequency at which polar plot changes the quadrant. Okay, be watchful here. The frequency at which the polar plot changes the quadrant. Okay, and like here, it changed the quadrant from the third to the second quadrant. And if it is changing quadrant, it is going to cut any axis in between. It is going to cut any axis in between. Okay, that is, it cuts any coordinate axis. It cuts any coordinate axis. Okay, so whenever polar plot intersects any coordinate axis, maybe negative x, positive y, negative y, when it cuts any coordinate axis, that frequency will be critical frequency. Okay, that frequency will be critical frequency. Okay, right. Now, especially when it cuts negative real axis. Okay, then our omega c is equal to omega p. Phase crossover, I will discuss it later. I will talk, because this is used in the, that is actually required for the stability analysis, okay, gain margin analysis. So I will calculate that later. Omega c equal to omega p, leave it, we will do it later. Okay, we'll do that later. When do we need the mirror? Just wait, Sajin. Okay, when do we need the mirror? That is a different story. First, let's complete this. Okay, so the frequency at which polar plot changes quadrant is the critical frequency. Now, how do we obtain the critical frequency? First of all, critical frequency, it is only possible. It is possible for whenever you have two or more tan inverse terms, okay, in the angle Gj omega Hj omega. When you have two or more tan inverse term. Okay, see what happens at 1 upon S1 plus St. This was our first function. Na? What happens at 1 upon S1 plus St? If you write down the phase expression of this, if you write down the phase expression of it, minus 90 degree, minus tan inverse omega t, correct? 90 degree because of the pole at origin, and then 1 plus j omega t, so tan inverse omega t, clear na? So this is having only a single tan inverse term, but when you have multiple tan inverse term, two or more tan inverse term, then you can get the critical frequency. That is why here we did not have any critical frequency, only in a single quadrant. Similarly, next also only in the single quadrant, that is second quadrant. But here, if you write down the angle expression, if I write down the angle expression, so let me take the Gj omega Hj omega here. Let me take up the Gj omega Hj omega and explain you this calculation. If you take up Gj omega Hj omega, it becomes K upon J omega 1 plus J omega T1 1 plus J omega T2. Write down the angle or the phase expression. Phase, that is angle Gj omega Hj omega. The phase, or that is the angle Gj omega Hj omega, is how much? Okay, 1 upon J omega, that is minus 90 degree. Then tan inverse omega T1. Okay, pure imaginary term. Sorry, the complex term, and then again tan inverse omega T2. Correct? Two tan inverse term are there. Okay, now critical frequency is possible when two or more tan inverse term are there. How do you calculate that critical frequency? How do you calculate the critical frequency? So first of all, you will simplify all the tan inverse term. Okay, under one umbrella. So simplify. What is the formula to be used? Tan inverse A plus tan inverse B. Okay, what are the formulas you should know here? Okay, tan inverse A plus tan inverse B is given by, you can combine them as tan inverse A plus B upon 1 minus AB, or if you have tan inverse A minus tan inverse B, so tan inverse of A minus B upon 1 plus AB will happen. Okay, so here I can take minus common and then it will become plus tan inverse A plus tan inverse B identity to be used. So what is my phase expression then? Okay, my angle expression here will be minus 90, and then using tan inverse A plus tan inverse B, tan inverse omega T1 plus omega T2 upon 1 minus AB. Upon 1 minus AB. So 1 minus omega square T1 T2. 1 minus omega square T1 T2, correct? 1 minus omega square T1 T2. That is correct. Okay. Now see, after simplifying the angle expression, see numerator or denominator equal to 0. Now, if you take the numerator equal to 0, to find the critical frequency, start solving numerator equal to 0. But if you take numerator 0, okay, what is the frequency you will get? Omega equal to 0. That cannot be the critical frequency. It is the starting frequency. Where is my critical frequency? My critical frequency is any frequency between the starting to the diving. This was starting 0 plus. This is the diving. Critical frequency somewhere between starting to the diving, where I am changing the quadrant. Okay, so when I take numerator 0, okay, it is not giving me the valid answer. I will try with denominator. Denominator equal to 0. So denominator equal to 0 is giving me 1 minus omega square T1 T2 equal to 0. So solving it, omega C 1 upon root T1 T2. 1 upon root T1 T2. Okay, now because you have taken denominator 0, how much will be the angle? See that angle also. Denominator 0, so 1 upon 0, infinity, tan inverse infinity. Tan inverse infinity, 90. So minus 90, minus 90, minus 180 degrees. So where is your critical frequency? As I've already shown in the plot, where is the critical frequency? It should be minus 180 degree. Okay, where is the critical frequency? It should be minus 180 degree. That means negative real axis. That means negative real axis as we have shown here. And what is this omega c? Okay, what is the omega c here? 1 upon of root T1 T2. 1 upon root T1 T2. Okay, 1 upon of root T1 T2. Correct. Geometric mean of poles you can say here for this case. Okay, so omega c here is 1 upon root T1 T2. Then next, we can also calculate the magnitude, the distance of this point from origin. You know, I'll write down this one separately. How much is this distance? Okay, at omega c, once you calculate, I'm writing it directly, you will get the answer Kt1 T2 upon T1 plus T2. Kt1 T2 upon T1 plus T2. Okay, Kt1 T2 upon T1 plus T2. All this will be required for some upcoming discussion. Okay, this is the polar plot. So to summarize, whenever there are two or more tan inverse term in the angle expression, critical frequency is possible. To obtain the critical frequency, simplify the tan inverse terms. Bring a single tan inverse term and then try numerator or denominator equal to 0. From that you can obtain the critical frequency. From there you can obtain the critical frequency. Okay, now dear, do you have to remember these polar plots? No, you can. That's why I'm telling you techniques, the starting angle, diving angle, so that you don't have to remember any polar plot. But as a suggestion, as a tip, only one particular polar plot, if you remember, it will be beneficial in the exam. You know, there are multiple questions that are discussed around this format. What is the format? K upon S 1 plus ST1 1 plus ST2. K upon S 1 plus ST1 1 plus ST2. Correct. So this one is important. If you remember the shape with these details I have mentioned. Okay, let me also draw the arrows. This was 0 plus. Okay, going towards infinity plus. Okay, this is what function? This is the function K upon S 1 plus ST1 1 plus ST2. Correct. Okay, now we had another case. Let me bring that case once again. Okay, this is one of the case we have seen earlier. Okay, and what case it was? This is the case 1 upon S 1 plus ST. Now compare the two functions first of all. If I compare the two functions first of all, what is going to happen? Yeah, if I compare the two functions, what is going to happen? See, a pole at origin, a pole on negative real axis. This has one more pole on the negative real axis. The two poles are similar. Okay, but one more pole on the negative real axis. So if you compare the functions, there is a pole on the negative real axis minus 1 by t. And if you compare the polar plot, see, the starting is same, 0 plus negative y axis. Okay, but diving has changed. Diving here was along negative x axis. Okay, now it is transformed 90 degree clockwise. The only diving is changed, transformed 90 degree clockwise, and the polar plot is diving along positive y axis now. Okay, so if I come back to the set of conclusions, I already told you what is the effect of pole at origin. Now addition of open loop pole on the negative real axis. Minus 1 by t means negative real axis pole. What is the effect of addition of pole on the negative real axis? Only infinity point. Okay, that is diving. Okay, shifted by 90 degree clockwise. Okay, but starting in the same direction. No change in the starting. No change in the starting. So if I talk about addition of 0. Okay, the reverse. Infinity plus will be affected by 90 degree anti-clockwise. What is affected? Infinity. 0 plus is in the same direction. Okay, so these are also some of the effects you must know. What happens when poles are added on the origin and on the negative real axis? What happens to the polar plot actually? What happens to the polar plot? Okay. And this one is an important polar plot. We'll come back and do some discussion. I'm telling you this is omega c. Later on we'll call it as omega p. Okay. Later on we'll call it as omega p to talk about gain margin and all. Okay. All right. Good to know that, Google. Now next. Try for this function. Polar plot 1 upon s plus 1 s plus 2. 1 upon s plus 1 s plus 2. Then quickly let's do some examples and then we'll come to complete Nyquist plot. This is only polar plot portion. This is only the polar plots portion. Okay. So what is happening here? N equal to 0. N equal to 0. If n equal to 0, firstly, please note, n equal to 0. The polar plot starts from where? n equal to 0, what I told you, polar plot starts with finite magnitude. Okay, with theta st equal to 0, minus 90 degree into 0. That is 0. That means positive x-axis. The starting will happen with respect to positive x-axis with finite magnitude, not from infinity. How much finite magnitude? Not required, but if you want to have the finite magnitude, starting means 0 frequency. Okay, so put down s equal to j0. Okay, so s will be 0, only 1 and 2 will be left in the denominator. Okay, so the finite magnitude will be 0.5, although not required specifically, but I have written it. Okay, now, okay, what about the total number of poles is 2 and the total number of zeros is still nil. Okay, and the diving angle minus 90 degree into p minus z, minus 180 degree, and minus 180 degree means negative real axis. Negative real axis. So how my polar plot should look like? Okay, how my polar plot should look like? Let me draw it here only. It starts from positive real axis, but from finite magnitude this time, which is 0.5, or you can take any finite point. If you have not calculated that value, that also okay, but on the x-axis, positive x-axis, some finite value. Okay, this will be starting. And diving, now if I talk about diving, minus 180 degree. Diving means where? Diving means dive into origin, but along negative x-axis. You have to come such that you cut the negative x-axis. Negative x-axis. Okay, so from starting to diving, if you connect, this is approximately the shape of the polar plot. From starting to diving, if you connect. Okay, now please see that. Please see that. Acha, one more thing before I talk about what I was going to say. Why not this one? So suppose sometimes there may be a doubt. Why not this one? This also starting from the point and diving along negative x-axis. Why not the upper half? Why only the below half? If you are one of them having this doubt, it is a valid doubt if you are having that doubt. Okay, if any such doubt comes into the mind, okay, think about the angle expression. Just very basically you can think about the angle expression. See, let me take the angle expression. What is the angle gj omega at j omega? What is angle gj omega at j omega? See, this is 1 upon j omega plus 1, j omega plus 2, s equal to j omega if you put, okay. So, tan inverse y by x. So, first term will be, and it is a denominator term. The face is negative. Okay, tan inverse omega by 1, again a denominator term. So, tan inverse y by x, that will become tan inverse omega by 2. Because both are denominator term, that means entire face is negative. Okay, entire face is negative. That is what, correct, Google. Because it only has denominator poles, that the face will be always a lagging face, negative face. Okay, negative face. Okay, now negative face means suppose any small frequency I take. See, omega equal to 0 will give you the 0 face, as I have told you. If I just show you to explain it, you don't need to calculate any value. What I am trying to tell you that it's a negative face. Okay, it's going to be negative answer. Just to explain you, at point 1, let me show you how much is the phase coming. It is coming out to be some minus 8.57. Clear? It is coming out to be some minus 8.57. It is coming out to be some minus 8.57. Minus 8.57. Now, if it is minus 8.57, tell me, I am starting from here. If I increase the frequency slightly by an inch, 0.1, I get minus 8.57, and this minus 8.57 should be what point? Which quadrant it should be? It should be fourth quadrant, na? Because minus means what? Minus means clockwise, a clockwise small phase. Okay, clockwise small phase. Okay, some 8 degree, some 8.57 degree, but in the clockwise direction. So fourth quadrant point. Because if you assume this case, then when the frequency increase, your point is going to the first quadrant where phase should be positive. It should be a leading phase. Okay, so that is in-depth analysis. Okay, but what I'm telling, even if you observe, okay, negative phase, so it has to go clockwise. It has to be in the fourth quadrant entry. Okay, so this is the correct answer. Now, next important point. Next important point. This polar plot, when going from 0 to infinity, okay, it changes the quadrant from the 4th to the 3rd, and hence to change the quadrant, it cuts a coordinate axis. It is cut the coordinate axis, and that is negative y-axis. So, and hence the frequency at which it cuts the negative y-axis is the critical frequency here. But understand the difference. This is only omega c, but this is not omega p. I told you when you specially cut the negative x-axis, then it will be omega p. I will explain you the importance of omega p in some time. Okay, so this is known as omega c, only a critical frequency, not a phase crossover frequency. So when you intersect any coordinate axis, here, that is critical frequency. When you especially intersect here, that is the phase crossover frequency. Because stability depends on intersection, on encirclement of -1, 0. Now, -1, 0 lies on the negative real axis. Clear? Okay, so this is what it is. Okay, this is the omega c. That is going to be the starting point. Clear, everyone? Clear? Chalo. Okay, this is some omega c. Not necessary to calculate right now. I've got the shape, because sometimes only polar plot basic MCQ question, so you should be able to match shape like this. Okay, see again, 2 or more tan inverse term are there. 2 tan inverse term, that is why critical frequency is coming, right? Next one, polar plot for this one. Okay, please do it. Next, the polar plot for this one. Please do it. Please notice that before you do any calculation, please note it that there is a 0 in RHP. S-2 will give you a 0 in RHP, and for a 0 in RHP, one particular formula will change. I told you. For a 0 in RHP, one particular formula will change. For a 0 in RHP, one particular formula will change. What is that one particular formula? We'll see that. Okay. Chalo. Multiple intersection in any x-phase. Okay, that usually comes up because of the transportation lag term. Okay, just wait. I will try to bring up that problem. Yeah, let's do it for this one. First of all, what is the value of n? Number of poles at origin is 2, not equal to 0. Okay, it is equal to 2, not equal to 0. Okay, that means polar plot starts from where? Starts from, polar plot starts from where? It starts from infinite. N is not equal to 0. Okay, what direction? With the theta st as -90 degree into n plus 180 degree. Because of a 0 in RHP, I have to add the 180. That is the correction actually. That is the correction. Yes, it is the non-minimum phase case. Okay. So this is going to be -90 degree into n. N is 2 and plus 180 degree, and this turns out to be 0 degree. That means positive real axis. It will start from positive real axis, but with infinite magnitude. With infinite magnitude. Clear? With infinite magnitude. Then what about the total number of poles? 1, 2, 3, 4. 4 poles, and there is a 0. Okay, so diving angle -90 into p minus z. Into p minus z. So -270. So diving is along negative y-axis. Positive y-axis, sorry. -270, positive y-axis. Okay. So how the diving is going to look like? How the entire polar plot is actually going to look like? Have a look into this example. See, what I'm going to do is, understand here. Okay, so diving is along, first let me start with diving. That is along positive y-axis. Okay, so you have to dive such that you dive along positive y-axis. And where is the starting? Okay, you have to start from positive real axis. Positive real axis 0 degree. Positive real axis, that is 0 degree. Okay. Okay, with infinite. Okay, somewhere from infinite. Okay, and because if you write down the phase expression, minus 180 at omega equal to 0, minus 180 and small frequency. Yes, so fourth quadrant point will be obtained. Okay, so the starting will be somewhere parallel to the y-axis and parallel to the positive x-axis. Diving will be positive y-axis. Starting will be positive x-axis. So you start somewhere from here. Okay, you have to cut two coordinate axes. Okay, you have to cut two coordinate axes. Now, how much away is it from the x-axis? That is not required. It is starting somewhere from infinity. Let me call it as the 0 plus. Okay, any doubts you mention? Okay, and it goes up to the infinity plus, that is the diving frequency up to here. Okay. Okay, so this is a case. Okay, this is a case. Okay. Yeah, we'll take it. Just let me complete some cases. If you are concerned about exponential term polar plot, I will take it. Especially I want to talk about the problem of exponential term with the gain margin, phase margin. There I will tell you the polar plot also. Okay, just wait. Okay, so what is going to happen here? This is the critical frequency, omega C1. This is another critical frequency. Whenever you cut any inter-coordinate axis, it is critical frequency. This is only critical frequency, but this omega C2 is also omega P, is the phase crossover frequency. Is the phase crossover frequency. This is the polar plot obtained. This is what is the polar plot obtained for this function. Important point to note is what? A 0 in RHP. Important point to be noted here was the 0 in RHP, which I have taken care. Okay, a 0 in RHP. We have taken care of that fact. Clear? Okay. Now, let's come to sketching the complete Nyquist plot and then apply the Nyquist stability criteria. For sketching the complete Nyquist plot, I will draw it into, I'll write down three different steps. Number one, sketch the polar plot. I've been explaining you the polar plot, which is the plot of positive frequency, omega equal to 0 plus to omega equal to infinity plus. Okay, so I've explained you polar plots and the shortcuts and techniques around that. Then plot for negative frequency. Plot for negative frequency. The second step will be plot for negative frequency. Omega equal to 0 minus to omega equal to infinity minus. You have to do nothing. For plot of negative frequency, you don't have to do any calculation. What you have to just do is take the mirror image. Okay. Take the mirror image of the polar plot. Just have to take the mirror image of the polar plot around real axis. Around real axis. The reason behind that is actually conjugate symmetry property of Fourier transform. Okay. Conjugate symmetry property of Fourier transform. Okay. The reason is, okay, conjugate symmetry property of the Fourier transform. The conjugate symmetry property of the Fourier transform. Okay. And then next, join from closing from minus j0 to plus j0. That is, join from omega equal to 0 minus to omega equal to 0 plus. Okay, I'm not deriving it. Okay, I'm giving, because if we spend time on derivation, only one chapter may be completed entire day. Okay, so join from omega equal to 0 minus to omega equal to 0 plus. Okay, through an arc of infinite radius and through an angle of n pi in the clockwise sense if Nyquist contour is also clockwise. I'll talk about Nyquist contour, just wait. If Nyquist contour is clockwise, otherwise this will also become anti-clockwise. Okay, through an angle of n pi in the clockwise sense, where n is equal to same number of poles at origin. Number of poles of the open loop transfer function at the origin. Now let's understand this. Okay, let's understand this. Okay, great to know, Popa. Okay, but yeah, for Nyquist, if you need any derivation like why, how do we join from 0 minus to 0 plus, or what is the Nyquist stability criteria? Okay, I'll come to the stability criteria. I'll talk about Nyquist contour, but before we talk about that, let's do a Nyquist plot. Let's complete sketching a Nyquist plot. And if you want a complete derivation, okay, and if you feel that you are done with the complete syllabus, okay, your revision is also almost on pace, then you can watch that Nyquist derivation. If you don't know, then it will be helpful. But if you have a lot of syllabus left, then you need not go to the derivation right now. Okay. So I have already taken a video on our Om Institute channel only. I'll share you the link. I'll share you the link for it. Okay, just let me complete this problem. Okay, so where, why we need the formula n is p minus z, what is the 0 minus to 0 plus closing, everything. Why do we need the Nyquist plot? How do we use it for stability? Complete with the detailed derivation I have explained there. Okay. In fact, in that video, I have not explained the sketching. Sketching I am covering right now, how do you sketch and all. Okay, but if you want the detailed Nyquist understanding with the derivation, you can watch that video. I will share you the link in some time. Let's come to this one. See, I am starting with what type of form? Something which we have done. I told you, I told you important form. I told you that this is the important form. What is the form? K upon S 1 plus ST1, K upon S 1 plus ST1, 1 plus ST2, K upon the S 1 plus ST1, 1 plus ST2. Okay, good to know that, Popa. You are all enjoying learning. Okay, so already the polar plot of this form is known to me, na? See, because for Nyquist plot, I told you 3 steps. Polar plot, mirror image, joining from 0 minus to 0 plus. Okay, so polar plot is known to me already. So let's, draw the polar plot here first. Let me bring up the polar plot, which is already known to me for this particular function. Okay, for this particular function, it is already known to me. Okay. Few minutes back, we have seen the polar plot was something of this kind. Okay. Few minutes back, we have seen that the polar plot was something of this kind. Clear? Starting from 0 plus diving at starting at 0 plus diving at infinite plus of this kind. This was infinite plus point. This is the starting 0 plus point. Here it is. 0 plus to the infinite plus. Clear? 0 plus to the infinite plus. Now, what I told you, understand. What is the next step I told you? Mirror image of the polar plot about real axis. Mirror image about the real axis. Okay, so let me invert it. Let me take the mirror image. Then I know the critical frequency and all also. Let me take the mirror image about the real axis. Okay, so just flip it. Okay, so infinite plus image will be infinite minus 0 plus image will be known as 0 minus. Okay, will be known as 0 minus. And then next what I told you, join from 0 minus to 0 plus through an arc of infinite radius. Okay, and through an angle of n pi. Okay, what is the n here? Okay, what is the value of n here? Okay, so if I write down the value of n here, see, n is 1, number of poles of GSHS at origin, n equal to 1. So closing angle is n pi. Okay, that is pi in the clockwise sense. Okay, I will write down here, assume clockwise Nyquist contour. Okay, the closing angle pi in the clockwise. So what I have to do is I have to start from 0 minus, I have to come to 0 plus through a very, very big arc, infinite radius arc, and through an angle of 180 degree clockwise. Through an angle of 180. Anyways, dear, 0 minus is towards positive y-axis, 0 plus is towards negative y-axis. So from top to bottom, anyways, 180 degree, na? From top to bottom. So from here, we come and join the 0 plus point. Okay, and this is what is your 0 minus point. Okay, so from 0 minus to 0 plus, arc of infinite radius. Okay, to come to the 0 plus true angle of n pi. Now let me complete the entire arrows. Infinity minus to the 0 minus, 0 minus to the 0 plus. Zero minus to 0 plus and 0 plus to infinity plus. This is what is the complete. Okay, this is what is the complete Nyquist plot. This is a complete Nyquist plot. 0 plus is 0 on the positive side. Why exactly I don't write 0, Sajin? I'll just explain you once I go to the Nyquist contour. Okay. Once I go to the Nyquist contour. Okay. Now, dear. Yeah, let's talk about the Nyquist contour also, and let's talk about the stability criteria. Okay, this is done. The question is telling sketch the Nyquist plot. Okay, and determine the range of K for stability. And actually in competitive exam, these are two different questions. Okay, right. These are two different questions. These are two different questions. Number one, sketching the Nyquist plot or polar plot, or given some Nyquist plot. I will show you those questions also. Given some Nyquist plot, what is the range of K for stability? That's again a separate question. Okay, right. That's a separate question. So within the same question now, range of K for stability. Now stability analysis using the Nyquist plot. Okay, let me first talk about the Nyquist contour. Okay, Nyquist contour is the, what is the path? What is Nyquist contour, or we also call it as Nyquist path? We call it as Nyquist path, which is shown here clockwise. Here it is shown to be clockwise. It can be any direction. What is this Nyquist contour or the Nyquist path? It is that particular closed path in the S-plane to cover up the entire RHP. To cover up the entire RHP. Okay, because RHP is an important zone for me. I am searching for the roots of characteristic equation in the RHP. I am searching for the roots of characteristic equation in RHP. So I define a closed path in the S-plane starting along the positive y-axis, but starting from plus j0. See, what is this point? Plus j0. And what is this minus j0? To understand that 0 plus and 0 minus, actually what will happen for most of the functions at least, okay, including the case given here. See, I told you, na? So I told you, this is n not equal to 0. Okay, what is going to happen? Okay, because there is pole at origin. Okay, now you put 1 upon 0. What will happen? If you start s equal to 0, origin means what value of s? Origin means s equal to 0. So if you put down s equal to 0, 1 upon 0, infinite. So if you actually include s equal to 0 in the Nyquist path, if you include s equal to 0, that is origin in the Nyquist plot, and if the function has poles at origin, the function value will be undefined. Okay, the function value will be infinite or undefined. Okay, and that is the reason in the Nyquist path, okay, we want to skip the origin. Okay, we want to skip the origin. See, if there are no poles at origin, for a particular function, if there are no poles at origin, you can go in the regular manner also. You can even join it like this. Then you can only call a single point origin. No need to say 0 plus and 0 minus. You can join it if there are no poles at origin. So for different functions, there can be a different Nyquist path also. But this is the general case we assume. This is a general case we assume. Now, what is happening here? I travel along positive y-axis. Okay, I travel along positive y-axis. From plus j0, I go to plus j infinity. That is along the positive y-axis. Then from plus j infinity, I reach minus j infinity through an arc of infinite radius. Okay, from plus j infinity, I reach minus j infinity through an arc of infinite radius. Okay, why infinite radius again? Because I have to cover up entire RHP. So I take a infinite radius arc so that everything in the right half plane is covered, and then I reach minus j infinity, negative y-axis. Then I travel up to the minus j0. Okay, then I travel up to the minus j0, and finally from minus j0, I will have to close to plus j0, and the reason I am skipping the origin is I have explained to you. Is that okay, Sajin? Okay. Now, the GSHS plot for this given contour. Okay, the GSHS plot for this contour. Okay. For this particular Nyquist contour. For this Nyquist contour or for this Nyquist path is what is the Nyquist is known as the Nyquist plot. The plot of GSHS, okay, when the values of GSHS are plotted considering these values of S, then that particular plot is known as the Nyquist plot. And now the stability criteria using the Nyquist plot. See, for clockwise Nyquist contour, like here I have taken clockwise Nyquist contour. Now you see the direction. I have taken the clockwise Nyquist contour. We turn up with a formula n equal to p plus minus z plus. If it is anti-clockwise contour, before I explain you the terms, if it is anti-clockwise contour, the formula is actually z minus p. The formula is actually z minus p. Z minus p, where n is the number of encirclements of the origin 0, 0. Listen carefully. N is the number of encirclements of the origin 0, 0 by the GSHS plot. Number of encirclements of the origin 0, 0 by the Nyquist plot, GSHS plot. P plus. Now I use the symbol plus to make it clear that I am going to talk about the poles and zeros only inside the closed path. Only inside the closed path. Only inside the closed path. What is my closed path? My closed path is such that it covers the entire RHP. Okay. Entire RHP means entire positive side area. So that is why I use the symbol plus. P plus, all poles in the positive side area, RHP. Z plus, all zeros in the right hand side area, that is the RHP, positive side area. So P plus is the number of poles of GSHS lying in the RHP. Z plus is the number of zeros of GSHS lying in the RHP. Number of zeros of GSHS lying in the RHP. Clear? Now dear, why this formula is coming up? This is not the final stability conclusion, but why this formula is coming up? Okay, that's what. If you want to have the complete derivation, okay, that why do we take some S plane, why do we take GSHS plane, how do we come to the Nyquist stability criteria, what is this formula n equal to p minus z, why we need the closed path, why number of encirclements are coming up. Okay, so of course in the revision time I don't have the time to make it derive, but if you feel you want to learn Nyquist in more depth, okay, on the same channel I have taken the video on the Nyquist plot. You can watch it later on if you have comfortable time. If your syllabus is on track, then you can watch it up. That is a very important video. But again, if your things are on track, if your syllabus is on track, do watch it. Otherwise, okay, right now keep focusing on revision. Okay. Okay, so that is the important, because Nyquist plot detailed discussion is always very, very important. Okay, so unfortunately during this revision and marathon time I cannot take it. Okay, but if you want, I've shared you the link. Okay, I've taken it maybe a month or 2 months back. I don't remember the date exactly. Okay, but recently only it was taken. Yeah, probably within a month only it was taken. Okay, so you can watch it. Okay, so for your reference, I have shared you the link. You can click and you can save it with you. Okay, you can save it with you. So why this formula, how this formula, why that 0 minus 0 plus, why that n pi angle is coming, everything has been explained in that particular video. Complete mathematical and detailed analysis. Now let's come back here. Okay, you can watch that later. Okay, but actually what is required for stability? Still, I have given you a formula where I am talking about number of poles of GSHS in RHP, number of zeros of GSHS in RHP. But stability depends on the poles of not GSHS, poles of closed loop transfer function. Poles of the closed loop transfer function. See, if I again go back, we know that stability depends on what? Not on the poles of open loop transfer function, but the poles of closed loop transfer function, or also known as roots of characteristic equation. Roots of characteristic equation, or we can simply say that, see, what is the characteristic equation? 1 plus GSHS equal to 0. That means we can talk about zeros of 1 plus GSHS. Those values of S where 1 plus GSHS becomes 0. Where 1 plus GSHS becomes 0. So actually for stability I am interested not in the zeros of GSHS. Not in the zeros of GSHS. I am interested in the zeros of 1 plus GSHS. Okay. 1 plus GSHS. And that is why we think about drawing the Nyquist plot. Okay, I'll tell you in brief. Okay, so there are two things. Okay, change the whole theory and draw the Nyquist plot not for GSHS, draw the Nyquist plot for 1 plus GSHS. Okay, or just shift the origin to minus 1 comma 0. So we will keep drawing the Nyquist plot for GSHS only, and we will shift the origin to minus 1 comma 0, and this is the final stability criteria. Stability of closed loop system with the Nyquist plot, n equal to p plus minus z plus, where I will now talk about the number of encirclements of something known as modified origin minus 1 comma 0. Okay, the number of encirclements of minus 1 comma 0 by the GSHS plot only. Okay, z plus will be the number of zeros of 1 plus GSHS lying in the RHP, or z plus is also equal to roots of characteristic equation in the RHP. Then P plus should be the number of poles of 1 plus GSHS. Everything should change, correct? But I'll tell you one more thing now. Poles of 1 plus GSHS. You try any example, dear. Poles of 1 plus GSHS will always be poles of, all the poles of 1 plus GSHS will be the poles of GSHS. You try with any example, any GSHS example. Okay, so if Z plus is the zeros of 1 plus GSHS, P plus should be the poles of 1 plus GSHS, I agree. But poles of 1 plus GSHS will be same as poles of GSHS. So we don't change the P plus definition, and P plus will be the number of poles of GSHS only in the RHP. Okay, again I am telling you how this formula is coming up. Each and everything has been explained in the detailed derivation video. In revision marathon, I am not doing the derivation. You can watch it later on. Okay, so P plus is the number of poles of GSHS lying in the RHP. Now let me explain you these terms with the current example going on. So what I have done for this example, the Nyquist plot was drawn. It is complete. And now what is the range of K for stability? Okay, from this Nyquist plot, what is the range of K for stability? That is what we want to check here. Okay, from this Nyquist plot, what is the range of K for stability? What is the range of K for stability? Let's check it out here. Okay, let's check it out. Range of K for stability. So, see, first of all, the stability depends on what? Stability depends on encirclements of minus 1 comma 0. Is that clear? Okay, encirclements of minus 1 comma 0. Now, if I want to talk about encirclement of minus 1 comma 0, where is the minus 1 comma 0? Do I know this coordinate? Okay, so now let me complete this Nyquist plot. Dear, this frequency, okay, which is omega c, or very soon I am going to define it as omega p, is 1 upon root T1 T2. Okay, so how much will be that frequency? How much will be that frequency? Okay, so let me do the calculations here. What are the time constant given here? T1 and T2. Okay, so T1 is 1 by 2, T2 is 1 by 3. So what is omega c or omega p here? 1 over root T1 T2, that will be 1 over under root of 1 by 2 into 1 by 3, and take the 2 into 3 in numerator, that is equal to the root 6. That is equal to how much? That is equal to the root 6. Okay, so omega c or omega p is same, and that is equal to the root 6. That is equal to the root 6. Now next. Okay, next, at this frequency, what is the magnitude? The magnitude, you remember, I have written that formula K T1 T2 upon T1 plus T2. Okay, K T1 T2 upon T1 plus T2. So you have to multiply by 6, and then in that case you will get K upon 3 plus 2, K by 5. So in that case I am going to get the answer as K by 5. I am going to get the answer as K by 5. K by 5. Okay, so how much is this magnitude? This is K by 5. Okay, and this frequency, let me write down the value since I have calculated. This frequency is the root 6, at which the magnitude is K by 5. Now since K is unknown, I mean K can take any value 0 to infinity, it's the open loop gain parameter. So because K can take the any value from 0 to infinity, I exactly don't know where the minus 1 comma 0 point is going to lie down. I exactly don't know where the minus 1 comma 0 point is going to lie down. That means I will have to consider different cases. Where is minus 1 comma 0? Where is minus 1 comma 0? Maybe here, case number 1, minus 1 comma 0. Maybe here, case number 2, inside. And if it is inside, then only encirclements will come. This is minus 1 comma 0, case number 2. Okay, so what are the two cases? Case number 1. Okay, case number 1, -1, 0, out. I have taken it out, case number 1. Okay, and out means this much of the magnitude, which is k by 5, should be less than 1. The magnitude of -1, 0 will be 1. So k by 5 should be lesser than 1. So out will happen if k by 5 is lesser than 1. Okay, and because it is out, then there is no encirclement. What is n? Number of encirclements of -1, 0, okay, by the Nyquist plot, by the GSHS plot, of the modified origin. So it is not encircled, it is sitting outside. Case number 2. First, let's talk about n only. Case number 2, -1, 0, I bring it in. Let me bring in the -1, 0. Clear, everybody? So if the -1, 0 comes in, that is only possible if this k by 5 is more than 1. This 1 is smaller. So this can be inside if the k by 5 is more than 1. Okay, and then how many encirclement? Now it is encircled. Now it is encircled. How it is encircled? Everybody please concentrate and see with me. How it is encircled? Okay, just please concentrate and see with me. Please concentrate and see with me. See how it is encircled. Case number 1, it is encircled once like this. It is encircled once like this. It is encircled once in the clockwise by the inner loop. And one more times it is encircled. Encirclement means when you complete one rotation around it. When you complete one full rotation around it, that is known as one encirclement. That is known as one encirclement. That is known as one encirclement. Clear? Okay, so one full rotation around this. Okay, so one by the outer loop, one by the inner loop. How many times encircled? 2 times encircled. How many times encircled? 2 times encircled. Okay, so it is encircled. Okay, how? Once, and both the times it was clockwise. See, this is also clockwise, the outer one is also clockwise. Once clockwise by the inner loop, and once again clockwise, but by the outer loop. Okay, and we know that the number of encirclements are associated again with the direction, anti-clockwise always being positive and clockwise always being negative. So since there are 2 clockwise encirclements, the value of n that we shall be taking here is the -2, is equal to the -2. The value of n that we shall be taking here is equal to the -2, right? Is equal to the -2. Correct, dear? Is equal to the -2, n equal to -2. Okay, now let us come to the stability formula. What is the stability formula? I have told you n equal to p plus minus z plus, because I have assumed clockwise Nyquist contour. Again, let me write down. If it is anti-clockwise Nyquist contour, then the formula you will use is z minus p. Okay, then the formula that you will use is the z minus p. Be clear about this. Then the formula will be n equal to z plus minus of p plus, z plus minus of the p plus, z plus minus p plus. Okay, so yeah, let's come here and apply the Nyquist stability formula. Okay, so the formula is n equal to p plus minus z plus. What is p plus? What is p plus? Okay, p plus is the number of poles of GSHS in the RHP. So what are the poles of GSHS? All right, if I write down the poles, S is 0 and a -2 and a -3. Okay, 2 in RHP, 1 at origin. Okay, nothing in RHP. So the poles of GSHS in RHP is nil. The p plus is 0. And because the p plus is 0, my formula n is now minus z plus, or z plus is minus n. Z plus is minus n. Okay, what is the range of k for stability? So case number 1. What is the case number 1? N is 0. Okay, case number 1. Okay, what is that case number 1? K by 5 less than 1. Okay, or k is less than 5. Okay, that n is 0. If n is 0, z plus is also 0, meaning stability. Because what is z plus? Because what is z plus? Number of zeros of 1 plus GSHS. Okay, that is the roots of characteristic equation in the RHP. And For stability, how many RHP roots you want? Nil, because even if one RHP root system is stable, even if one RHP root system goes unstable. So for stability, I would require Z plus equal to 0. I would require Z plus equal to the 0. Okay, now under the second case, that is the k by 5 greater than 1 or k is greater than the 5. Okay, k is greater than the 5. Okay, so what is the value of n? N I have already shown you minus 2. So Z plus, which is minus of n, Z plus equal to plus of 2. Z plus equal to plus of 2. And plus of 2 means unstable. Any RHP root system is 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 unstable, correct? Any RHP root system is unstable. So question was asking range of K for stability. The system is stable for my answer. How will I frame my answer? System is stable for case number 1, K less than 5. Okay, to be more specific, K between 0 to 5. Gain K by default assumed positive. Yes, most likely it will be given directly or some hint will be given around it, clockwise, anti-clockwise. Otherwise, normally you can assume clockwise. That's just a convention. There is no theorem to support that, why to assume clockwise. That's a convention seen in most of the problems. But yeah, normally if it is a gate question, they are mostly careful and they will give you, especially recent years, they will carefully give you what the type of contour is, clockwise or anti-clockwise. Directly or indirectly they will give, okay? Directly or indirectly they will give. Directly or indirectly they will give out. Okay. So this is how we determine the range of K for stability using the Nyquist plot. Range of K for stability using the Nyquist plot. Clear? Now, before I take the next question, we'll do some more similar questions. Okay, we'll do some more similar questions. Or actually, let's do it. Let's complete these questions in the flow. Okay, and then I'll come to this important point, -1, 0, which lies on the negative real axis. And that is why when the Nyquist plot cuts the negative real axis, that is important. This omega c, which is going to be named as omega p very shortly. I'll define phase crossover point and that will define the gain margin of the system. Okay, that will define the gain margin of the system. All right. Okay, but before we go to that, have a look into another question. Yeah, have a look into this question. I hope you want this gain margin and phase margin to be covered right now. Tell me, do you want this gain margin, phase margin immediately after this discussion? No, n again has a sign convention that remains to be same, that is independent of contour. N means number of encirclement, that has a sign convention. Okay, positive encirclements are anti-clockwise, negative encirclements for clockwise. Okay, yeah. So right now taking some more Nyquist plot questions, but tell me, do you want the gain margin and phase margin in continuity only? So we'll go with that in continuity. All right, good. Chalo, let's take this question. Let's take this question. Answer me. Okay, yeah, let's start it then. Let's start this question first of all. The Nyquist plot of an open loop transfer function of a negative feedback control system is shown below. If the open loop system is stable, then the closed loop system will be what? Then the closed loop system will be what? If the open loop system is stable, what will be the closed loop system? Unstable with 2 RHS poles, unstable with 1 RHS pole, unstable with 3 RHS poles, and stable. And stable. What will be the closed loop system equivalent to? What will be the closed loop system equivalent to? Closed loop system equivalent to? Closed loop system equivalent to. Let's do it. So What is this statement meaning? If you are done, please mention the correct answer. The Nyquist plot is shown. If the open loop system is stable, open loop system is stable. Okay, now any system is stable if it does not have RHP poles. If it does not have RHP poles. Open loop system stable means what? Okay, that means no RHP pole of open loop transfer function of GSHS. That means P plus. So, directly, indirectly, in such questions, the GSHS not given. I told you these are two separate questions. GSHS given, draw the Nyquist plot. Second, given the Nyquist plot, talk about stability. So there GSHS directly won't be given, some indirect information will be given, right? So P plus is 0. Now the system is stable or unstable, and for that I need what answer? For that I need the answer using n equal to P plus minus Z plus. Okay, assuming clockwise contour, they have not mentioned. Okay, let me take the clockwise contour. So n equal to P plus minus Z plus, and n is equal to minus Z plus. P plus is 0 or Z plus is minus n. So how many encirclements here? How many encirclements you are able to feel for the point? Minus 1 is clearly, because GSHS is not given, so they will have to tell where is minus 1. Previously I calculated the magnitude k by 5 and then we located minus 1 comma 0. So let's trace it here. Let's spend the time on tracing it. Have a look into it. See, let me begin up this from origin. Take origin as the reference point. Okay, yeah, one encirclement complete. You start from origin, means that is the part of x-axis only. Positive x-axis to positive x-axis. Okay, the point is a complete rotation, a 360-degree face should change. Okay, now whether 360-degree face is changing or not. Okay, that's what. See, sometimes, okay, sometimes what students will do. Okay, this much means one encirclement. No, one encirclement means one rotation. One rotation means 360-degree, one full. What will happen if you are going like this? Okay, the face is changing in the from this point to this point. Let me actually use this pen better. From this point up to this point you go, the face has changed in the anti-clockwise sense. Okay, from this point to this point you come, the face will change in the clockwise. Face will change clockwise. So that is not any face change, I would say. That is nullified. So dear, when you go from this point to this point, now I will draw it again. Okay, when you go from this point up to this point, okay, you went anti-clockwise, you came back clockwise, no phase change. Okay, now I'm continuing from here. From here, now I'm moving in the same direction. Clock. This is one encirclement complete. This is one encirclement complete. This is one encirclement complete. Clear? This is a tricky question. Remember, one encirclement complete. Why one encirclement complete? Again, see with the pen. See what I'm telling. I start from this point and I'm moving in this path. Okay, so I am moving clockwise, and I move 360-degree. Okay, I move 360-degree in the same direction clockwise, and that is one clockwise encirclement. Okay, so this is one clockwise encirclement, right? One clockwise encirclement. Now let me keep continuing. Okay, now I again take from here clockwise. Okay, but coming back anti-clockwise. See now, to reach this point. Okay, to reach this point, from here to here I go clockwise, but from here to here I am coming actually anti-clockwise. So this is also nullified. This is nullified. So only one clockwise encirclement. Right, only one clockwise encirclement. Okay, what is OO? Google, can you specify what OO you want to say? Okay. I am in the interest of encirclements of minus 1 comma 0. Okay, so how many encirclements? N equal to minus 1. 1 clockwise, n equal to minus 1. So Z plus will be equal to plus 1. Okay, that means unstable also, and with how many RHP roots? Right, it is unstable with one RHS pole, one right hand side pole. It is unstable with one right hand side poles. Got this? I told you it is tricky. Sometimes we just keep on counting via start and end. See, understand like this. If there is a confusion, understand like this. Suppose I am on positive x-axis. Okay, on the positive x-axis, okay, I go to some other point like this. Okay, and I come to this point. See, what is the theta here? Positive x-axis means 0. Okay. I went like this. Okay, but I am going and I reach how much? This is the positive y-axis. Okay. I reach how much? I travel how much? Okay, I travel how much? I first traveled anti-clockwise 90. Okay, but then I traveled. Okay, in the reverse direction, 90 degree. So, do you say I traveled 180 degree? No, I traveled 90 degree clockwise. I traveled 90 degree anti-clockwise. Nullified. The net change in phase is 0. The net change in angle is 0. Okay, the net change in angle is 0. What is the meaning of one encirclement? One encirclement means when you have done one complete rotation about -1, 0, and one complete rotation means 360 degree phase change. Whether it is clockwise or anti-clockwise, okay, both are acceptable. They have a sign change. But 360 degree of phase difference is important. 360 degree of phase difference is important. Is that clear? Okay, so only one encirclement here. Okay, that's the reason I brought this question. Only one encirclement, option is B. Unstable with one RHS pole. Unstable with one RHS pole. Okay. Otherwise, I know normally students will do, okay, from here to here, one. From here to here, one more. No, not actually. Not actually. Hope that is clear to you. And let's be ready for the next question then. Let's be ready for the next question. Okay, the loop transfer function of a feedback system is given to you. GSHS equal to S plus 3 upon S square S minus 2. S plus 3 upon S square S minus 3, sorry. Take the Nyquist contour. See, mentioned, na? Take the Nyquist contour, okay, in the clockwise direction, which usually should be mentioned. Then the Nyquist plot of GSHS encircles what point? Now this question, very smart question, please listen to me. The Nyquist plot of GSHS encircles -1, 0. How can you calculate? How can you calculate? The Nyquist plot encircles -1, 0. So question is on N. And encirclement of what? Encirclement of -1, 0. So what do you think? How many times the Nyquist plot encircles -1, 0? Normally what we will think? Okay, we have to draw the Nyquist plot. Normally what will I think? We have to draw the Nyquist plot to see how many encirclements coming up. How many encirclements coming up? We have to draw the Nyquist plot. But actually, let's not do that. Actually, we can avoid it. Actually, we can skip it. How we can skip it? Listen to me. Let's not do that. We can avoid that. Okay, the Nyquist plot encircles -1 plus j0. We can avoid that calculation. Okay, we can avoid drawing the Nyquist plot. Okay, so that's what. Method number 1 is draw the Nyquist plot and see. Draw the Nyquist plot and see. And talk about N. Okay, or simpler, smart method. Drawing Nyquist plot, of course, will take some time. Na? Better directly use the formula. Because GSHS is given, you can use the formula. You can use P plus and Z plus. What is P plus? What is P plus? Okay. Poles of GSHS in RHP. What are the poles of this function? S equal to 0, 0 and plus 3. This is in RHP. Okay, so how many poles in the RHP? Is 1. So P plus is known to me. But what is Z plus? What is Z plus? I can do that also. What is Z plus? Z plus is zeros of what? Is zeros of 1 plus GSHS in RHP. Characteristic equation. I have told you multiple times. Zeros of 1 plus GSHS means roots of characteristic equation. So what is my characteristic equation? GSHS given, so I will build it. 1 plus S plus 3 upon S square S minus 3 equal to 0. 1 plus S plus 3 upon S square S minus 3 equal to 0. Giving me S cube minus 3S square plus S plus 3. You don't have cubic calculator. You don't have cubic calculator. How do you know how many roots in RHP? Dear, we have the something known as RH criteria. S cube and S square. So 1 and 1 minus 3 and 3. S power 1 minus 3 minus 6 upon minus 3 2 and 0. Last element 0. 2 into 3 by 2 3 and 0. How many sign changes? I have a one sign change. I have another sign change. Okay, these two sign changes means 2 RHP. 2 sign changes, 2 RHP roots of characteristic equation. Z plus is also known to you. No need to draw the Nyquist plot. It becomes a RH question actually. And N is P plus minus Z plus. P plus I told you how much? P plus is 1. Z plus is 2. And N is equal to minus 1. What is the meaning of minus 1? 1 clockwise. What is the meaning of -1? 1 clockwise, once in the clockwise sense. Once in the clockwise direction. Clear enough? Once in the clockwise direction. Once in the clockwise direction. Okay. In the clockwise direction. Negative feedback. Negative feedback. Positive feedback systems are mostly unstable. They are used for oscillator design and all. Stability, when we are talking mostly, not mentioned, assume negative feedback only. Don't worry. Okay, done. Clear. So once in the clockwise direction. Once in the clockwise direction. That direction is also important. Clockwise or anti-clockwise. Clockwise or the anti-clockwise. Now the next question. Now the next question. A unity feedback system has the loop transfer function. Again, let me write unity negative feedback system has the open loop transfer function GS 1 upon S minus 1, S plus 2, S plus 3. Nyquist plot of GS encircles the origin. In what direction? In what direction? Origin. Origin means, when I say origin, it automatically means 0, 0. Na? When I say origin, it automatically means 0, 0. It means 0, 0. So how many times Nyquist plot encircles the origin? Okay, so question is again on N. But encirclements of 0, 0. Again I will say two methods. Method number 1, draw the Nyquist plot. Spend some time, draw the Nyquist plot. Or method number 2, again make it easy, use a smart approach. Use N equal to P plus minus Z plus. But what N? N is the encirclement of 0, 0. So P plus to we know will remain same. P plus is anyway same in both the cases. Poles of GSHS in RHP. What will be Z plus? Finish. Question is finished here only. What is Z plus? Zeros of GSHS in RHP. Remember na, when you are talking about encirclement of 0, 0, when you are talking about encirclement of 0, 0, come here, come here, come here, come here, come here, come here, come here. Where is my criteria? Yes, this is what I told you. Okay, when you are talking about encirclement of 0, 0, then the Z plus was the zeros of GSHS. Only GSHS, right? When we talk about encirclement of modified origin, then we talk about zeros of 1 plus GSHS. This is important for stability, but there can be numerical question. Encirclement of 0, 0, which is not required for stability, but there can be a numeric question. Concept, so dear, should be known to me, na? Okay, concept should be known to me. So how many poles of GSHS in RHP? So it has no zeros first of all. Only zeros of GSHS known. So zeros, nil. And what are the poles here? S equal to 1 and minus 2 and minus 3. And 1 means RHP. Okay, so 1 and RHP. So P plus is 1 and Z plus is nil. Z plus is nil. Now, actually contour is not mentioned. See, that is the reason in this they have not mentioned the direction of encirclement. See now. Okay, what is the contour? Previous question I mentioned, na? See the previous question. Assume the Nyquist contour in the clockwise. Okay, contour is not mentioned here. It may be clockwise or anti-clockwise. If it is clockwise, then you use the formula N equal to P plus minus Z plus 1 minus 0, that is 1. Positive 1 means 1 anti-clockwise. But if you use the formula, if the Nyquist contour is anti-clockwise, then what is the formula? Z plus minus P plus. Z plus minus P plus. Okay. So N is how much? Z plus minus P plus. Z plus is 0, P plus is 1. N equal to minus 1. Okay. Why? Minus 1 means 1 clockwise. Okay. But whether it is anti-clockwise or clockwise, that is why they have asked only the number of encirclements, the magnitude. Okay. How many number of encirclement? It is option number B, once. That is for sure it is going to be encircling the minus 1, 0 once. It is going to encircle minus 1, 0 once. That is for sure. Okay, whether anti-clockwise or clockwise, that depends on the contour. That depends on the contour. Clear? Which was not mentioned here. Okay, which was not mentioned here. Clear? Done. Then we are done. So option number B, once. Whether anti-clockwise, clockwise, that is not clear here, but it is going to be once. That part is clear to me. That part is clear to me. That part is clear to me. Come to a very good question. GATE 21, for 1 mark specially, it is a very good question. For 1 mark specially, it is a very good question. Think about this. Think about this. Yes, encircling -2, 0 can also be asked. Tell me, if you want encirclement of -2, 0, what will you do? Numerically, they can ask encircling -2, 0. Yes, they can. Correct. Avinash has given the answer. Okay. P plus will still be the same. P plus will still be the same. Z plus will be the zeros of 2 plus GSHS. Z plus will be the zeros of 2 plus GSHS. GSHS equal to -2 also we can say. Correct. So you have to form an equation like we form characteristic equation. 1 plus GSHS, you will have to form an equation 2 plus GSHS. Got it? Okay, fine. Chalo, let's continue this question. The complete Nyquist plot of the open loop transfer function GSHS of a feedback control system is shown in the figure. If GSHS has 1, 0 in the right half of the S-plane, then the number of poles that the closed loop system will have in the right half of the S-plane. In the right half of the S-plane. Okay. If GSHS has 1, 0 in the right half of the S-plane, the number of poles that the closed loop system will have in the right half of the S-plane. See, what is given? The complete Nyquist plot is given. Okay, that is what I'm telling you. When Nyquist plot is given, GSHS not given, some information around this is given. Okay, so what are the answers coming up? Till now, B and C, I've got the answer. Let's see. Now, GSHS has 1, 0 in the right half of the S-plane. Now, what is the question? Number of poles that the closed loop system will have in the right half of the S-plane. See dear, important point. Okay, what I want? The question is asking about number of poles of what? Closed loop system, closed loop transfer function in RHP, in the right side of the S-plane. Poles of closed loop transfer function means roots of characteristic equation in RHP. Roots of characteristic equation in RHP. Okay, that means Z plus. Z plus. Okay, but for N, okay, Z plus is for what encirclement? When you want the roots of characteristic equation, 1 plus GSHS, 1 plus GSHS. Okay, then the encirclement is for -1, 0. It is for -1, 0 encirclements. It is for -1, 0 encirclement. Okay. Okay, Avinash also says answer 1. Yes, Ashok, happy Bogi, happy Lodi, and tomorrow is Sankranti, Pongal. Wishing you all positive festive of time. See, of course, GATE is very close, so your festive time means preparation on the peak only. So that is what I meant by positive festival time. You spend maximum time on the preparation only right now. Okay. See guys, if we are done with, just answer me one thing. If we are done with, most part of the revision today, I'm going to continue. Don't worry. I'm still there. Okay. If we are done with most part of the revision, so tomorrow also is the day I reserved for control. Then what we will do tomorrow is, I have an idea. Like few days back, I took a MSQ session on mathematics. Tomorrow, let us take a MSQ session on control system. Not necessarily GATE question. I will bring up some new questions also. Okay, tomorrow let us plan a MSQ session on control system. Okay, how do you say? How do you say? Then I will think about it after I close the session. I'll think about this. Okay, but if you are interested, let me know. Tomorrow we can, since we have revised lot many things today, and I'm still continuing. So tomorrow let's have some MSQ practice on the control system, because MSQs are becoming dominant. You need to handle from every subject. Okay, so like that with signals also I will plan once the signals revision is over. Let me know if you are interested for the plan and if you want to attend that MSQ session. Okay, then only I will think and try to plan it by tomorrow itself. Tell me, come here. Maths MSQ session was taken, I've taken 3-4 days back. Maths MSQ, I took it purely previous year because lot of previous year questions of Maths MSQ. I took it, I think, on Friday or Saturday, somewhere exactly, I don't remember. Friday or Saturday, I took it mostly. Right. So tomorrow, similarly, we can plan a MSQ of control system. Okay. Of course, from MSQs, definitely we can build up the questions on controllers and compensators also, because they have a lot of factual, the conclusions, this controller does what and does that, etc. Chalo, so let's do that. Again, answer coming up is C. Now let's talk about this. It's a tricky question. It's a very good question, I would say. It's a good and tricky question. See. Nyquist contour is not mentioned, na? Okay, let me start. N equal to P plus minus Z plus. Okay, not given, so as a regular practice, let me assume clockwise Nyquist contour. Keep listening to this. Let me assume a clockwise Nyquist contour. Clear? Let me assume a clockwise Nyquist contour. Okay, Vikram. So N equal to P plus minus Z plus. Okay, where is P plus? C? Where is P plus? I want Z plus. Okay, and a number of encirclements is there in front of me. Na? How many number of encirclements? Minus 1, 0 encirclements is how much? Minus 1, 0 encirclement. That can be noted from the plot. Everybody, please notice the encirclements with me from the plot. This is one encirclement. Very clear. And one more encirclement. Okay. How many encirclement? How many encirclement? How many encirclement? Okay. How many encirclement? One. One anti-clock. One clockwise. This is anti-clock. The outer one is clockwise. So number of encirclement. Anti-clockwise means plus 1. Clockwise means minus 1. So there is no net encirclement actually. Please be careful. There is no encirclement. There is no net encirclement. There is no net encirclement. Okay, so number of encirclement is 0, is P plus minus Z plus. So the question is on Z plus, it should be equal to P plus, but what is P plus? P plus is the poles of GSHS in RHP. If you are using this value 1, that is wrong. GSHS has a 0 in RHP. Why do I need the 0 here? Okay, I need P plus. P plus is the poles of GSHS in RHP. How do you calculate P plus? Not possible. Not possible right now. Okay. But what can I do is, now consider 0, 0 encirclements. Because there is some data given, it will have some role maybe, na? It will have some role. What is the data given? Data is telling you the GSHS zeros in the RHP. Zeros of GSHS in the RHP comes under 0, 0 encirclement. Comes under 0, 0 encirclement. Comes under 0, 0 encirclement. So that is why I am considering 0, 0 encirclement. Okay. So what is the formula? N equal to P plus minus Z plus. The formula remains to be same. Clockwise Nyquist contour has been taken. What is the value of N? See, what is the value of N? 0, 0 encirclement. 1 in the clockwise. One more in the clockwise. So if you talk about origin encirclement, plot is given, we can see every encirclement. 1 clockwise, 1 more clockwise. Okay, 1 more clockwise. So 2 clockwise. And what is the meaning of 2 clockwise? Minus 2. Minus 2 is P plus minus Z plus. Now Z plus is the, in this definition, we know that what is Z plus? Okay, in this definition, Z plus, P plus is still the common. Okay, Z plus is zeros of GSHS in the RHP, which is given to me. Zeros of GSHS in the RHP, which is given to me. Okay, which is given as 1. Okay, and hence P plus is minus 1. Oh, this is a trap. This is a trap. Not possible. P plus can't be negative. Na? P plus, Z plus, these are some counts. These are some counts. Okay. Right, these are some counts. Okay, we'll think about calculus marathon also. Just wait. Let me just finish this technical part first. Okay, P plus are counts and counts cannot be negative, right? The count number cannot be negative. It will have either no pole in RHP or 1 pole or 2 pole. What is the meaning of minus 1 pole? Minus 1 number of poles. Not possible. Okay, not possible. So this was a trap. Okay, the contour not given was a trap in the question. So now assume anti-clockwise Nyquist contour. assume anti-clockwise Nyquist contour. Again, let me use the formula n equal to p plus minus z plus. N is the number of encirclements of minus 1 comma 0 originally, which is same. Number of encirclements depends on Nyquist plot, that is given. So n is 0 is p plus minus z plus, and again z plus is p plus. But where is p plus? I don't know. Okay, so again I will go for 0, 0 encirclements. Similar story I am repeating. I will go for 0, 0 encirclements. Okay, so n is again, oh sorry. And here was the formula z plus minus p plus, and hence p plus is z plus. Okay, now again I will use the formula n equal to z plus minus p plus. 0, 0 encirclements is already noted, minus 2. Z plus we know is 1. Z plus we know is 1. Okay, so hence p plus will be 1 plus 2, and which is 3. Okay, so p plus equal to 3 can be the very, very correct answer. This looks correct, and hence z plus is also 3. Z plus is also 3. Copying this calculation here. The correct answer is option number A. A very good question. GATE 2021, 1 mark, a very good. Especially for 1 mark, I would call it as a really good question. Okay, fine. Chalo. Let's move ahead to the next. Let's move ahead to the next. Yeah. So guys, important announcement before I go next. Okay, yes. Okay, the GATE 2026, the first offline regular batch for EE and EC, both the branches. Okay, the offline batch, okay, at our Hyderabad center. The first of them is on February 24th, 2025. The fee is currently priced at 54,999, and over and above that, early bird discount of 4,000 you can avail if you register till 30th of January. So you can inform, okay, for all those who may be looking for the future GATE courses, your juniors, your colleagues, your friends. Okay, and for any queries, you can contact 95156940053. And now let's talk about the gain margin and face margin. The gain margin and face margin. The gain margin and the face margin. Okay. See, what is important for stability is the minus 1 comma 0 encirclement, isn't it? What is important for the stability is the minus 1 comma 0 encirclement. Is the minus 1 comma 0 encirclement. That is the important point for stability. Okay, that is the important point for stability. Now keep listening here. Let me again take up one of our regular polar plot example. The K upon S, 1 plus ST1, 1 plus ST2. Suppose this particular polar plot crosses the x-axis at the point minus of 1 by 2 comma 0. Okay, so where is minus 1 comma 0? It automatically goes out. I am only drawing the polar plot. If you complete, this will be the Nyquist plot, and you see minus 1 comma 0 outside. Minus 1 comma 0 outside. Okay, so the first case possibly I am taking when the minus 1 comma 0 is outside. So how many encirclements? How many encirclements? Okay, 0 encirclements. Okay, p plus for this function is also 0. Same function I am repeating. Okay, and this case is stable case. This case is the stable case. Okay, but if I do one more calculation, if I draw one more plot here, see, what can be the next possibility? Okay, maybe this point is, say for example, minus 3 by 2 comma 0, and hence minus 1 comma 0 comes inside. And one more possibility is that the plot itself is crossing the minus 1 comma 0 point. Correct? This was stable. Here encirclements will come and the system will become unstable. Okay. Yes. EMFT marathon is there. 15th. Hemant sir. Hemant sir is taking it. Okay. 15th January. That is Wednesday. Okay. EMF marathon is there to be taken by Hemant sir. After that, I will take signals. Okay. 15 January EMF marathon by Hemant sir. Now come up here. Now please come up here. This one. The system has to be stable in the first case. In the next case, encirclements will come. Okay. And Z plus will also come. And for non-zero Z plus, system is unstable. Okay. And in this case, the boundary between stability and instability is marginally stable case. Here the system is marginally stable. Okay. So stability depends on number of encirclements of what point? -1, 0, and -1, 0 lies on -1, 0 lies on the negative real axis. The important point here is this -1, 0 point lies on the negative real axis. Okay, I am now interested in the frequency. Okay, coming to this important term, I am now interested in the phase crossover frequency. It is the frequency at which the Nyquist plot intersects the negative real axis. Okay, negative real axis. The Nyquist plot intersects the negative real axis. Okay, so when does the Nyquist plot intersect the negative real axis? At this particular frequency. And this is known as the phase crossover frequency. Now, what is the magnitude at this phase crossover frequency? This is omega p. Now, what is the magnitude at this phase crossover frequency? Okay, what is going to be the magnitude at the phase crossover frequency? Okay, so at omega p, what is the magnitude? Magnitude here is 1/2. The magnitude, this distance is 1/2. Okay, now that means, can I increase the gain of the system? Yes, you can. You can make the gain of the system as 1/2 or 2/3. This is 0.5. Now you can make it 0.6, 0.7, 0.8, 0.9. You can increase up to what point? You can increase the gain up to 1. Because as soon as you make the gain 1, you are at the boundary, you are at the risk of instability. And if you increase the gain beyond 1, the system becomes unstable. There is a stable system. There is a stable system for which you can increase the gain. By how much? Maximum 2 times. By how much? Maximum 2 times. Okay. So gain margin. Okay. It is the margin by which the gain of a system can be increased. Multiplication factor by which the gain of a system can be increased. So the gain margin is how much here? It's actually 2 times. Okay. It's actually 2 times because 2 into 1/2 will be 1. Why it is 2 times? It is the reciprocal of this current magnitude. It is the reciprocal of this current magnitude. So what is the next idea? What is the gain margin? Okay, gain margin for a stable system, it is the margin by which gain of a stable system can be increased. Okay, before it reaches the point of instability. And what is the gain margin? Reciprocal of the magnitude at omega p. Magnitude of what? Gj omega hj omega. So we calculate mod gj omega p hj omega p and calculate that magnitude at omega p. The reciprocal of that magnitude. Okay, like here the magnitude was half, the reciprocal of half is the gain margin. Correct? Is the gain margin. Commonly calculated in decibel to be consistent with the log plots also, the Bode plots. The gain margin in decibel is given by 20 log 1 by mod gj omega p hj omega p. The standard unit of gain margin is actually in decibels. 20 log mod gj omega p hj omega p. Okay, Avinash. Okay. So that is why the phase crossover frequency is important, where the Nyquist plot intersects the negative real axis. But when we come to question, to calculate phase crossover frequency, you actually don't need the Nyquist plot every time. Like phase crossover frequency means you are intersecting the negative real axis. And what is the phase at negative real axis? Okay, the phase at negative real axis, 180 degree, plus or minus anything. So how do you calculate? Given gj omega hj omega, calculate the phase of it and equate to plus or minus 180 degree. Okay, the solution of it will be the omega p. Clear? You don't have to draw the Nyquist plot. Okay, you don't have to draw the Nyquist plot. Okay, you don't have to draw the Nyquist plot. Okay, but yeah, here gain margin is 2. The absolute value is 2, but when you take it in log 2 is positive. Okay, what about the magnitude here? So magnitude here is 3/2. Okay, the magnitude here is 3/2. So even if you want to calculate 20 log 1 upon this magnitude, it will become 20 log 2/3. Reciprocal of this will be 2/3 and the log 2/3 will be negative. When you take log of number less than 1, it will be negative. So the idea is, So the idea is whenever the system is unstable, gain margin will be negative. For stable system, it will be positive. Okay, because in decibel, it will be here 20 log 2 and 20 log 2 is 6 dB positive. And for a marginally stable system, how much is the magnitude? 1. So log 1 is 0. Okay, so remember gain margin positive for stable, negative or unstable, and 0 for marginally stable. I will write down, very, very important. You will see they are very, very important conclusions. Okay. The next point is stability always depends on -1, 0. -1, 0 can be located on 2 points. One is on the x-axis. One is on the negative x-axis, in the Cartesian form. Now talking about polar form. Okay, -1, 0 can also be located on -1, 0 can also be located on unit circle. If I draw a circle passing through the -1, 0 and center at origin, okay, this becomes my unit circle. Okay, because the radius will be 1 since it is passing from -1, 0. Okay, and -1, 0 is also found on the unit circle. Okay, so what I'm telling, two things are important here. Number one, when the Nyquist plot crosses the negative real axis, that is omega p. When the Nyquist plot crosses this unit circle, okay, that will be omega g. Now, earlier I was talking about changing the magnitude of the system. Can I increase the gain of the system? Yes, you can increase it up to a point so that it remains to be stable. And that margin by which you can increase was the gain margin. Now, can you change the phase? So this particular point when you join from origin, this particular point when you join with respect to origin, this point -1/2, 0, let me write it here separately. Suppose I have assumed this point to be -1, 0. Now, when I join this point with respect to origin, it will have some phase. Okay, it will have some phase. Okay. Okay, let me write down that phase actually separately. See here, the next calculation. Let's talk about in this side. Okay. So at this particular point, the system will have some phase. Okay, the system will have some phase. Okay, let us say this is the phase. I have taken clockwise phase right now. So we know that whatever is the value will be placed with a minus sign. Okay, minus sign, correct. Right, so the phase has to be clockwise. The phase has been taken as clockwise. This point has a phase. Now, can I change the phase of the polar plot? If you change the phase of the polar plot, suppose you change it by sometime something, but if you keep changing the phase, there will come a point if you keep changing the phase where again this Nyquist plot is going to cross through, the -1, 0 and which will be equal to the case number 2. The system will become marginally stable, and if you change the phase beyond it, it will become unstable. So the point is, I have a stable system. Okay, I have the stable system. Okay, say for example, the value of the phase is 150. The magnitude of the phase is 150 degree. So actual phase is -150 degree because it is clockwise. Okay, by how much can you change the phase? So dear, if this is 150 degree, how much is this much of the remaining angle? 30 degree. Okay, so can you change the phase of the system? Yes, you can change the phase of the system. By how much? Not more than 30 degree. Because if you change by 30 degree, you come to the case number 2, marginally stable. If you change it beyond 30 degree, system is going to go to the unstable zone. Okay, by what margin you can change the phase? Okay, that will be known as phase margin, and that is 30 degree. 30 degree can be exactly written as 180 plus of this -150, and that will give you the phase margin formula. Clear? So phase margin, first I need the omega g point, the gain crossover frequency. Okay, what is the gain crossover frequency? When the Nyquist plot crosses the unit circle. So listen to this definition. What is the gain crossover frequency? It is the frequency at which Nyquist plot intersects the unit circle. That means at this frequency, the magnitude should be equal to 1. Unit circle, how much is the radius? How much is the distance from origin? Okay, 1 unit. So again, to calculate omega g, you don't have to draw the Nyquist plot. Given GSHS, take mod gj omega hj omega, put it equal to 1. Mod gj omega hj omega equal to 1 is the gain crossover frequency. Okay, the solution of this will give you the gain crossover frequency. Then, what is a phase margin? As I just told you, phase margin is 180 degree plus this particular face opted. That much is the margin in your hand. Okay, so that is the face margin. Okay, the margin by which face of a stable system can be changed before it reaches the point of instability, and it is given by the formula standard unit in degrees 180 degree plus angle Gj omega g at j omega g. These are the phase margin formula. This is the phase margin formula, correct? Because stability depends on -1, 0, na, Sajin? Okay, stability depends on number of encirclements of -1, 0, na? That is why -1, 0 is the standard for us. That is why -1, 0 is the standard for us. That is why -1, 0 is standard for us. That is why -1, 0 is standard for us, correct? Okay, next. Let's move ahead to the next. Okay, let's take up a question here actually. Let's take up a question here actually. Okay. Some important key points. Okay. For a stable system, okay, gain margin and phase margin both are positive. Like phase margin 30 degree, positive. Gain margin 6 decibel, positive. For a stable system, both are positive. For unstable system, both will be negative, and for marginally stable system, both will be 0. That means they are always of the same sign. It will never happen one positive, one negative, okay? It will never happen that one is positive, one is negative. Okay, both are positive. Gain margin means decibel gain margin, be very clear. And phase margin means degrees. Okay, so for stability, both are positive. For, unstable, both are negative. For marginally stable, both are 0. Okay, then this is the comparison. Two systems having the gain margin. The one which has more phase margin is more stable because they are the quantity of stability. More means more stability. If two systems have similar phase margin, then the one having more gain margin is more stable. And this is also some connection to quickly comment on some of the answers. Whenever omega g less than omega p, system will be stable, as you can see in our current example also. Okay, see, this is 0 plus. This is our polar plot which started from 0 plus and went to diving frequency infinity plus. So from 0 to infinity, what comes first? Omega g. Then what comes? Omega p. Okay, so omega g coming before omega p was the stable case. So let's highlight these important results also, generally true. Okay, so what are these important results? What happened? Yeah, here it is. Okay, omega g less than omega p stable. If they are equal, marginally stable. Omega g greater than omega p unstable. Okay. Now dear, the first question, okay, that I have taken is, okay, will be solved directly without using the formulas of gain margin, phase margin. Why? Because the GSHS is given as 7.5 upon S, 1 plus 0.2 S, 1 plus 0.4 S, clear? 7.5 upon S, 1 plus 0.2 S, 1 plus 0.4 S. Determine the omega p and the gain margin, and then the omega g and the phase margin. These are the things to be taken. But this is again of the standard format, and one result I have always asked you to remember. K upon S, 1 plus ST1, 1 plus ST2. Remember, so for this we know the omega p directly. This is the important form. For this, omega p was given by 1 upon root T1 T2. Clear na? Omega p was given by 1 upon root T1 T2. Okay, 1 upon root T1 T2. So what is omega p? 1 upon root T1. 0.2 into 0.4. Okay, T1 and T2 are multiplied here. Okay, 3.54 approximately. 3.54 radian per second. Okay. Then at omega p, how much is the magnitude? At omega p, how much is, once I think last year only, GATE 2023, there was a question only on the formula of this form. Given the GSHS K upon S, 1 plus ST1, 1 plus ST2, what is the omega p formula? Okay, 1 upon root T1 T2. Direct formula question, it was for 1 mark. Okay, and not only that, I'm telling you, the questions around this particular function are important. So you are remembering only one polar plot, rest we will solve. Okay, now at this omega p, what is the value of the magnitude? At omega p, We know that the magnitude was given by what formula? The magnitude was given by the formula k T1 T2 upon T1 plus T2. Remember? At omega p, the magnitude, this magnitude which I am talking about, at omega p, this was the magnitude given, correct? K T1 T2 upon T1 plus T2. So what is that magnitude here? Okay, what is that magnitude here? So K is 7.5 and T1, T2 0.2 into 0.4 respectively. So divided by 0.2 plus 0.4, and solving it, you will get it magnitude equal to 1. You will get the magnitude equal to 1. You will calculate this, you will get the magnitude equal to 1. Okay, so what is the gain margin, dear? Now listen, what is going to be the gain margin? Gain margin is given by the formula in decibel. I will calculate generally 20 log 1 upon mod Gj omega p Hj omega p. Okay, to calculate gain margin, I need the magnitude at phase crossover frequency, which has been calculated already. Okay, that is 1, and log 1, 0 dB. Now, that solves your complete question actually. That solves your complete question. Why? Why? Because gain margin equal to 0 dB indicates a marginally stable system. Okay, and since the system is marginally stable, so phase margin will also be 0. I told you for marginally stable, both will be 0. The phase margin will also be 0, and omega g also not to be calculated. Omega g and omega p are same. So those conclusions, there will be important for you. So omega g and omega p same, that is 3.54 radian per second. That is a 3.54 radian per second. That is going to be the omega g and omega p. 3.54 radian per second. 3.54 radian per second, right? That is going to be the omega g and omega p. Okay, so second question is sort of done using the first question only. Okay, using the first question only. Next question. Determine the phase crossover frequency and gain margin. Open loop transfer function given. Please attempt this and answer me. Please attempt this and answer me quickly. Okay. Let's do it. Let's do it here. Okay, so phase crossover frequency and gain margin. Let's convert it to the frequency domain function first. Okay, Gj omega. Okay, 100 upon 1 plus j omega whole cube, and write down the magnitude and phase. Okay, let me start with the phase expression, since first we need to calculate omega p. Numerator is positive real number. Okay, for denominator, tan inverse omega 1 plus j omega, but that is a factor 3 times. So tan inverse omega 3 times, and denominator means minus, so minus 3 tan inverse omega. Okay, so at omega p, what I want? At omega p, we know that the phase is either plus or minus 180. Let me choose minus 180. Okay, so that the minus would be cancelled. So at omega p, that is minus 3 tan inverse of omega p will be minus of 180 degree. Okay, so what is omega p? 3 cancel with 180. So tan you shift on the right side, tan of 60 degree, and that is equal to root 3. That is equal to the root 3. Okay, so omega p is equal to the root 3. Is that clear? Omega p is equal to the root 3. Clear? So that is the omega p obtained. If they only ask omega p, sometimes they only ask omega p also. Okay, now coming to the mod Gj omega. For gain margin, I need the mod Gj omega first. So what is the general magnitude? 100 is divided by 1 plus j omega. 1 plus j omega magnitude is root over 1 plus omega square whole cube, or I can write it this way also. 100 upon 1 plus omega square raised to the power of 3 by 2. Raised to the power of 3 by 2. Okay. So at omega p, how much is the magnitude? At omega p equal to root 3. Okay. This magnitude, which will be known as mod of Gj omega p, is 100 upon 1 plus omega square. Omega is root 3. So root 3 square 3. So 1 plus 3 power 3 by 2. Okay, so 4 power 3 by 2. The 4 cube is 64 and under root will become 8. Okay, so what is the gain margin? Gain margin, dear, is 20 log 1 upon mod Gj omega p. Okay, or I can write it as 20 log over 8 by 100. Okay, so 20 log 8, 2 power 3, 6, 6, 6, 18. 18 minus 22 is 40, minus 22 decibel. 22 decibel. 22 decibel. Okay. Yeah, let's keep going. Let's see how long you and we go. Okay. So minus 22 decibel, meaning what? Negative. Gain margin negative means the system has to be unstable. Even if you check by any other methods like RH and all, it has to be unstable. It has to be unstable. Clear? Okay, so gain margin is negative, meaning the system is unstable. Let's move ahead to the next question. Clear? Let's move ahead to the next question. Achha, remember, see, actually all these calculations many a times are mind calculations. Always remember, a tip from my side, always remember, because gain margin, or especially when you go to Bode plots also, log calculations are very common, and in other subjects also. Log, when you talk about log to the base 10, common log, okay, just remember 20 log 2 is 6 dB. 20 log 2, that one value should be fixed in the mind. The 20 log to 6 dB. That is where I wanted, and also remember one more thing. When you take log to the base 10, the log of any 10 power k will be simply k. Okay, so that is where, these calculations came in mind only. I wanted log 8 by 100. What I did simply 20 log 8 minus 20 log 100. Okay, and log 8. 8 is what? 2 cube. 8 is 2 cube. And log of 100 is 10 square. So that is where 3 comes outside, 20 log 2 is 6. Power will come always outside, na? And log of 10 square is 2, and that is how I got my answer as minus 22. Just showing you the calculation so that you can also use this in the exams. Okay. Especially gain margin, Bode plots, these calculations are useful. Okay, log to the base 10, 20 log 2 will be 6, and log of 10 power k will be k. Okay. Correct, dear. Okay, moving ahead to the next calculation. Here it is. The open loop transfer function of a unity negative feedback control system is given to you. K upon S, S plus 3. velocity error constant kV is 1.054, then what is the phase margin? We know about velocity error constant. Okay, the question is kV given, what should be the value of the phase margin of the system in degrees? Okay, so this one is the next question on the phase margin. This one is the next question on the phase margin. Clear, everyone? This one is the next question on the... Let's start it. Let's start it. So first of all, kV. Let me start with the kV information. What is the kV? kV is given by limit of s tending to 0, s into gs. Na? We studied it today, velocity error coefficient, we revised that also. Okay, limit s tending to 0, s into gs. So ss cancel. Okay, and then s tending to 0, k by 3. And this is 1.054. So what is the k? It's going to be how much? Let's multiply this as... So that is 3.16 roughly. K is 3.16. K is 3.16. Okay, that is clear. Now, what is the phase margin? For phase margin, the phase margin is calculated at the omega g. The phase margin is calculated at the omega g. Okay, the phase margin is calculated at omega g. Let us see what is the value of omega g. Let us see what is the value of omega g. Okay, so let me convert this function into gj omega, frequency domain. Okay, gj omega is k upon s plus 3, k upon j omega into j omega plus 3. J omega plus 3. Okay, now omega g. Okay, omega g is the point where mod gj omega should be equivalent to 1. Mod gj omega should be equivalent to 1. Okay, so mod gj omega, acha, what is 3? What is k? Is 3.16. That is also calculated. Okay, so now magnitude means 3.16. Okay, upon 3.16 upon j omega magnitude omega, and for j omega plus 3 root over omega square plus 3 square. This should be equal to 1. Okay, so do the square on both the sides. 3.16 square, right side is omega square, and this is at omega g. So let me say the omega is omega g. So omega g square into under root cancel to omega g square plus 9, and 3.16 is roughly root 10. The 3.16 square means 10. Okay, and for simplicity, let x be omega g square so that you get a quadratic equation, not a fourth power equation. So this is x into x square, and then plus 9 into x. Okay, so what I am getting is x square plus 9x minus 10 equal to 0. Factorizing it would be giving me x plus of 10, x minus of 1 equal to 0, and x would be minus 10 and plus 1. X would be the minus 10 and plus 1. Okay, but x, which is how much? X is actually omega square, so it cannot be negative. Frequency cannot be imaginary. Okay, so hence negative solution not acceptable. Omega g square is 1, so omega g also equal to the 1. Okay, the gain crossover frequency obtained is 1. Okay, is 1. Okay, it is equal to 1. Correct. Now, what is the phase margin? For phase margin, I first need a phase expression. Okay, so what is the phase expression? Okay, what is the angle gj omega expression? Okay, what is the angle gj omega expression? The angle gj omega will be, numerator is positive real number, first term denominator pure imaginary, so 90 degree, and again minus tan inverse omega by 3. Minus tan inverse omega by 3. Okay, so at omega g, how much is the angle? What is the omega g obtained is 1. Omega g obtained is 1. How much is this angle? Minus 90 minus tan inverse 1 by 3. Let's do it. Tan inverse 1 by 3. Minus 108. Minus 108.43 degree. So what is the phase margin? Phase margin given by what formula? 180 degree. Phase margin given by what formula? 180 degree plus angle gj omega g hj omega g, and that is calculated as minus of 108.43 degree, and that becomes how much? 72 or 71.57 degree. That is the final answer. 71.57 degree is the final phase margin answer if they finally calculate the phase margin of the system, right? So what is the phase margin? Let me enter the answer here. It is 71.57 in degrees, 71.57 in degrees, 71.57. 71.57. Okay, 71.57. Next. Okay, the phase margin of the system with the open loop transfer function. Okay, open loop transfer function. Okay, the phase margin for the open loop transfer function, 1 minus s upon 1 plus s, 2 plus s. Okay, 1 minus s into 1 upon 1 plus s, 2 plus s. It can be, but not as a conclusion. Yes, it can be infinite, but it's not a conclusion that for type 1 order 2 it has to be infinite. Okay, it has to be infinite. If all the magnitudes are lesser than 1, okay, phase margin can be infinite. See, that's what you're going to get here, and as important remarks I will make with this question. The phase margin of the system with the open loop transfer function, 1 minus s upon 1 plus s, okay, 2 plus s. So when you convert it into the frequency domain, gj omega hj omega, you are getting it as 1 minus j omega upon 1 plus j omega into 2 plus j omega. Correct? Okay, so when you talk about the magnitude function, especially mod gj omega hj omega, magnitude 1 minus j omega 1 plus j omega, magnitude wise it is the same because minus omega square or omega square same. So root over 1 plus omega square, again root over 1 plus omega square into root over 4 plus omega square. So root over 1 plus omega square will be cancelled and the magnitude will be 1 upon root over of 4 plus omega square. Clear? This is what is the magnitude term. Okay. Now, see here, if I talk about omega g calculation, what should happen? Okay. At omega g, I want this magnitude equal to 1. So, magnitude 1 upon under root of 4 plus omega g square equal to 1, which means that 4 plus omega g square should also be 1, which means that omega g square is minus 3. Okay. Omega g square minus 3, and this equation cannot have any real solution. Because square under root of minus 3 is imaginary. You cannot have a real solution to this. That means no omega g will exist. No real solution. That means this system does not have gain crossover frequency. And actually, if you see, I will write down the conclusion, just giving you a small hint. Magnitude is 1 upon root 4 plus omega g square. And the minimum value of the omega g square, it is square function, na? Minimum value 0. So 1 upon root 4, 1 upon 2 magnitude is 1 by 2. And if omega will increase, omega g square will increase and magnitude will decrease only. Okay, so all the magnitudes will be lesser than 1. Actually lesser than half also. But what I want is all magnitudes are less than 1. Okay, that means entire polar plot, if you want to draw, no need here. But the entire polar plot, if you want to draw, is always inside unit circle, because unit circle, to touch unit circle, you should have the magnitude equal to 1 at some point. That is why I don't get any omega g. Entire polar plot inside unit circle. Okay, no omega g. Okay, there is no omega g. And what about the phase margin? Phase margin in such a case is infinite, because if it is inside unit circle, what is phase margin? The margin by which you rotate till it touches minus 1 comma 0. Then only it will go beyond it. Na? Okay, so it will never touch minus 1 comma 0. It will never touch minus 1 comma 0. Are you getting it? The phase margin of it is infinity. The phase margin of the system is going to be infinite. Okay, just a second. Correct. The phase margin of it is going to be infinite. Okay, remember some special points I will mention here. Some special points I will mention here. Some special points I'll mention here. Number 1, if there is no real omega g, meaning no omega g, Okay, phase margin turns out to be infinite. Similarly, if omega p turns out to be infinite. Okay, omega p turns out to be infinite, and infinite means diving frequency actually. Okay, infinite means diving frequency. Magnitude will be 0 because it is the diving case, and magnitude 0, gain margin will be infinity. In such case, gain margin will be infinity because this is the diving case. This is known as the diving case. And number three, if omega p equal to 0, that is the starting case of the polar plot, theta st case. Okay, precaution, this is an important precaution. Okay, don't trust the gain margin formula. So gain margin formula has a limitation. It can fail if omega p equal to 0. Okay, it can fail if omega p is 0. So if you don't trust gain margin, and if there is a question of gain margin, okay, you have to solve it by characteristic equation or by drawing the polar plot. If it is a lower order system, you can directly solve by characteristic equation, or you can draw the polar plot and see how the gain margin is, the margin by which you can amplify the gain before it reaches the point of instability. Okay, that is what is the important discussion to be done here. Don't trust. I don't say it's not applicable, but mostly not applicable. So this is one case where GM formula, gain margin formula, may fail, and that is when the omega p turns out to be only 0. There is no other value of omega p coming out, but it is only coming out to be, what? It is only coming out to be 0. Clear? It is only coming out to be 0. Right? Just a second. Okay, chalo guys, next question then. For the unity feedback system, GSHS equal to involving an exponential function 10 e power minus st upon s 1 plus 0.1 s, determine the range of t for the system to be stable. Okay, determine the range of t for the system to be stable involving exponential function. Normally range of k for stability, we go by RH also. Okay, but whenever there is the exponential term, okay, the exponential lag term, even if you want to go for RH is for polynomial. You will have to expand by Taylor series, and that will be giving you an approximate but a lengthy answer. What we will do is, okay, using, whenever there is the exponential term e power minus t, okay, which is also known as the lag term because it is like a delay term. Okay, transportation lag or a delay element. Okay, time delay element. Okay, we usually prefer its analysis by, okay, Bode plots, okay, or just go for the phase margin calculation, PMGM. Prefer the phase margin calculation. Okay, because this is something that is not going to affect the gain crossover frequency. Why it will not affect the gain crossover frequency? If I convert to the frequency domain function Gj omega 10 e raised to the power minus j omega t upon j omega 1 plus 0.1 plus 0.1 j omega 1 plus 0.1 j omega, correct? 10 e power minus j omega t. So when you write down the magnitude of it, see the magnitude. Okay, see the magnitude. 10 e power j theta magnitude is 1. Okay, that will not come in the magnitude function. J omega magnitude omega, and for the other term 1 plus root over x square plus y square, that is root over 1 plus 0.01 omega square. And what about the phase function? Okay, what about the phase function? The angle function, the phase function will be angle Gj omega. For e power j theta, theta is the phase. Theta is the phase. But when you write down theta, remember that theta is in radian, normally standard unit. Okay, so when you write down the phase of denominator j omega, we normally write 90 degree. But since theta is in radian, either convert radian to degree or degree to radian. So better let me write this 90 degree as pi by 2, that is easier. And then tan inverse 0.1 omega. Tan inverse 0.1 omega, tan inverse y by x. Okay. So this t is actually coming in the angle expression, and hence it will change. It will try to decrease the phase margin of the system. It will try to decrease the phase margin of the system. What is the phase margin formula? What is the phase margin formula? 180 degree, or let me write down everything in terms of radian. Pi plus angle Gj omega J Hj omega G, correct? Okay, so the phase margin of the system will be pi plus of the expression that I have written, minus omega t minus pi by 2 minus tan inverse 0.1 omega. Okay, so what is the final phase margin? Pi minus pi by 2 is pi by 2 minus tan inverse 0.1 omega minus omega t. If the t was 0, if the t is 0, then this is the phase margin. So what is the role of t? Okay, the t is going to reduce the phase margin of the system. Okay, more the time delay value, more is the reduced phase margin. Okay, now to calculate phase margin, I should have omega g. I should have omega g. Okay, what is the value of omega g? First of all, omega g. Okay, means I have to take the mod Gj omega Hj omega equal to 1. What is the magnitude function? 10 upon, this value I will copy. It will be 10 upon omega square, upon omega under root 1 plus 0.01 omega square. This is equal to 1. So solving, taking the square, 100 equal to omega g square. I am calculating at omega g 1 plus 0.01 omega g square. Okay, again I will put omega g square equal to x. So 0.01 omega g square, that is x square. Okay, plus x minus 100 equal to 0, or x square multiplying by 100, x square plus 100x minus 100 square, that is 10,000 equal to 0. So what is x from here? Let me directly give you the calculations, dear. You can do it quadratic formula. Okay, so you can calculate, you know the formula for quadratic equation, not a big deal. Let me write down the answers right now directly. 61.8 and minus 161.8. 61.8 and minus 161.8, and again same thing, it cannot be negative because omega g square cannot be negative. So omega g square is 61.8 and under root of it will be final answer 7.86. 7.86 radian per second. Omega g is 7.86 radian per second. Clear? Now what is the phase margin then? Okay, now substituting in the phase margin, as I told you, pi by 2 minus tan inverse 0.1 into the frequency. This expression, I am using this expression. Pi by 2 minus tan inverse 0.1 omega minus omega t. Minus omega t. And what is the omega obtained? 7.86 into t. Okay, so how much is this value? When you are calculating this tan inverse value, you have to give me the answer in radian. Everything is in radian right now. Everything is in radian right now. Okay, so writing down the answer completely and then subtracting from pi by 2. Okay, so this is the phase margin turning out to be 0.904 minus 7.86 t, and you want the system to be stable, range of t for stability, phase margin has to be positive. So 0.904 minus 7.86 t must be positive, giving you the value of t, okay, dividing by 7.86, 0.115. So t less than 0.115 is the correct answer. T less than 0.115 is the correct answer. The t has to be less than 0.115 and that is the correct answer. Right? That is how we deal with the transportation lag or exponential delay term. Transportation lag or exponential delay term. Clear, everybody? Clear, everybody? Okay. Put down any doubts if you have. And guys, time for another next topic. Okay, we have discussed about omega g, omega p, and including some questions. I'm trying to include a question also. Again, guys, reminder that, The next online course for GATE 26 and GATE 27 is coming up for you on the 8th of February. It's coming up for you on the 8th of February. Okay, and yes, if you enroll till 30th of January, you have additional 25% early bird discount. Okay, for the online courses. Okay, for the online courses. Come on, lot of slides in the PPT today. Yesterday, that's what, till late night I was preparing the content for you so that we revise efficiently and a lot of things in the limited amount of time. That is how I targeted. That is how I have targeted. Oh, just a second here. I think that is lost right now. Just a second. This is already done. Polar plot and all is done. It is again stopping at polar plot. Just a moment. Okay, yeah, let me stop here. Okay, we'll go for a small break right now. We'll go for a small break right now. Okay, we are going for a small break right now. Just allow me 5 to 10 minutes. Yes, you want to continue more? First tell me. Okay, small break for roughly 10 minutes, and so that we resume at 5:20 p.m. Approximately we'll resume at 5:20 p.m. Okay, we'll approximately resume at the 5:20 p.m. Yes, we want to continue. Energy is there. Energy is there. Password. Take the password margin. I will write down after the break. Gain margin, face margin we completed. Na? I will keep the password as margin. MARGIN, everything in small. I will write down. Let me come after the break. So allow me 5-10 minutes of time and we'll continue. Let me have a quick deep breath. But it's evening and I'm continuing, so I want the attendance. I want the attendance. Don't think you will watch later. I will stop if the attendance is not there because it's evening. We are continuing in morning non-stop, okay? Right. 10 minutes we'll start. Okay, ready once again? Ready to run the marathon more? Let me actually see. Are you ready to run the marathon more? Evening break is also done. We are running this marathon, say from morning 10 a.m. or so. 10:15 we started and we are running non-stop, and that is what marathon will mean. Okay, marathon will mean. Okay, so let me see how many of you want to run more and more. Yes, good evening everyone. Good evening Avinash. Good evening, keep continuing. Let's see what is the next thing that we need to take up. Let's see what is the next term that we need to take up. Yes guys, keep on sharing the session, and as I told you, tomorrow let's also try to plan the MSQ session only from control system. Okay, so that's what, you know, I'll just get free and I'll update you. I'll just get free, I'll update you, you know, at what time and how I can plan the marathon. That is why, you know, if you're not subscribed, okay, do subscribe to the channel. Okay, so that, you know, any sessions that I'm planning, you know, immediately also, randomly also, you should be aware about all those sessions. Okay, you should be aware about all those sessions. So yes, let's continue our run, and let's move ahead. Yes, so as per the demand that I was seeing during the lunchtime also, as per what many of you are demanding, stop, and the topic immediately after the break is the root locus, coming up to the root locus. Okay, the locus of the roots of characteristic equation, because, you know, we have been seeing, just like, you know, if I go to one of the RH problem once again, you know, especially that frequency of oscillation case that we did in the morning. Okay, what we clearly saw that as the value of k will change, okay, the range of stability will keep off varying. Okay, when k is 0 to 1.49, okay, when k is between 0 to 1.49, system is stable. For k greater than 1.49, system is unstable. For k equal to 1.49, system is marginally stable. That means j omega roots. Okay, that means j omega roots. So the roots of characteristic equation will keep on varying with respect to k. Okay, here stable means all LHP roots. Okay, for k greater than 1.49, 2 RHP roots. So for different values of k, the roots of characteristic equation will keep on varying. Okay, the roots of characteristic equation will keep on varying here. Okay, and that is why we draw the diagram, that is the locus of the roots of the characteristic equation. Okay, when the gain parameter k is varied from 0 to infinity. Okay, when the gain parameter k is varied from 0 to infinity. Okay, although it can also be taken from minus infinity to 0, that will be known as complementary root locus when the gain is varied in the negative direction, minus infinity to 0, and the complete range of the k, when we see the complete root locus varying the k from minus infinite to infinite, that is the combination of root locus and complementary root locus is root loci. And when some other parameter other than the gain k parameter is varied or multiple parameters is varied, we refer to it as the root contour case. Now let us first quickly revise the steps and important highlights about the root locus plot. Okay, root locus is always going to be symmetric with respect to real axis because of complex conjugate poles. If there is a complex pole, it will always occur with a conjugate pair, and because of that, root locus, because it is the locus of roots of characteristic equation, it will always be symmetric with respect to x-axis. If there is x plus jy, below x minus jy will always be there. So above and below will always be symmetric because of complex conjugate roots occurring. Now, very important point is any point lying on the root locus will satisfy characteristic equation, because what root locus is? In a simple way, what you are plotting in the root locus? Okay, the root locus is, okay, is showing you a graph which will show you the variation of roots of characteristic equation versus k. Okay, which will show you the variation of the roots of characteristic equation versus k. Okay, so like suppose if you have a parabola y equal to x square, any point lying on the parabola will satisfy the definition of parabola. Similarly, any point lying on the root locus will satisfy the definition of root locus, and root locus is a plot of what? Roots of characteristic equation. So any point lying on the root locus, okay, will satisfy the characteristic equation. Okay, that is 1 plus GSHS equal to 0. You have questions based out of this only. Sometimes you have the questions based only out of this. Okay, so characteristic equation 1 plus GSHS equal to 0, or GSHS is minus 1. And if GSHS is minus 1, if I say that the GSHS is minus 1, so mod GSHS will be equal to 1. The magnitude of it will be equal to 1. Mod GSHS will be 1. And minus 1 lies on the negative real axis. So if you want to take the face of this point, okay, negative real axis, if you want to take the face out of this point, it is 180. Or even if you go clockwise, it is minus 180 degree. So the face is plus or minus 180 degree. The plus or minus 180 degree, or any odd multiple of 180 degree will work here. Okay, so for a point lying on the negative real axis, we can have the angle criteria plus minus 180 degree or odd multiple of 180 degree. Okay, the gain, the constant gain k parameter in the open loop transfer function, Sajin. Okay, now the steps to talk about the root locus. See, some steps are very basic, just like formality. You can say that how many branches root locus will have. Okay, the number of branches of root locus should be equal to order of characteristic equation. See, root locus is locus of roots of characteristic equation. The order of characteristic equation will determine how many roots, and we need one branch for every root. That is why number of branches is the order of characteristic equation, which is finally given by, okay, n equal to max of p comma z. Okay, p and z meaning the same as I told you earlier also. P is the number of open loop poles, z is the number of open loop zeros. I have written it here once again. P and z, the number of open loop poles, the number of open loop zeros. We have talked about p and z earlier also when we were talking about polar plot. Okay, so n is given by max of p comma z. Where will the root locus always start? Start means k equal to 0, because root locus is the variation for k equal to 0 to infinity. So starting for k equal to 0, the root locus will always start from the open loop poles. Termination k equal to infinity, the root locus will terminate either at the open loop zeros, or if open loop zeros are less or not available, then those root locus branches will go towards infinity. Okay, will go towards infinity. Okay, now let me keep relating it with respect to an example also, so that you know one by one directly a question you understand. Okay, let's not derive these steps. Okay, let's have a quick revision and go to the miscellaneous question. So, okay, take one question here. Take one question here, or let me just brief you the steps, then I'll go to the question, not a matter here. Okay, so the root locus branches will terminate at the open loop zeros, or if open loop zeros are not available, they will terminate at infinity. And if any branch is going towards infinity, it will be approximated by, it has to be approximated by asymptotes. Okay, it will be approximated by asymptotic lines. Okay, now what are asymptotes of the root locus? How many asymptotes? Okay, so you know some branches started from open loop poles. Okay, if the number of zeros are not available, what is the difference between p and z? Suppose there are 3 branches. Okay, and there is only, suppose there are 3 poles and 1 open loop zero. So maximum is 3, number of branches will be 3. 3 branches will start, but only one of them can terminate at the 0. How many will go towards infinity? 2 branches will go towards infinity. So 2 asymptotes will be required. So what is the number of asymptotes? It is the difference between these 2 numbers. Okay, it is the difference between these 2 numbers. So first, okay, what is the number of asymptotes? What is the number of asymptotes? It is given by the formula p minus z. Basically the number of branches going towards infinity, that many asymptotes are required. Okay, that many asymptotes are required. Angle of asymptotes with the real axis. What is the angle of asymptotes? So now you know how many asymptotes, from where they will start, and what is the angle they will make with the x-axis. So angle of asymptote will be given by 2k plus 1 by n into 180 degree, or remember this way better. 2k plus 1 odd multiple of 180 degree by n. 180 divide by n number of, divide equally by n number of asymptotes and take the odd multiples of this calculation. Take the odd multiple of this calculation. Odd multiple of 180 degree by n. How many angles? Based on number of asymptotes. So k is 0 to n minus 1. Total n angles will be required. Intersection of asymptotes on the real axis, which is also known as centroid. Okay, it is given by the formula summation of poles minus summation of zeros upon P minus Z. Summation of poles minus summation of zeros upon P minus Z. Upon P minus Z. Now dear, sometimes if you are only interested in a rough sketch of the polar plot, okay, without any detailed calculation, you can do it very basically. Okay, suppose I give you a function, okay, where I only want a rough sketch. So now before showing you the next step, let me jump to a question, let me do the rough analysis, and if detailed calculation required, I will come and do it. Okay. But before that, let us come to this. Sketch the root locus of the system having this open loop transfer function. Okay, having the open loop transfer function k upon s, s plus 1, s plus 3. Okay, so basically let me write down the open loop poles. Okay, let me write down what are the open loop poles here. What are the open loop poles? Open loop poles are s equal to 0, minus 1 and minus 3. These are the open loop poles. Clear? Okay, how many open loop poles? 3. What are the open loop zeros? Okay, no, there are nil. No open loop zeros. Okay, so z equal to 0. How many open loop zeros? Nothing. So z equal to 0. Okay, z equal to 0. So how many branches will be there? 3 branches will be there. Number of branches will be definitely 3 here. Okay, starting at all the branches. Okay, they start at open loop poles. Okay, they will start at 0, minus 1 and minus 3, and the branches ends at, ends means k tending to infinity at open loop zeros or at infinity. Do you have any open loop zero here? No, you don't have any open loop zero. The branches will end towards infinity. See, how many branches going towards infinity? 3 branches. So that is why we need 3 asymptotes. Okay, that is why we need 3 asymptotes. 3 infinities, so we need 3 asymptotes. That is what? Number of asymptotes, as I already told you, given by the formula P minus Z. Okay, P minus Z. Clear? Now, where will the asymptotes intersect on the x-axis? What is the centroid of the problem? What is the centroid of the problem? The centroid, as I told you, given by the formula summation of poles minus summation of zeros divided by P minus Z. So x is given by the formula 0 and minus 1 and minus 3. Zeros are not available, so that's blank, and P minus Z. So this centroid becomes minus of 4 by 3. This centroid becomes minus of 4 by 3, minus 1.33. The centroid value is minus 1.33. Clear? That is the centroid problem. Now the theta, okay, the angle of asymptotes. What is the angle of asymptote? So I told you theta is given by 2k plus 1. That is odd multiple of 180 degree divided by n. N is 3 here. 3 asymptotes are required. That means odd multiple of 60 degree. What are the odd multiples of 60? Okay. First odd multiple 60 into 1. Next odd multiple 60 into 3. Next odd multiple 60 into 5. So first 3 odd multiples 1, 3, 5. These are the 3 odd multiples. So 60, 180 and 300. Okay, 60, 180, 300 also equal to 60, 180 and minus 60 degree. 300 degree is equal to minus 60 degree if you go clockwise. Anti-clockwise you go 300, smaller angle will be 60 degree. Clockwise, so minus 60. Okay, now up to this much if I have to draw a rough polar plot. Up to this much if I have to draw a rough polar plot. See, I just want to right now draw a rough polar plot based on this much results. Okay, if the details are not required, if you only want to get the shape of the polar root locus, if I just want to get the rough shape of the root locus. Okay, see, the root locus will always start from the open loop poles. Okay, what are my poles? My poles are at 0. My poles, next pole is at minus 1. Minus 3. Clear? What are the asymptotes? Okay, the asymptotes, okay, are having the angle 60, 180, minus 60. 3 asymptotes are there, all starting at minus 1.33. All of them starting at minus 1.33. Okay, so let's say this is minus 1.33. Okay, so the first asymptote, okay, will be at 60 degree. So roughly a 60 degree line. Okay, then next asymptote roughly means this angle should be 60 degree basically. This angle should be 60 degree. Next asymptote 180 degree. 180 degree means towards negative real axis. And next is minus 60 degree. Minus 60. Minus means clockwise 60 degree. That will be symmetric. This is 60 this side and this is 60 the other side. These are the asymptotes. Now dear, where will the root locus branches start? The root locus branches will start from the open loop poles. Okay, the root locus branches will start from open loop pole. This is one open loop pole. This is the next open loop pole. Now understand the next step of the root locus. Okay, the root locus branches will start from open loop pole. But if a root locus branch has to start here, where? Should you start right? Should you start left? Should you start right? Should you start left? Okay, should you start right or should you start left? So for that we have the odd number criteria. We have the odd number criteria. Now listen, what is the odd number criteria? Okay, what is odd number criteria? Okay, the root locus will exist on what part of the real axis? The root locus, now suppose real axis is broken into different parts. This is one part. At every pole, I'll break the real axis. Real axis this much part, real axis this much part, real axis this much part, real axis this much part. Okay, the root locus, I will show you the step right now. Listen to me orally. The root locus will exist on the section of real axis if the total number of poles and zeros towards the right, if the total number of poles and zeros towards the right is an odd number. Let me call it as forward poles and zeros. When suppose you are sitting here and you see in the forward direction, the forward poles and zeros total count should be an odd number. Okay, so how many forward poles and zeros from here? 1, 2, 3. 3 is an odd number. From here, how many forward poles and zeros? 1 and 2. 2 is an even number. If you are sitting here, how many forward poles and zeros? 1, odd number. If you are sitting here, how many forward poles and zeros? 0. That will be counted in even case. You want the forward poles and zeros to be odd, 1 or 3 or 5, like that. Okay, so where will the root locus exist on the real axis? Where will the root locus exist on the real axis? Where you have the odd numbers. Okay, that is to the left of minus 3 and between minus 1 and origin. Between minus 1 and origin. Okay, so let me only now take up the tick mark portion. Okay, so let me take up the tick mark portion. The root locus will exist where? It will exist between the minus 1 to 0. Okay, this is one case. And then to the left of minus 3. On the real axis, it can only exist on this part. Odd number criteria. Odd number criteria. So that is what, dear, the branch which will be starting from the open loop pole minus 3 is just going to go left. Okay, left and towards the asymptote. Yes, it is going to go towards asymptote. The second asymptote is at 180 degree. Okay, but the branch which is starting from minus 1. Now the next important point. The branch which is starting from minus 1. It has to start left or right. So only orange zone. It has to start right. Forward poles and zeros, odd number criteria. So from the minus 1, the branch is starting to the right, and from the origin, branch is starting to the left. And what is happening? One branch is starting to the right, one is starting to the left. So two branches, the picture is now two branches traveling in the opposite direction. Two branches are traveling in the opposite direction, so they will intersect. Two branches are traveling in the opposite direction, they will intersect. They have to intersect, correct? Two branches traveling in the opposite direction, they have to intersect. That means an intersection, a clash, a collision will happen here. That will be defined as the breakaway point. Okay, breakaway point. When two branches traveling on the real axis, they intersect and then travel to the complex plane. There can be break-in also, I will say, but without calculating breakaway point, first let me complete the shape. Okay, so because two branches are traveling in the opposite direction, okay, at some point they will intersect. At some point we know they will intersect. Na? Let them intersect. That point I will tell you later. But if it is not required, if I can manage with the shape right now, then what will happen? The branches on the real axis will intersect and then travel to the complex plane. Okay, where they will travel? They have to go towards termination. Where is the termination? The branches terminates at open loop zeros, which are not available, or at infinity. So branches will terminate at infinity. For the branches going towards infinity, they will go in the asymptotic direction. So I have drawn the asymptotes earlier. These green ones are asymptote. The green ones are asymptote. So you have to make one of the branch from here go towards the top asymptote, so that so that towards infinity the asymptote looks like the tangent to this curve. The asymptote should look like the tangent to this particular curve. Okay, and similarly, bottom one is anyway symmetric. Root locus is symmetric with respect to the real axis. Complete. As far as the shape is concerned, the root locus is complete. As far as the shape is concerned, the root locus is complete. Okay, the root locus is complete. This branch goes, this branch goes, and it keeps on going for k tending to infinity. For k tending to infinity, it is going to approach the top asymptote, and here for k tending to infinity, it will approach the bottom asymptote. Okay, right. This is what I mean by the breakaway point. Okay, this is what is my breakaway point. Correct. This is what is my breakaway point. What is the breakaway point? I will show you the calculations of. If required, I will show you. Otherwise, the shape is complete. Okay, then when the branches are going from breakaway point towards the asymptote, in between they intersect the imaginary axis. Okay, so it is s equal to something. We can calculate that also. We can calculate that also. Okay, it intersects the imaginary axis for what values of s and for what values of k. For what values of s and for what value of k. So first of all, what is the breakaway point calculation if required? Otherwise, shape is done. Shape is done. Okay, I will specify for you that this orange one is actually the root locus branches. Okay, easy for you to remember in the revision also. These orange ones are the 3 root locus branches. Okay, and the dotted green segments are your asymptotes. These are your asymptotes. Clear? These are your asymptotes. Okay, now if I have to calculate the breakaway point, how do I calculate the breakaway point? So now let me show you the breakaway calculation, and then I will take you back towards the step. Okay, first let me tell you manually only. Breakaway point calculation. So for breakaway point, what you do, first write down the characteristic equation, which is 1 plus GSHS equal to 0. And from the characteristic equation, write down k as a function of s. From the characteristic equation, write down k as a function of s. So when you write down k, it will become minus of s, s plus 1, s plus 3. Minus of s, or even if I first solve the characteristic equation, it will become s cube, then 3 plus 1, 4s square, 1 into 3, 3s plus k equal to 0. So what is k? Minus of s cube plus 4s plus 3. Okay, and then solve dk by ds equal to 0. Okay, write down k as a function of s and solve the dk by ds equal to 0. No derivation required right now. Just keep on listening to the steps. So s cube derivative 3s square, 4 2s are 8s plus 3, and this much part should be equal to 0. So solving it, what are the values of s? Let me give you the answer directly right now. Let's not spend time on the calculation. You can calculate using the quadratic formula. Okay, so 2 roots I am getting here. Minus 0.45 and minus 2.21. Which of them is the valid breakaway point? Okay, for that already I have the breakaway point, which should be between minus 1 and 0. Now where is the breakaway? Minus 2.21 is anyways here. Minus 2.21. It is not on the root locus. Root locus on the real axis is only the orange zone. Okay, so here root locus anyway is not existing. So here it cannot be the breakaway point. So what is the valid breakaway point? Okay, minus 0.45. Okay, so what is the actual breakaway point? After drawing the root locus, it is clear also that it should be between the minus 1 to 0. And that is the breakaway point, which I will write down here. S equal to minus 0.45. S equal to the minus 0.45. Clear? That is my breakaway point. That is my breakaway point. So yeah, I first explained you the procedure up to the asymptote calculation. Step number 7, breakaway calculation. Okay, I have explained you for breakaway. Okay, you have to solve dk by ds equal to 0. solve dk by ds equal to 0, and every solution of it is not necessarily a breakaway point. For it to be breakaway point, it must lie on the root locus. So I've just like I shown you, minus 2.21 was not on the root locus, so that was not a valid breakaway point. Okay, actually breakaway point are actually intersection points. Okay, so to be more specific, there can be three cases. Okay, breakaway points are related to the intersection of the root locus branches. Okay, when I talk about the intersection of root locus branches, okay, we have three different cases. One is breakaway point. Generally, we call it as breakaway only, but to be more specific, okay, you can have breakaway points, okay, or you can have BIP, okay, that is break in points, and you may also have complex breakaway points. You may have complex breakaway points. Okay, what is the breakaway point? As I have shown you just now, the branches traveling on the real axis, they intersect and move towards complex plane. Okay, so what is that breakaway point? When the two branches which are traveling on the real axis, okay, between any two open loop poles, okay, two branches, one branch start right, one branch start left, okay, they intersect at some point and then they are moving in the complex plane. This is the breakaway appearance. This is the breakaway appearance, okay, right. It may so happen sometimes that the poles were complex. For complex poles, we calculate angle of departure, that I am going to cover for you. Okay, what may happen is, the two branches start from these two poles. Suppose they start in this direction. Okay, and they first come and intersect at a point on the real axis. So this is opposite. Actually, branches traveling in the complex plane, they come and intersect on the real axis. And suppose this is 1, 0 and this is another 0. One of the branch will go towards 1, 0 and one of the branch will go towards another 0. Okay, this is break-in point actually. When branches traveling in the complex plane, they come and intersect on the real axis and then move to the real axis. Okay, opposite cases. And there can be complex breakaway also. Complex breakaway means, say there is one branch traveling in the complex plane this way, there is one branch traveling in some complex plane this way. Okay, from bottom it is coming and they intersect here. That is complex breakaway. That point will be the complex breakaway. So this is break-in, okay, this is breakaway, and this is complex breakaway. Okay, these are the three cases possible. Okay, these are the three cases possible. Okay, I'll inform to the team that tickets are not directly with me, but yeah, I'll inform to the T Kavinash to check about that. Let's go. Okay, let's go to the next question. Let's go to the next step, sorry. Okay, then this is the odd number criteria. Already I explained you with the question. The odd number criteria. Okay, the forward poles and zeros must be odd. Okay, the root locus will exist on section of real axis if the total number of poles and zeros towards the right is an odd number. I already explained you with the question directly. Okay, now root locus, when it is going from LHP to RHP, it can intersect the imaginary axis, correct? Okay, like our root locus has intersected. And to calculate intersection with imaginary axis, you have to calculate that, using RH criteria only, which we have learned earlier. I will show you for the current question. Then if there are complex poles, I will take a question separately onto this. But if there are complex poles, okay, the branches from complex pole, at what angle they will depart, that will be known as angle of departure. Okay, this alone, independent of root locus, this alone produces question. Normally 2 marks. Given, some GSHS, what is the angle of departure or angle of arrival at complex poles or zeros respectively. Okay, so angle of departure is given by the formula 180 degree minus 5p minus 5z, where I will explain you. Just by language you may not understand. 5p sum of angles subtended by the remaining poles, 5z is the sum of angles subtended by the zeros. Just keep noting it. I'll explain you with the proper question. Okay, if there is a complex zero at a branch, the branch will terminate at a zero, branch will arrive at a zero. It arrives at the angle, if it is a complex zero, it arrives at the angle given by 180 degree minus 5z minus 5p. Okay, whereas phi z is the sum of angles subtended by remaining 0, phi p is the sum of angles subtended by the poles. Okay, by language it may not be clear. I'll show you how to solve angle of departure arrival. I will take a separate question out of this. Clear? I will be taking a separate question out of this. Now, complementary root locus, as I told you, complementary root locus. Okay, it is the root locus for negative feedback systems. Okay, negative feedback systems for k less than equal to 0. Okay, now if I talk about negative feedback system, characteristic equation remains to be same. 1 plus GSHS equal to 0, but gain k is negative. Okay, 1 plus k GSHS may be written as ns k ns upon ds. In the GSHS, what can you have? You can have some constant gain term k. Okay, you can have some numerator function which will give you zeros. You will have some denominator function which will give you poles. Okay, or it is also equal to the root locus for positive feedback systems. Complementary root locus is also known as the root locus for positive feedback system. For the gain k also taken positive only, because for positive feedback system we know that the characteristic equation is 1 minus GSHS. Correct na? 1 minus GSHS or 1 minus k ns upon ds equal to 0. Okay, so for both of them, you know what, actually n by d will come up. For both. For the first case, n by d is minus 1 by k for the case number 1, but in the case number 1, k negative. Minus 1 upon negative, overall positive. Okay, or in the second case which I am mentioning, what is n by d? What is n by d? Okay, 1 upon k, but in the second case, k is positive only. So 1 upon positive is still positive. Okay, so for both the case, n by d is positive. That means whatever is the angle. Okay, if a point lies on the positive real axis, okay, the angle is 0 degree or plus minus 360 degree. Or it can also be taken as plus minus 720 degree. Okay, if a point lies on the positive real axis. So angle is 0 because you're on x axis, or you can take a 360 degree rotation, or you can take another 360 degree rotation. So angle can be 360, 720, anything like that. Okay, that means what will change? What will change? For complementary root locus, magnitude criteria will still be the same. Angle criteria will change. Okay, magnitude criteria remains same. Okay, but angle criteria, what was the angle criteria for the regular root locus? For the regular root locus, angle criteria was, okay, odd multiple of 180. Okay, but now it is 0, 360, that is 180 into 2. So 180 into 0, 180 into 2, 180 into 4. So it can be written as, even multiples of 180 degree. Okay, so only those steps which are related with the angle criteria will change. Okay, so in the complementary root locus, if the question is on complementary root locus, only I am now giving you the changed steps. The steps will change. Angle, that means I have not written 1, 2, 3, 4. That will be same. Step number 1, 2, 3, 4 will be same. Angle of asymptotes will change. Okay, it will now be given by the formula. Make it like this, easy to remember. 2k into 180 degree by n. Earlier, what was the formula I have given you? Odd multiple of 180 by n. Now it is even multiple of 180 by n. Even multiple of 180 by n. Okay, next. Okay, existence of root locus on the real axis. Existence of root locus on the real axis. So now it will follow even number criteria. Rather than odd number criteria, just now I have shown you odd number criteria. Now it will be even number criteria. Okay, that the total forward poles and zeros must be even in number. The total number of forward poles and zeros must be what? Must be even in number. Clear? Okay, next. Angle of departure. That 180, the formula that I have shown you was 180 minus 5p minus 5z. 180 will become 0. That means only minus of 5p minus 5z, and angle of arrival also minus of 5z minus 5p. But how to calculate 5p, 5z? I am telling you, I will take with a question and explain you the 5p and 5z calculation. Okay. Then this was a question we were solving. We have done all the required steps. Okay. Even breakaway point I have calculated. Okay. I have shown you the breakaway point here. Okay. One more thing let me calculate. This root locus intersects with the imaginary axis for what value of s? I told you, intersection of root locus with imaginary axis. Step number 9, to be solved by RH only. To be solved by RH only. So already I know the characteristic equation. Okay, if I apply RH to this characteristic equation. Okay, if I apply the RH to this characteristic equation, s cube plus 4s square plus 3s plus k equal to 0. Okay, if I apply the RH, s cube s square 1 3 4k, s power 1 12 minus k by 4 0, last element s power 0 x into k by x, k and 0. Okay, for imaginary roots, okay, if you want imaginary axis intersection of root locus, okay, that means imaginary axis if you intersect, that means characteristic equation has j omega roots. Imaginary roots can come with auxiliary equation, and auxiliary equation can come with ROZ. ROZ is always in the odd power. So what is the odd power row? S power 3 is fixed. Okay, we can, there is the parameter k here. Okay, so what we can do, we can choose 12 minus k is 0. If this is 0, then entire row will become 0. So k equal to 12. What are those j omega roots? To obtain the j omega roots, we need auxiliary equation. 4s square plus k equal to 0. 4s square plus k is 12 equal to 0. So s square is minus 3. What is s? Plus minus j root 3. What is s? Plus minus j root 3. Clear? The s is plus minus j root 3. So if I come here, see, this is point s equal to j root 3. Now clear? For k equal to 12. And this is the point s equal to minus j root 3. And this occurs for k equal to 12. For k equal to 12. Clear? Okay. One last calculation from the same root locus only I'll explain. What is the value of k at the breakaway point? Okay. For this, let's calculate what is the value of k at the breakaway point. Breakaway point is obtained. Okay. For the same question, extending one more case here. Okay. Find the value of k at the breakaway point. See, this is again important. Breakaway point is ultimately a point on the root locus. Breakaway point is ultimately a point lying on the root locus. And any point lying on the root locus. So there are two methods. Any point lying on the root locus. Okay. To calculate the value of k for any point lying on the root locus, method number 1. Satisfy magnitude criteria. What is the magnitude criteria? Mod GSHS equal to 1 at that point. Satisfy the magnitude criteria. Okay, and method number 2, coming from magnitude criteria only, derived from magnitude criteria, method number 2, you can note down the formula. K is given by product of distances of all poles with respect to that point, whatever point is given, product of distances of all pole with respect to that point divided by product of distances of all zeros, with respect to that point. With respect to that point. Okay. Product of distances of all poles with respect to that point divided by product of distances of all zeros with respect to that point. Correct. Okay, so if I show you this calculation here, okay, let me duplicate this and show you the calculation separately so that you understand it. Let me duplicate this particular point. So what I'm telling, product of distances of all poles with respect to that point. So what my question was? My question was find the value of k at which point? At the breakaway point. Okay, at the breakaway point. This is my breakaway point. Correct. This is my breakaway point. Okay, so from this point, see, from this point, what is the distance with respect to the first pole? Suppose this is P1. Distance of this point with respect to the second pole, suppose that is P2. And distance of this particular point with respect to the third pole. This is P3. Is there any zero? There is no zero available. There is no zero available. Forget all these calculations I have written on the earlier root locus. Okay, so what is the value of k? Okay, at the breakaway point, what is the value of k? It is the product of the distances with respect to poles P1, P2, P3. P1 into P2 into P3 divided by okay, the product of distances with respect to zeros. But if there are no zeros, denominator is 1. Okay, the denominator will be 1 if there are no zeros. Okay, so k is how much? Now what is P1? See, this point is minus 0.45. Okay, so minus 0.45 to 0, distance is 0.45. Then minus 0.45 to minus 1, so absolute distance will be 0.55. And minus 0.45 up to 3. So 3 and 0.45, both are minus, 3 and 0.45 distance will be 2.55. Okay, so how much is k? Calculate approximately and write down the answer. Roughly 0.63. Roughly 0.63. So this is the value of k. Okay, at any point along the root locus. I have explained with breakaway point, but there are direct questions out of it. Given this point lies on the root locus, find the value of k. You don't have to draw root locus for it. You can draw the pole zero diagram and solve it, or if GSHS is given, just satisfy mod GSHS equal to 1 at that point. Okay, so this is the breakaway point, s equal to 0.45, and which occurs for k equal to how much? 0.63. K equal to 0.63 is the value I can write down here. Oh, good to know that, Venkat, you are studying hard up to this time. Yes, guys, all of you, I appreciate you. It's almost 8 hours complete for the marathon, I would say. It's almost 8 hours complete. Okay, now, before I move forward, as I told you, before the break also, the password for today's PDF, I think I told you margin. Yes. The password for today's PDF is going to be margin. Then let's go to the next question. Okay. Those who have done that much of effort, that much of sincerity, almost attending 8 hours of class. Okay. The password is there for you. That is margin. M-A-R-G-I-N. M-A-R-G-I-N. The password will be margin. Okay. M-A-R-G-I-N. Everything in small. Okay. The PDF which will be shared in my Telegram group. Maybe if my energy permits, I'll share the PDF tonight, or otherwise by tomorrow I will share. Okay. Yeah. Take this next question. Telegram link I shared. Now I'll share it once again. I'll share the Telegram link once again. You're going to find the PDF in this Telegram. Here is the Telegram. Please note that. You can join the Telegram group. Okay. Chalo. Next question. A unity negative feedback configuration has the open loop transfer function GS equal to S square plus 2S plus 2 upon S square minus 2S plus 2. Find the angle of departure for complex poles and angle of arrival for complex zeros. Both I am covering in the same question. For k between 0 to infinity, and for minus infinity less than k less than 0. Okay, so your angle of departure and angle of arrival. Angle of arrival and angle of departure. Both let me explain to you because it will have both complex poles and complex zeros. Okay, for that first let me calculate the poles and zeros. What are the zeros actually? S will be equal to minus 2 plus minus root over b square minus 4ac divided by 2a. Okay, so minus 2 by 2 minus 1 and plus minus j. These are the zeros which will be on the right hand side. If I talk about the poles will be zeros were in LHP, I'm sorry. 2 plus minus root over b square minus 4ac by 2a. So that is going to be 1 plus and minus j. 1 plus minus j. Under root of 2j by 2 is j. 1 plus minus j. The poles are 1 plus minus j. One plus minus j. These are the values of the poles. Correct, dear? These are going to be the location of the poles. 1 plus and minus j. 1 plus minus j. Now, let's draw the pole zero diagram and first talk about the angle of departure. Okay, let's cover one by one. Okay. Okay, but anyways, departure or arrival, first I need the pole zero diagram. So I'm just drawing the pole zero diagram first. Yeah, just a second. I think some error is happening. Yeah. So this is the angle of, not the angle of departure. I've just drawn the axis right now. And what are the poles and zeros? Okay, the zeros at minus 1 plus minus j, poles at 1 plus minus j. Okay. Poles at 1 plus minus j. 1 plus j and symmetrically 1 minus j. And zeros minus 1 plus j and conjugate 0 minus 1 minus j. Okay, so angle of departure and angle of departure is calculated for complex poles. Okay, the formula that I have told you, dear, is 180 degree minus phi p minus phi z. If I take for root locus. First, what is phi p and what is phi z? So suppose, let me calculate the angle of departure. Take a particular pole. Okay, take a particular pole. Okay, 1 plus j. Take the pole in the upper half plane for simplicity. What is the first thing you will do, dear? Join this pole with respect to all the other poles and zeros. Join this with respect to all the other poles and zeros. I join it here. Okay. Join it here and also join it here. Okay. Now, join this particular pole with respect to all the poles and zeros. Okay. Okay, suppose this is my pole of interest. Okay, this is my pole of interest. I'm talking about this one. Okay, now when you have joined, make sure that the direction of the line is towards that particular pole. I'm telling you a simple geometrical method. When you join, okay, with respect to that pole, make sure the direction of the line is towards the pole. Okay, now what is phi p? As I told you, phi p is the sum of angles subtended by the remaining poles. This is the pole whose angle of departure is calculated. So what is the remaining pole? 1 minus j. So what is the angle of this line? Angle with respect to positive x-axis. So this becomes phi p. Phi p1. Only one other pole. Na? Okay, so what is the angle of poles? Phi p, which is only phi p1. If there were multiple poles, multiple other poles, we will add all of them. And what is this phi p1? It is 90 degree. Because it is a vertical line. Vertical line. So phi p1 90 degree. Similarly, when you are going to calculate phi z. Similarly, when you are going to calculate phi z, what will happen? Phi z is the sum of angles subtended with respect to zeros. So there are two zeros. Okay, let's say this is the z1. Let's say this is the z1. Let's say this is the z2. Okay, so these are the two zeros, correct? These are the two zeros. Okay, these are what are the two zeros. Okay, so with respect to these two zeros, let me write the z1 and z2. Okay, with respect to these two zeros, what is the phi z? Sum of angles, okay, subtended by both the zeros. So what is phi z1? Now see, the line joining the z1 to the pole is parallel to x-axis to how much angle? Okay, because it is in the x-axis direction to 0 degree. 0 degree, but phi z2. Okay, phi z2. What about phi z2? Okay, so what is the angle of this line with respect to x-axis? This angle will be phi z2. This angle will become phi z2. So what is that phi z2? What is the phi z2? Okay, so phi z2 will become, okay, this will become how much? Let me calculate it here only. This will be given by tan inverse of how much? Tan inverse height. Height is y coordinate 1. Base is also 1, x coordinate 1, and tan inverse 1 by 1 is 45 degree. Okay, so phi z is 45 degree. Now dear, phi p and phi z are both ready. Phi p and phi z are both ready. Now let me give you the answer. There are two cases I told you. Okay, calculate for k 0 to infinity. That is the regular root locus. Calculate for k minus infinity to 0. That is complementary root locus. Okay, so if any one question will be there for you. If I talk about the root locus condition, that is 0 less than k less than infinity. What is the angle of departure formula? It is given by 180 degree minus of phi p minus phi z. Okay, so what is the angle of departure? It will become 180 degree minus phi p 90 and phi z 45. Okay, so 91 is 45, 45. Further you subtract, so 135. That is your answer. Angle of departure 135 degree, close. Close. Okay, now dear, remember this is the angle of departure for which pole? Okay, for the pole 1 plus j. Okay, for the pole in the RHP, that is 1 plus j. This is the angle of departure for the pole that is in RHP 1 plus j 135. If I ask you for the other pole, you don't have to repeat the calculation. Okay, for the conjugate pole, if you know the angle of departure for x plus jy, for x minus jy, it will just be minus theta, just a sign change. Okay, so if this is 135, the below one is going to be minus 135. The below one is going to be minus 135. Clear all? The below one is going to be minus 135. That should be clear to all of you. The below one is going to be minus 135. Minus 135, right? Okay. The below one will be minus 135. The below one is minus 135. Okay, if the question was on complementary root locus, okay, that is minus infinite less than k less than 0. The background calculation will be same only. Only thing is the angle of departure formula, as I told you, is minus of phi p minus phi z. Okay, so that is minus of 90 minus 45 and that will be minus 135. That's it. Okay, so this is the angle of departure with respect to the pole 1 plus j minus 135, and the angle of departure for the conjugate pole will be opposite in sign, so that will be plus 135. Plus of 135. Clear? Okay, so these are the two cases. Now coming to, this was angle of departure. Okay, now coming to angle of arrival. Okay, now coming to the angle of arrival. What I want is the similar pole zero diagram. So at least let me take that once again. Yeah. So angle of departure is clear. Now angle of arrival, similar approach. Let me conclude to angle of arrival also. Okay, so now I am calculating angle of arrival, of course, for complex zeros. Angle of arrival for complex zeros. Okay, for the complex zeros. For the complex zeros. Okay, No, I think even these lines won't be required. So I'll have to redraw only. Better forget this, because the lines will also go opposite. The zeros are opposite. So this is not required. This entire thing. Why it is not picking up this element? Okay, yeah. So we have the 0 at -1 plus j. Suppose this is my important 0 where I want to calculate the angle of departure. Angle of arrival, sorry. Okay, let us say this is its conjugate part. Okay, 1 -1 minus j. And here we had the poles, that is 1 plus j, and its conjugate part. Which is 1 minus j. Okay. Now suppose I am interested in calculating angle of arrival for -1 plus j. Okay, but for angle of arrival, again what I need is phi z minus phi p. Now what is phi z, phi p? Now let's come here. What is phi z? Phi z is the sum of angle subtended by this 0. Suppose this is the 0 which I am calculating angle of arrival for. Okay, sum of zeros, sum of angle subtended with respect to remaining 0. So remaining only 1 0. Okay, so what is the angle of this line? I told you, make sure that the angle of the direction of the line is towards that particular pole or 0. So right now I'm calculating for 0. So all the lines direction should be towards that 0. Okay, and this becomes my phi z1, which is vertical 90 degree. So phi z is only phi z1, only one other 0, and that is a vertical line, so 90 degree. But if I talk about phi p, it will be phi p1 plus phi p2. There are two poles, so sum of angles subtended with respect to the pole. Suppose this is P1, suppose this is P2. Okay, very clearly what is phi P1? 180 degree, because phi P1, the direction of this line is anti-parallel to x-axis, opposite towards negative x-axis. So towards negative x-axis, 180 degree angle. Okay, what about phi P2? The phi P2, okay, now phi P2, this is phi P2. First let me show you. The angle is always taken with respect to positive x-axis. Okay, so this much is P2. Okay, so this is the exterior angle of triangle. So better calculate this interior angle. Tan inverse height 1, base is also 1, and 180 minus this will be the answer. 180 minus the interior angle. The interior angle, which is tan inverse 1 upon 1. Okay, so 180 minus 45, so 135 degree. So what I have done right now is phi z and phi p calculated. Okay, phi z and phi p. Now angle of arrival. Okay, angle of arrival, if the question is on root locus, see, any one question will be there for you. Okay, so if it is k positive, root locus, if it is k positive, what is the angle of arrival? What is the angle of arrival? 180 degree minus of phi z minus phi p was the formula told. 180 degree minus phi z minus phi p. What is the phi z? 90, and phi p is 135. 90 minus 135. So total minus 45 minus plus, so 225 degree. Now again, angle of arrival for which 0? This is for the 0 minus 1 plus j. For the 0 minus 1 plus j, if this is 225, okay, what is the angle of arrival? For the conjugate 0 will be same magnitude, but just only a sign change, so minus 225. And last answer, if it was a complementary root locus question, that is the range of k minus infinite less than k less than 0. Okay, the angle of arrival formula, as I told you, angle of arrival formula is only of minus of phi z minus phi p. Here reverse, phi z minus phi p calculation. Okay, so this is equal to minus of phi z. Phi z was 90, phi p is 135. Minus of 90 minus 135 minus 45 minus plus. Okay, so dear, angle of arrival for which 0? Okay, for the 0, minus 1 plus j is 45 degree. Okay, so angle of arrival for minus 1 minus j will be minus 45 degree. Minus 45 degree. will be minus 45 degree. Minus 45 degree. Clear? So these are the answers of angle of arrival. Okay, earlier one was the answer for the angle of departure. Angle of departure. Oh, dear, here there is a correction nobody even noticed. This is 90 minus 45, minus 45 only, dear. Okay, dear, there was a correction, nobody noticed it. I will change it right now. Angle of departure for complementary root locus, minus 45 degree and plus 45 degree. I think nobody noticed, but yeah, that's a correction. Or I think Avinash is mentioning that 45 for same only. Yeah, so this is what it is. Okay. I hope the procedure is clear. So I have covered both angle of departure, angle of arrival for root locus or for complementary root locus. Any one case will come to you. Maybe angle of departure only. That too for either 0, either k positive or either k negative. Okay. Any one such case can come to you. Okay. The damping ratio with respect to the root locus. The damping ratio with respect to the root locus. Okay. Characteristic equation of a unity negative feedback system is given to you. Okay. The characteristic equation is 1 plus kgs equal to 0. It's a GATE 2 mark question also. The open loop transfer function GS. Okay. The open loop transfer function GS has one pole at origin and two poles at minus 1. Okay. So how the characteristic equation will be looking like? The characteristic equation actually will be 1 plus kgs. Okay, where GS has one pole at origin and two poles at minus 1. That means there are no zeros mentioned. So one pole at origin and minus 1 means S plus 1 is the factor that should be repeated. Two poles at minus 1 are there. The root locus for varying k is shown in the figure. Okay. The constant damping ratio line zeta equal to 0.5 intersects the root locus at the point A. Okay, at the point A. The distance from origin to the point A is 0.5. What is the value of k? Value of k at any point A. Point A is a point on the root locus. So value of k at any point on the root locus. I have told you, na? Let's understand this question, dear. Okay, so there is this root locus given to you. These are the two poles. There is a pole at origin and there are two poles at minus 1. Okay. Okay, these are the two poles at minus 1. Remember, these are repeated poles. These are repeated poles. Correct. How the root locus is given, if the picture may be slightly unclear, I'll overlap it. This is the root locus branch of the real axis that is given, and then this is some breakaway point after which the root locus branch is moving in this direction and in the negative direction here. Okay. There is a constant damping ratio line. There is this constant damping ratio line. This is zeta equal to 0.5. This line is what is given as, this is the line given as zeta equal to 0.5. But remember, zeta is cosine of phi. Remember, zeta is cosine of phi. So what should be phi? Phi is 60 degree. What is the angle phi? As I told you, okay, when you join any particular point with respect to origin, the angle of that point with respect to negative real axis was phi. In the transient part, I explained you the phi. Okay, so this is 60 degree. Okay, this coordinate is minus 1 by 3 and this is the point A. The zeta equal to 0.5. What they have mentioned, the line zeta equal to 0.5 intersects the root locus at the point A. Okay, the distance of A from the origin is 0.5. Okay, what is the value of k at the point A? Let me actually separate out this triangle. Okay, to solve it more easier, let me separate out this triangle actually. What triangle? See, what triangle? This is the point A, this is the origin, and let's say this is some point B. Okay, let's say this is some point B. This is given the distance of point A from origin, and this angle is indirectly given as the form of zeta. Zeta is 0.5, so this angle is 60 degree. So can you calculate the coordinates of the point A? Why not? Hypotenuse given. We can calculate the coordinates of the point A. Suppose the point A is x comma y. It is in second quadrant. No? The point A is minus x comma y to be more precise. Okay, to be more precise. Okay, so what is the value of cos 60 degree? Cos 60 degree is base upon hypotenuse. Base means the magnitude of x coordinate upon hypotenuse is 0.5. Okay, so x is how much? Cos 60. Cos 60 is also 1 by 2. 5 is also 1 by 2. So x is 1 by 4. Okay, and similarly, if I use the sine 60 degree, okay, which is opposite side, that is the y coordinate, upon hypotenuse, which is 0.5. So y will be equal to sine 60 degree, which is root 3 by 2, 0.5 also I'm writing 1 by 2, root 3 by 4. Okay, so this coordinate is respectively now minus 1 by 4 and root 3 by 4. Now question is, what is the value of k at the point A? What is the question now? The question is value of k at the point A, which is minus 1 by 4 root 3 by 4. And what is the value of k at any point? What is the value of k at any point? Now, it is given by the same product of distances with respect to all the poles divided by product of distances with respect to zeros. Again, zeros are not there. So these are the two poles. Again, I'll try to draw a separate diagram for you. See here. Okay, this is one pole at origin, and then there are two poles at minus 1. These are two poles at minus 1, and this is your point A. This is your point A. Okay, so what is the distance of point A with respect to the first pole? Suppose this is P1. Distance of the point A with respect to the second pole, suppose P2. Okay, so the answer, the value of the k at the point A, is P1, okay, into P2, because there are two poles, distance with respect to every pole. So P2 is divided, P2 is repeated, divided by distance with respect to 0, and there are no zeros, so denominator will be 1. Same formula. Okay, so the answer actually has to be P1 into the P2 square. Now what is the P1? What is the P1? We know the coordinates, na? This is origin 0, 0, A is minus 1 by 4, root 3 by 4, and this is the point minus 1, that is on the x-axis minus 1, 0. So what is the value of P1? Distance formula. The P1 is root over of x square, that is minus 1 by 4 square, plus root 3 by 4 square, into P2 square. So when you take square, under root not required. So distance formula, minus 1 by 4, minus plus 1, x2 minus x1 whole square, y2 minus y1 whole square. Okay, so how much? 1 by 4 plus 3 by 4. So 1 plus 3 divided by 16. Okay, into, this is 3 by 4. 3 by 4 square, 9 by 16. Root 3 by 4 square, 3 by 16. Okay, so this is 1 by 4. So under root 1 by 4, 1 by 2 into 12 by 16, that is 3 by 4. So net value of k is actually 3 by 8. NAT question it is 0.375. 0.375. 0.375. Again, the value of k at any point given by the formula product of distances of pole divided by product of distances with respect to zeros. And zeta with respect to root locus can be again related with the concept zeta equal to cosine of phi. Great to know, Murali. Okay, this is a good question of GATE 2 marks. Okay. Guys, not really much questions. I'll just go to one topic. Not really, you get a lot of questions, but only thing is formulas I will brief to you. Okay, resonant peak and resonant frequency. Okay, the frequency at which the maximum amplitude of, oscillation will occur, okay, is known as the resonant frequency, and the maximum value of mod Tj omega is resonant peak. And if you come to the second order system, okay, okay, where my transfer function is of the format omega n square upon s square plus 2 zeta omega n s plus omega n square, or when you convert to the frequency domain, Tj omega will become omega n square, denominator omega n square minus omega square. This will become s equal to j omega. So minus omega square plus j to zeta omega n omega. Okay, and then for maximum, okay, what we need, what is a simple approach for maximum value of this magnitude? First we find the magnitude function. Okay, but for the maxima, always we have to solve for the stationary points. Okay, that is d by d omega of the mod tj omega function equal to 0. Solving with the formulas that you get here. The formulas that you get here, if zeta is less than 1 by root 2, okay, the omega r is given by omega n root over 1 minus 2 zeta square. Mr is given by 1 by 2 zeta under root 1 minus zeta square. For Mr, again a simple way to remember the formula. For Mr, again a simple way to remember the formula is it is cosec 2 phi. See, put down zeta as cos phi. So 1 minus cos square theta sin theta. So 2 sin theta cos theta. 2 sin theta cos theta is sin 2 theta and 1 upon sin is cosec. Okay, so for easy remembrance, you can remember resonant peak given by the formula cosec 2 phi. The resonant peak given by the formula cosec 2 phi. Okay, and for any zeta greater than equal to 1 by root 2, the resonant frequency is 0. The maxima is only obtained at the 0 frequency, and that resonant peak, the maximum value is 1. Actually, if you look into the MATLAB graphs, okay, if you look into these graphs, okay, these are some graphs taken from MATLAB, okay, that for any zeta which is less than 1 by root 2, okay, that is why for clarity I have drawn separate graphs. So for any zeta less than 1 by root 2, you get the peak value. The magnitude rises, okay, from, from 1, it rises to a peak and then decreases. But for any zeta greater than 1 by root 2, okay, the maximum magnitude is 1 and thereafter it is just a decreasing function. Thereafter, it is just a decreasing function. For different values of zeta, different graphs have been taken from MATLAB. Okay, also please note that if zeta is increasing, see 0.1, 0.2, so what is happening? If zeta is increasing, Mr is decreasing, the peak value is coming down, and as well as omega r. Omega r is the frequency at which you get the peak, so the frequency is also coming left. Towards left means frequency is also decreasing. So if zeta increases, Mr and omega r both will decrease. Omega r and Mr and omega r both will decrease. Okay, for up to zeta less than 1 by root 2, because beyond that, so both are constant only. Okay, so sometimes, not very commonly, but you can expect the questions out of this formula. If you are using the Mr formula in terms of phi, cosec 2 phi, so what is the condition of phi? You must remember. Okay, zeta, we know that is cos phi. Okay, because zeta is cos phi, zeta less than 1 by root 2 would mean phi greater than 45 degree. So you can use the formula phi greater than 45 degree. Okay, in terms of phi, so Mr is cosec 2 phi. In terms of phi, the Mr is cosec 2 phi. Right. So, not taking any problem, but, just I have given you as the basic revision in the notes. Okay, now for 1 or 2 topics, I'll tell you important thing, guys. So as you know, these mega marathons are live from today, 13th of January. Okay, so next marathon, important updates first. Next marathon will be 15th of January. Okay, that will be day after tomorrow, EMF. Okay, and that marathon for you will be, okay, from Hemant sir. That marathon for you will be from Hemant sir. EMF. Okay, the EMF marathon. Clear? Right. And also 14 Jan, that is tomorrow. Okay, I will plan a session on control systems MSQ questions. See, today we have done lot of revision. Okay, today we have done the transient discussion, steady state part discussions. Okay, Routh-Hurwitz criteria, root locus is discussed, Nyquist plots and polar plots are discussed, and gain margin, phase margin concept discussed. Resonant peak and frequency I have not discussed detail, but I have given you the formulas. Okay, now Bode plots. Bode plots. Okay, so guys, it's almost 8.5 hours. Okay, it's almost 8.5 hours. I'll be yes. Next, we'll keep telling you the updates. Okay, Gautam sir will be taking analog circuits marathon as well. Okay, so I am just shared a link to you. Okay, if you are just very recently, maybe a week back, I took a class on Bode plots. That is sufficient. That is sufficient to cover up Bode plots. Okay, just around a 1 hour class it is. Okay, just around a 1 hour class. Okay, numerics from controllers, compensators are very rare these days. Okay, so at least I wanted to cover up the important areas. Okay, Bode plot is important. Bode plot is important. Okay, so controllers, compensators, anyways I did not plan to cover. That's easy part, you can study on your own and not that important also. Okay, in MSQs I will bring up the question of controller compensator. Okay, in the MSQ session I will bring up the question. Okay, state space analysis takes lot of amount of time. Okay, the controllability, observability, I took it very recently, so at least you can watch it, guys. That's what, it's more than 8 hours, 8.5 hours also. Okay, so the best I could do is cover up these many topics. If you are demanding state space analysis, let me see if I can plan a separate session onto it. First, let me cover up the signal and systems. That is again a big subject. Okay, but yes, if the bandwidth permits, I will plan up a state space analysis separate session. Okay, for state space analysis, I'll try to plan a separate session, okay? For the state variable analysis especially. Okay, for the state variable analysis, I'll try to plan up a separate complete session. Okay, so that we quickly revise. Many of you are demanding onto that. Bode plots, I took it recently only, just a week's back time, I think. Okay, so Bode plots, it's sufficient. That session is sufficient for Bode plots, okay? Okay, that question is sufficient. So I'm again sharing the link. That is the Bode plot. So you can continue right now only. If you have the energy, go and watch that 1 hour Bode plot. That also will be finished for you in a sense. So you can finish up the Bode plots also. State variable, I'll try to manage another session for the state variable. But out of that also, important concept of controllability and observability I have taken soon. I have taken, maybe 2 weeks back, I have taken the controllability, observability. Okay, so if you are interested, you can watch that. Let me see if I am able to find the link of it. I'll share you. So at least the controllability, observability. Because even if I start state variable analysis, it cannot be finished within, it cannot be finished just like that within 1 hour. Even 1 hour, it will be less. Okay. Because all state models, CCF form, OCF form, DCF, JCF, all that. So controllability, observability, actually I took 2 sessions. I've taken 2 sessions. Okay. I've taken the 2 sessions for controllability and observability. One is on the Kalman's test and one is on the Gilbert's test. One is on the Kalman's test, one is on the Gilbert's test. Okay, so I have shared you both the links, so you can watch that Kalman's test and Gilbert's test. For both the things I have taken. PDF I'll share in the Telegram. The Telegram link I've shared once again in front of you. The PDF, the password for the PDF. As I told in the beginning, I'm telling one more time. The password for the PDF is going to be margin. Everything in small. MARGIN. Okay. Right. Correct. No. Any one method I will not say. Kalman's is enough, but sometimes Kalman's is lengthy. The most general method is Kalman's. Okay. Never stop learning. So I will suggest you go through both. Total it is, will cover up every possible case of controllability, observability. Okay, Gilbert's is only for DCF and JCF. Kalman's can be applied everywhere. Okay, but for DCF, JCF, if you learn Gilbert's, your answer is in seconds. And especially from DCF, JCF, you have earlier got 3x3 questions in GATE. 3x3 solving using Kalman's will be pretty much time consuming. That is why Gilbert's is important. Okay. So guys, as I updated you, the GATE 2026, the regular offline first batch for GATE 26 offline coming up from February 24th. You can enjoy 4,000 additional flat early bird discount if you register till the end of this month, 30th of this January. And the online live course starts 8th of February. Okay, for GATE 26 and GATE 27, if you want to learn in the live manner, okay, we are going to have the course for 1 year and 2 year validities respectively. Again, 25% additional discount till 30th of January. Okay, and for OHM online courses, especially you have the OHM online scholarship test. This is just coming Sunday, next Sunday, 19 January, 6:30 p.m. Okay, where the top 3 performers will be getting flat 100% scholarship on the live courses. And then based on your rank, you still have fascinating scholarships that you can, just have to prove and earn your respect, earn your scholarship. The syllabus includes basic subjects, which is mentioned on screen. Okay, as I mentioned you in the beginning also, if if you or your friends are planning for AE batches, for AE examinations, okay, whether Telangana state or whether AP state, okay, so the new batch for AE starts January 23rd. Okay, the new batch for AE exams, okay, TG Transco, TG Discoms as well as AP Transco and AP Discoms starts 23rd of Jan. Okay, for any more queries about the batches, you can contact 95156940053. And thanks a lot. This is again the link of the Telegram, which I have already shared for you. Hope you enjoyed it. 8.5 hours non-stop. Okay, 8.5 hours non-stop. Hope you have enjoyed it. Okay, do not forget, still to share this video to all your friends. Okay, to all your friends, those who are preparing. Okay. And yeah, hope this marathon, the control system marathon, helps you a lot, boost the reason that we are putting up the marathon, that your performance in the examination is boosted. Okay, you somehow improve on some of the performance parameters. Okay, of course I could not cover 100%, but yeah, that's what even in the yesterday's launch session we told you, we'll cover as much as possible. So it's 8.5 hours. I did not stop at 4 hours, 5 hours or even 6 hours. I went as much as possible. So I hope you also understand that, the time constraint, but I'll see if time permits state space, I'll take session, because first my target will be completing signals, which will be happen after EMF. So exact date of signals will inform you. That's why, guys, if you are still not subscribed, okay, subscribe to the channel so that you don't miss any event. Okay, EMF is going to come up, signals is going to come up. For electrical students, machine, power system, power electronics is going to come up. For EC students, again, EDC and analog marathons will come up. So you should be aware and updated, okay, of all the activities happening on the channel. Okay, so stay subscribed, stay safe, take care, all the very best. If you really attended and if you really enjoyed and if you feel that yes, your performance is boosted, do not forget to press your attendance, and your attendance is as simple as the like button. Okay, like the session. Okay, if you gain something out of the session. Okay, and thank you. Bye bye. See you next in the Signal and System Marathon. And as I'm telling you, for tomorrow, I'll try to plan, mostly I'll plan only, that is the Control System MSQ practice session. Control System MSQ practice session, and that we will plan in the evening hours. That will not be starting from morning. Okay, that we'll plan in the evening hours. Okay, around after 5-6 p.m. Okay, so everything, if you are subscribed, you will come to know the timing and everything, and I'll share in the Telegram also, the Control System MSQ. But let's see how many of you are attending the MSQ session, because again, if you take the MSQs also seriously, then same we will keep repeating for different subjects. Like if you really like that MSQ sessions are helpful for you, then we'll plan it for EMF also, we'll plan it for signals also, for other subjects also we'll plan up. So let's see tomorrow how much are you attended for the MSQ sessions. Okay, and tomorrow so mostly I'm taking. Then if you really enjoy, if I feel that students are really looking for MSQ questions, and that too after the subject, it is goodness. So today we have revised a lot. Okay, let's see how much you respond in the MSQ, then we'll plan for other subjects. Okay, this is Rakesh Salreja finally signing off. Bye bye. Thank you. Stay safe and do take care of yourself.